the delay. Uh, will might start after 10 minutes. Thank you. This is screen is not showing. Acha, okay. Let's start. Good morning and namaste to everyone. A, ve- a very warm welcome to the RIS workshop. A very warm welcome to the RIS workshop organized by COMET Foundation in technical collaboration with TSDSI and support from Bharat6G Alliance. I am Tushar Kulsrest from TSDSI, your host for the workshop. So before we begin, here are a few hygiene announcements. This workshop is being recorded and will be posted on the TSDSI website within the next few days. Speakers are requested to kindly deliver your presentations within the allotted time durations. Participants are requested to type their questions in the question tab in the tool. This workshop will provide a platform for Indian researchers and industry working in the field of RIS to exchange ideas, demonstrate COMET testbed facility capabilities to the Indian researchers and industry, and making it open for use and identify the needs of the community from this testbed. It will discuss global and domestic standardization activities in RIS to enable Indian researchers and industry to contribute on the same. So we'll begin the workshop with the inaugural session. I kindly request the presence of the following distinguished individuals for the inaugural session. Mr. Sridhar P, Triple IITB Comet Foundation, Professor Debabrat Das, Triple IIT Bangalore, Mr. Rajesh Pathak, Bharat6G Alliance, Mr. R. Prakash, TSDSI, Mr. G.K. Sutar, DOT. Please join us on the stage as we commence this workshop. I now invite Mr. Sridhar P, Triple ITB Comet Foundation. Mr. Sridhar obtained his master's MTech in Control and Instrumentation. Mr. Sridhar P obtained his master's MTech in Control and Instrumentation from Triple IT Bombay and his bachelor's in Electrical Engineering from IIT Kharagpur. He has about 35 years of experience in the technology industry and has worked in techno managerial roles, fostering a culture of collaboration with focus of achieving shared goals. Sir will chair this session. Sir, now the floor is yours.
Thank you, Tushar. And welcome to all the participants. I welcome with the dignitaries on the stage, Mr. G.K. Sutar, DGM Technical from DOT, Director General of Bharat6G Alliance, Mr. Rakesh Pathakji, uh, Prakash R, who actually wears many hats, but we actually work closely with CDOT, and he's been supporting Comet in various roles. But right now, today, is joining as part of the supporting TSDSI, right? So thank you. I welcome you. I welcome the people from the industry. I can see Jishnu from Tejas, and some of you I've just got introduced. I may not know your names offhand, but Dr. Tapas, Anil, and I think Anandya, Professor Arzad, Professor Prem, Professor Vinod, my fellow colleagues of COMET, all the participants, academic participants from who are online today, all the industry participants from online, and everyone here. Welcome to this session, and thanks for joining in today. Today marks a day where we at COMET, in collaboration with TSDSI and Bharat6G, as well as some of our collaborators, are opening up the RIS test bed. And this is a platform for exchanging all the different work which is happening on the RIS and we would like to see the session fruitful in engaging and bringing the collaboration perspective of where to do with respect to the future developments of RIS as well as what has happened so far. Thanks, and great to see all of you together. And I do welcome once again on behalf of Professor Das, who is going to be joining in a few minutes, and on behalf of IIIT Bangalore and IIIT COMET Foundation. Thank you. I now invite Mr. Rajesh Patak to say a few words and let us know what is happening with respect to Bharat 6G as well as the developments towards how RIS can impact.
Uh, Namaskar and very good morning to participants here, distinguished speakers, and all online participants. So, what's important that this RIS, I'm not technical person, so I won't be discussing much or even covering this topic. But what is important that how can we make or develop more and more standards from India for India and for the world. So coming on these lines, we have to make our efforts for supporting startups, entrepreneurship, liberalized funding. On these lines, I recall 2018 when DOT came up with the Making India 5G Ready report on 5G. At that time, DST, they said that they are bringing a proposal in which they'll be working on cyber physical systems for so many 5G applications. So I remember Professor uh, Astosh Sharma sir was heading as a secretary of DST, and 5G high level forum was having co-chaired by DOT, Mighty DST altogether. And this COMET is one of the institution in wireless technology. But I feel that all those 25 institutions set up by DST, maybe in 2020 or so, they are all relevant for connectivity. Because if you discuss any applications in 5G, in 6G, they say that we are here to solve societal problems. So naturally, if you say Comet is one of the wireless technologies, I think someone is working on robots also, someone is working on even chemical and all those things or health. They are all connected with the wireless technology. So I think we have to work with all those institutions to make them that their communication portion will be taken care of. That is the first thing. Earlier, Department of Telecommunications, they were mostly not funded startups or academia. So they started with the 5G indigenous 5G testbed around 2018, and 5G was their first standard one can say, which is part now release 17 of 3GPP. Mighty has a history of funding academia and to start up through their incubation centers, and same is the case with DST. However, Now, Department of Telecommunication has a fund of more than 500 crores each year. That is a 5% of USOF, Universal Service Obligation Fund, which can be utilized for the funding startups, academia, pilots, including demonstration of technology. And the 100 5G use case labs, which were funded by Department of Telecommunications last year or so, they were from another fund. However, the time has come that we utilize the USO fund liberally for development of use cases through institutions like COMET and other those 100 institutions. Bharat 6G Alliance, one can say, is a research alliance in which we bring together TSP, telecom service providers, startups, academia, industry, and other institutions like hyperscaler, test instruments vendors to discuss that what all required for the development of a wireless technology. It can be 6G, AI, quantum, or any technology. Presently, we have about 77 members, and the work is being done through 7 working groups on spectrum technology, spectrum policy, technology, network technology, device technology, applications, use case, green sustainability, and they are headed by industry, academia, startups together. We have already given the recommendations to the government what will be their spectrum roadmap for 2030. So it's more important for any technology that the roadmap or your vision for 10 years should be very clear. Otherwise, if you just start technology, deploy technology, then I think you are delayed and you can be just adopter or user like we have been in the case of 4G and to some extent even the 5G. So if you want to be a leader, then you think in advance at least 10 years ahead of the technology itself. And that's why presently government is working on 6G. So we have made the clear what is the roadmap for spectrum. We are contributing at ITU. So proposals from Bharat 6G Alliance, they are discussed within the working group and they are submitted to ITU in relevant study groups or working parties. Same is the case we started doing in case of spectrum as well. What is more important is that how can we influence the policies of the government that most of the components of 6G is software driven. So let it be driven by India. So the time has come when I think we have to realize that we should get our share in the technology development as well. So how can we have more and more IPRs? So Honorable Prime Minister has given us a target that how can you produce 10K IPRs and maximum SEPs in the 6G technology. In another direction that 1/6 of contribution has at 3GPP or different forums has to be from India. So lot of work is required, groundwork is required for making this reality. And Department of Telecommunications along with other institutions is working for realizing those visions. Because the Bharat 6G vision document was released by Honorable Prime Minister, and that's a Government of India vision, in which Bharat 6G Alliance is playing its role for its implementation, and it's a not-for-profit society like COMET here. So, for realizing 10,000 IPRs, we need more than 1,000 PhDs on a specific subject of related to 6G. So even when I study, then I see those 15, and I mean there can be more than 100. So I think government is deciding some more than 100 topics on which they are bringing out more than 1,000 PhD, and let them produce IPs and even contribute in 3GPP at ITU at different forums. So that is the one of the strategies. How can we convert these 100 use case labs, uh, 5G use case labs, scale it to 6G, and set up more and more regional test labs? Liberalize funding for use case development that can be presently for the 5G, which will be naturally scaled up for the 6G. Because even in the 5G, there is no killer applications. And can India take that lead that they develop the technology for the world from India? So that's why a liberal funding will be required to academia to make it up to TRL3. Different components of 6G are related technology, and from TRL3 onwards, it will be the naturally the bigger companies who will take it to up to proof of concept or commercialization. So there will be role of system integrator as well. And startups can play a role for use case and applications. So perhaps people feel that uh, in 6G it will be lot of distribution will be there. So there will be so many local applications and revenue centers depending upon the geography. So the same network will be utilized maybe in different manner. So how can India play a role in 6G technology, and how our students, postdoc can form their own companies and become a entrepreneur? So that is my thought process, and we are working with the government to facilitate liberal funding, maybe 100% funding or up to 99% funding as a grants to startups, and definitely some funding 50% or something even to the bigger companies, because that has been the case in case of NOFO of USA, or rings project of USA, or 6GIA, or Horizon of Europe, or other countries as well. And Bharat 6G Alliance has already MOU with NextG Alliance of ATIS USA, 6GIA of Europe, 6G Forum of South Korea, Brazil, NGMN Alliance, that is a operators alliance, uh, uh, offices in Germany, and 5G ACIA, they are working on Industry 5.0, and UK India Future Network Initiatives, UK TIN as well. So even we have to work together on TN and NTN integration as well. So I think Starlink news is there, but definitely we have to see that what can we can do from India. So I think we have to work in realizing that those applications are even system development can be influenced by our startups or companies in India. So I think this is my thought process, essential thought process. Subsequently, I can discuss more and more on the subject. And I would like to thank you, sir, for giving this opportunity and bringing me here, and to my colleague from Department of Telecommunication and others. Thank you all.
Thank you, Rajesh Patakji, for your sharing the Bharat6G Alliance vision and the vision of Government of India towards telecom, wireless, and in this space. Thanks a lot, and thanks for coming. I now invite Mr. G.K. Sutar, Department of Telematics. So he's the Deputy Director General of Technology of DOT Government of India. Has been telecommunication professional for 3 decades. Very supportive of academic research and very supportive of all this collaboration work which we are trying to do. So thank you. Please come in and share your vision. 10 minutes. Thank you.
Yeah, that should be okay. Yeah. Respected Dr. Devabrata Das, of course, he will be joining us shortly. He's not there. Sri Sridhar, CTO of COMET, Mr. Pathak from Bharat6G Alliance, Mr. Prakash from CDOT, distinguished professors from IIIT Bhillai and other IITs, uh, members from industry and startups. Very good morning to all of you. Namaste, namaskara. It gives me immense pleasure and pride to participate in this highly contemporary tech event amidst brightest minds from academia, industry, and startups. My sincere admiration to and congratulations to IIIT and COMET, Bharat6G Alliance, and TSDSI for organizing this important tech event. This workshop is being conducted under the shadow of successful launch of 5G services in our country. Let me say briefly few words about 5G services. It was, the journey began in year 2022 in July when 5G spectrums were auctioned in our country, and after that, Honorable PM inaugurated first 5G service during IMC 2022 in October 2022. After that, industry and Department of Telecom have come a long way. As of now, very close to 5 lakh breast transceiver station called BTS are enabled in 5G. And of course, we are enjoying the high-speed internet services from 5G services. And 5G rollout in our country is one of the fastest in the world. And almost all major tier 2 and tier 3 cities are covered with 5G service. And of course, we are enjoying high-speed access. If you might have come across the news item, particularly recently in Mahakumbh, where there was a large congregation of people on daily basis, average speed from 5G was coming roughly around 200 Mbps compared to average speed of 15 to 20 Mbps in 4G. So that speaks volumes, the capacity and capability of 5G technology. Basically, three promises were made from 5G. One is enhanced mobile broadband services, ultra reliable low latency communication, and massive man-machine type communications. Because 5G, deploys higher frequency, particularly in millimeter wave, particularly this ultra reliable low latency communication is a possibility in 5G. But these millimeter waves have there also propagation challenges associated with high frequency bands because they are prone to more signal attenuations, blockage and interference, which are common in, particularly in congested area like Bangalore city. This reconfigurable intelligent surface, which is the theme of this today's workshop, holds the promise to optimize network in a dense area and to boost the performance and efficiency of particularly 5G network. RIS essentially, of course, it might be a repetition because almost everybody knows what is RIS. Still then, for the sake of repetition, let me say that it's a smart surface that can reflect, refract, or scatter radio signals and can manipulate phase, amplitude, and direction of signals in a controlled manner so as to guide signal to optimally and reliably travel to desired location with better strength and minimum delay. RIS thus can focus radio signal more efficiently towards the users. And these features of RIS can really help us in mitigating the propagation challenges being encountered in 5G, and of course it will be more serious in 6G because it offers benefits of fast improved coverage. RIS can be placed in a proper location where there is no coverage or there are some blind spots or dark zones, particularly in congested landscapes or high traffic environments, say Bangalore city. It can supplement the 5G features of beamforming so that signal quality is enhanced up to the user level. Improved QoS, because directing signal in an optimized manner, RIS can help mitigate interference, and improve the signal quality. For example, we have been interacting with many users. Recently, we had a meeting with some state government agencies. They are from state disaster mitigating agencies. They were telling their office is, if you are familiar with the Bangalore city, if you go to, towards that central hub of the city, like Kandya Bhavan or Kaveri Bhavan, their offices, though telcos have almost covered Bangalore city, but there are some pockets where difficult to cover. These are congested areas inside, surrounded by salt straw structure. So their offices, they are getting, sir, we are not getting the coverage. Then it reminded me that probably RIS will be of a great help in that scenario, because normally what telcos will do, they have to look for, they'll try to cover the area from the adjacent BTS. If it is not possible, then only possibility is you have to look for an alternate site. That, of course, in a city like Bangalore, it's a quite a tedious job. You have to look for a tenant who is ready to give, his house or rooftop for installing the tower. After that, municipal authorities, you have to take permission for right of way, and it involves cost also, because you have to install a tower, BTS, genset, everything. Okay, and this, think of now RIS. If I can install RIS in a proximity location so that my signals are guided to the desired location, my job is done. So this RIS coming with these features, probably it will be of great help, particularly for low latency applications where you require a significant SNR level, because then only we can reliability can be achieved, low latency also can be achieved. Though these are applicable for time sensitive applications like autonomous vehicles, which is practically a long way to go. At least it will be applicable for AR, VR, and XR applications where immersive online is the talk of the day. So that latency feature also this RAS will be able to solve. Then coming to dynamic network optimization, Professor Das is talk up in the traffic today, so it was reminding me, if you go to Bangalore, some terrible junction points like, one is Silk Board, probably our sir is stuck up there. Other is, Jesse Road up to Town Hall, that's also massive place, you have to minimum 30-40 minutes, you have to spend time in that junction. So this junction tells me, can I do something dynamically so that at a particular point of time I can pump my signals and I can ensure better SNR, because that time only that will be large congregation of users. So this dynamic network operation, particular timing, I can say morning 8 o'clock to 10 o'clock or 6 p.m. to 8 p.m. I can turn on my RIS to improve the SNR level in a particular congested area. Then coming to spectral efficiency, because RIS is able to guide my signal to reach in optimal way without much dilution in strength and time. So probably without investing on additional spectrum, I can achieve better bandwidth. So that will definitely help me achieving the more spectral efficiency. Energy efficiency, of course, is there because it is all passive components, so it doesn't consume much power like active components like BTS. So it will be of great help to telcos if they can supplement RIS in that network, so that they don't have to install new BTS, so that not incur much more money. Then of course these are cost effective naturally, because instead of deploying an active BTS, I can, if you can supplement RIS, and tomorrow maybe city that will be dotting of electronic dashboards. Instead of that, probably the time will come when it will be dotted by RIS structures. So I'll not take much time, sir. So to conclude, I can say RIS is a very promising technology that can significantly improve performance, energy efficiency, and cost effective of 5G networks. I sincerely commend the efforts of TSDSI, IIITB, COMET, Bharat6G Alliance for organizing this workshop, which will go a long way in undertaking pioneering research on RIS and will certainly help all stakeholders, government, telecom service providers, and users, and industry also. I would like to thank TSDSI, IIITB, and sir, giving me this opportunity to share some thoughts. Thank you very much. Thank you all.
Thank you, Siddharji, uh, for the insights on the 5G journey in our country and about the RIS you talked about. And glad that you could come, and thank you for coming. I now invite Mr. Prakash to share in-depth presentation on RIS and the ongoing work with TSDSI. So, like I said, Mr. Prakash is a scientist G from Center Department of Telematics. He has been working in the space of 4G, 5G, and 6G, and a man of many hats. And today is representing TSDSI. Please, thanks.
Thank you, Dr. Sridhar. Uh, Thanks to IIITB, Professor Das, Mr. Sutar, and Mr. Patak, and distinguished guests here and members who have joined online. Thanks to the conference organizers for giving us a slot in this session. So today I work for CDOT, but today I'm here as a study group networks chair. I'm more talking about TSDSI and the RIS related activity. So I thought I'll use this opportunity since there's a workshop with a lot of experts coming. So I'll not spend too much time on RIS, but rather talk about what is happening in TSDSI or in and around 5G, 6G, and where does RIS sort of try to place it in perspective so that going forward in the day, as the day progresses, I think there are a lot of experts. I went through the speaker list, so I sort of let the others talk about the details of RIS. I will rather talk about the standardization and related perspective. So coming to TSDSI, if we have a okay, just get the slides going. Okay. So TSDSI is a standards development organization, and usually we talk of technology. So question is, what is technology and what is a standards development organization? How do they all correlate? And what is a patent? What is a IT service? What is an operator? So some of these questions when we discuss, so a lot of you are already comfortable, some of you are new to these terms, and maybe I'll use this opportunity to give a small, 30-second brief. See, we always talk of technology, but we never consume technology by itself. You don't like buy a patent, you don't buy a technology. So for example, if you're consuming, you want to use TV, you don't buy TV technology, you buy TV from a system, you buy it from one of the sellers. Similarly, with telecom or any of the technology aspects, you buy systems. And when systems are made, a lot of technologies go into it. And in a large, complex ecosystem like a telecom, where 4G, 5G, 6G, these are generations, when they all have to interwork, you need to arrive at a common platform or interworking techniques or methods agreed, which is where a standards development organization comes in. And India, one of the cost of development of standards is technology is also that you need to push your patents and your technology into the standards. And always it was perceived that if you have to make standards, you have to go abroad and participate in ITU or 3GPP and so on. So that is where the government over the years had been trying to how to make the cost of the technology agreements between various stakeholders, and that's how TSDSI was formed. It was being attempted, and I think Mr. Patak is one of the brainchild, and also probably the initial what you say, got it kickstarted, brought in the framework around which the TSDSI is started. So it's now been there for 10 plus years. It's pretty established. We are now known around the various circles. The work is considered. So for all of you, TSDSI is a forum where you can go meet academics, you can meet OEMs, you can meet operators, you can meet regulators. So all of them come together, discuss, debate, and try to bring working, out artifacts which is useful for the industry. Okay, so I request all of you to take active interest and participate. But just a small brief. So TSDSI is a SDO from India, and we members of partners in 3GPP and 1M2M. So it's like if there's an HC for Europe, ATIS for US, TSDSI is for India. So sometimes and we are trying to striving right now. We also help in 3GPP standards specifications being transposed and used in India, but there's also trying to get more traction on the ground and see if more and more aspects of technology can be standardized and as TSDSI base and can be used in India. We also work closely with DOT and the other government agencies who look to TSDSI as one is a panel of experts, but also as a forum for bouncing off their ideas and discussing, getting inputs on topics before some sort of policy making. We don't directly do the policy, but there is a policy of panel of experts who discuss and put together. Okay. So on any topic, whether it's RIS, whether it is 5G, 6G, the various individual topics. Okay. And we also have special arrangements with ATSC and IEEE where we are transposing their standards and adoption, okay, into the. So there are various forums using which, because a lot of times when people say 6G, today's topic is RIS. RIS is one of the topics of 6G. So when various topics of 6Gs are getting people work on the topics, you need to see when does standardization come in. So I try to give standardization as is a second or a triple order derivative. Standardization doesn't come, it's not the first thing you make. You build a working technology, you study it, you try to interwork with other entities, and then there's a requirement for standard. So standardization sometimes, last time there's a workshop here, I was trying to give an analogy. Standardization is, standards are like the pujari in the village. You need the other, you need the farmers, you need the, what do you say, the cooks, the shepherds, and all the other people, the blacksmiths. And then you can have the pujari who will help each other all work together in a manner. Okay, so that's like you can't have only standards. Okay? You need the other ecosystem in the place on a pyramid. The pyramid, it sits on a pyramid. Okay, so that's why coming here, you see TSDSI helps out in a lot of these aspects. We have a roadmap. We do pre-standards work with various people. We do studies on standards. Also work with other global bodies and also bring in these aspects. So we're a membership-based organization. There are a lot of work, not just on wireless. It's the complete end-to-end telecom aspects. There are also aspects of application. So the work business gets conducted in two study groups. Okay, and in terms of members, it's a membership-driven organization. The interest of the activity. So these are all the partnerships. There's a wide variety of partnerships from being part of TSDSI. And all these entities work on leading topics across the world. It's 6G by and large. TSDSI, we try to bring in the world, what works, what's happening in the world to India. We also try to take what's happening in India to the world. So we bring in an Indian flavor to the importance of the Indian needs and necessities into standard. Otherwise, the set of people sitting and discussing in Europe or America might not be very concerned about the troubles and situations and the needs of the Indian networks. Okay. So that is where the TSDSI provides a forum to take it forward. Now this is the structure, but I'm part of the study group. It's an elected position. I am the chair right now, this second term. In a few days there'll be elections, so some of you are will, who are keen to do come and participate and pick it up. The other study group is the study group of services and solutions. So there is networks and applications, trying to break it. It's a simple structure. All aspects of networks goes into SGN, and trying to make the networks usable to the customers is the part of services. There are also security aspects that gets taken care in the SGSS. Okay. And the journey so far, we've been, we had a very stormy start with a lot of heated debate, a lot of people trying to find out why we need to do. But over a period of time, we have found the footings, and we've been working on standards on across all of them, whether it's transport, whether it is wireless, on applications, on clouds, and so on. And we've also helped in bringing some of the global standardization activities to India in conjunction and support of DOT and Bharat6G Alliance. So as a part of that, we also put in white papers and reports and specifications which are relevant to the industry. So the critical ones that one of the notable things that happened was that India proposed 5G-I, that is an alternative to 3GPP based radio, because we felt at that time that the needs of Indian network were not being taken care, the rural communications, because the definition of rural was felt that a 500-kilometer per hour train going past the villages is the rural requirement, okay, which didn't seem like something our India requires. So we were more focused on coverage, larger cells, lesser number of towers, energy efficiency, and so on. So that is what we pushed, lobbied, fought across, the meetings went across the world and got it as a 5G-I standard, which later got merged back into 3GPP. Because of all the work done here, we managed to get it into the situation. So, like I said, these are the key work that is currently happening. Okay, there's 6G, there's 5G, work on 5G enhancements, there's spectrum studies that happen. Okay, people come in and do characterization studies and so on. We are also working on open disaggregated systems, visible light communications, and quantum communication. In terms of study group and services, it's security, application layer, okay, and framework, edge communications, cloud interoperability, and AI/ML models for delivery of services and so on. So I'll not tell all of them; they're pretty elaborate, but we're now working on a roadmap 3.0. There's in fact a meeting happening this today and tomorrow towards standardize, the roadmap. The roadmap group tries to mentor people who are trying to build new technologies and help them go and face the rigor of a standardization. Because when you go into standardization, it's a lot of members who have their business interest, and it's a very tough forum. And to stand the rigor of it, there is this roadmap committee which sort of mentors the people coming in and help them face the situation in the hall. Okay. So these are the topics that is getting discussed about 6G, 5G enhancements and 6G in terms of wireless networks. But you can, wireless is the key, larger portion, but anything involving the core and transport, even that gets taken care. In turn, quantum communications, VLC, I've already talked about. So we always keep this rural broadband as one of the key topics of interest, whichever is come, whoever brings in. Then ITS has some traction, security has some traction, and NTN is one more topic which people have started showing, HAPS and non-terrestrial networks. So these are some of the accomplishments, the total number of technical reports prepared. the number of standards that have been there. But going by, if you see the list of what are the standards developed, I've just highlighted one of them. We've got a standard for RIS assisted communication. The version 1.0 has been released, and there's an upgrade to that is happening now. It is being taken to the next level by various members. There are what we are also seeing. I'll come to the next aspect. And these are the other standards and whatever is got transposed. But if you see here, other than 5G ICPRI, we have also started doing on end-to-end architectures and in terms of even services aspects to started coming. So in terms of RIS, there's again a larger list of all the this one published, the technical reports, and the TSDSI outputs are in terms of either technical reports or technical specification. The technical specification goes to TEC, and there a consultative committee decides to adopt or not, and then it gets adopted as a national standard. So anything that you want it to be used countrywide, TSDSI is a good approach. And this is the aspect of global forum engagement. So we have active members actively participating in ITU, 3GPP, 1M2M. C dot internally is also very active on these activities. So I'll not talk about the detail aspect because it's just a 10-minute overview. I'm more here to just brief. So one of the stuff I wanted to highlight was that RIS is one of the topics of 6G. So the activities that is happening in TSDSI covers a broad spectrum of the whole communication aspect. And when you have to get RIS in, the you will also have to see the interplay between RIS and the relative weightage of RIS with respect to the other topics, how much resources of it will be consumed. So this is a diagram which is widely discussed in 6G. Over the day, you will see a lot. So what was a triangle of 5G is now got enhanced into an hexagon of 6G with AI getting added and integrated sensing and communication, ubiquitous community, and so on. But coming to one my personal observation, not as a TSJSI, but as over the seeing all the development industry as technologies, we have promised a lot in 5G to the society and community. There's a gap between what was promoted and talked about and what people pursue as benefits they received. So that gap, I think the operators and people, there's been a pushback saying, in fact, some of the operators, when the technologies went to them and saying we have started working on 6G, they said, look, I don't want any more G. Please come back with how can I earn more money, or how can I provide something tangible to users. So there's been a pushback now. So of course there will be a 6G. It will be called 6G whether somebody wants it or not. But I think the challenge that is coming in is that telecom is getting commoditized, and the ARPU is, there's only so much money. I was talking to somebody today, and there's only so much money you can extract from a family or a person for basic communication. Now, if we want as a community to do better, okay, so we need to bring in aspects and value to the end user. So that is where, when all of as we discuss in the workshop today, one of the aspects that has to be kept in mind is, the topic that is happening. People talk about, there's a workshop on 6G. So what is the asks from the operator? What is the asks from the this one? They're asking for ease of use, ease of network deployment, energy efficiency, better spectrum utilization, and so on. So the question is RIS an answer? Okay. Then another aspect I want to talk about is RIS standalone. RIS topic the solution for the problems of the operator and users. One thing that I'm quite personally enthused about RIS is that it does bring in a certain amount of energy efficiency improvement, because there is a scope for doing, if you see what does a base station do, it's basically if you just look at, strip away all the aspects, telecom is essentially a business of converting electricity to money. And better conversion you do of the electricity to money, the better is the revenue or the profits for the operator. So if you keep putting more and more base station, as we see from 3G, 2G to 5G transition, what has essentially happened is that there has been a lot of densification is what has provided all the benefits. Okay. There's hardly spectral efficiency improvement and other aspect. It's just increasing the bandwidth and increasing the densification, and there's very little else. Okay. Maybe IP is the other aspect, IP network. So the thing about RIS is that RIS brings in an aspect of passive element into the network. And rather than radiating energy all over, can you beamform and just spread the energy? Can you narrow focus the energy and point to the energy to the end user? And sort of if it reduces the amount of energy consumption, reduce the interference, your systems might be simple. But then I don't want to, the discussion that happened in the day, I don't want to, but just set the tone of, optical networks. One of the progress that happened was when PON came in. It did simplify because it is not that a lot of places you don't have the energy or the money, but the ability to maintain an active retransmitter or a amplifier or a relay element, okay, is very costly in terms of maintenance aspects. So that is something, if we are able to reduce the energy consumption, improve the efficiency, make spectrum better utilized. Okay, so RIS is probably uh, in the works. So in a workshop that happened in 2023 of IMT, a lot of topics got discussed, but I have highlighted a few of these where RISs make probably sense, probably can get coverage extension, make it more sustainable. Maybe can you improve energy efficiency, maybe merge it with sensing and communication and so. Okay. So this is the standard that we have already got published in TSDSI, and I'll not talk about it. The whole RIS, I think there's a tutorial plus stuff, so let me not this. But in terms of the 1.0 is getting upgraded to 2.0 under the work item. This is the current work item, so people who want to dig it out and see. So there's an active engagement and people debating on all aspects. That is, should it be, there's IMT, there's the other technologies, non-IMT and by IEEE and so on. So there's debate and discussion going on, and how should it be structured? What is generic RIS? What is should it be generic? It should be specific. Should it be passive, active? So intense debate, quite enlightening. I request all of you to come and actively participate. So you might agree, might not disagree with the uh, member who's talking, but at least you get more insight into a lot of those aspects. And over and above the basic work item, there are a lot of other new study items that have come in. So these are members who are doing active work. They are funded research. They have their own funding, and they are all coming and getting active work done on RIS. So I mean, there are other forums, but TSDSI as an Indian SDO engaged with the this one. There's an active body of experts who are debating this. So I request all of you to participate and benefit from the this one. I, as a chair, facilitate it, but if in a few days my term comes to and there'll be somebody else. But TSDSI is now providing quite a bit of good value to the industry. So that is why I request all of you to join in. Thank you.
Thank you, Prakash, for the nice talk on TSDSI and RIS and other standards. So I'm sure the audience, both of industry and academia, will actively participate and support this cause. Thanks a lot. I will quickly go through. I know we're getting a little delayed. I'll quickly go through what is before passing to Professor Das. I'll quickly go through IIIT COMET Foundation. Maybe I'll take 5 minutes. So, as uh, Dr. Rajesh Patakji has already mentioned about the TIH, there were 25 TIHs which were formed across the country. My slide. So IIIT COMET is a technology innovation hub, which is started somewhere in the same June, 2020, 2021. It was one of the later hubs. So it's part of the national mission of interdisciplinary cyber-physical systems. So as part of the NMICPS mission, uh, different hubs, as Professor Patakji mentioned, Dr. Patakji mentioned. So these hubs are each focusing on different verticals, largely in some connectivity, the horizontals, the verticals. IIIT Bangalore COMET Foundation is focused on advanced communication systems. So it's a Section 8 company, and like I said, it's a part of advanced communication systems. So we are focused on technology development, entrepreneur development, and skill development. The basic intent and the idea of the mission was that a lot of research has been happening across the different institutes, IITs, IIITs across the country. But how can this research can meaningfully get into some commercial aspects, either products as part of the Atmanirbhar mission? How does it come in there? So it's better to form a Section 8 company under the host institute, and that basically works on the translational research or technology development on some of the areas. At the same time, a lot of support is required. Unlike the incubation hubs, which are focused on other aspects of incubation, there's a lot of technology mentoring, and how the business use case mentoring with technology is very, very important, and how you can actually nurture creation of industry in the space of what research is happening. And that's why entrepreneurial development came into picture. And skill development, because in this area, in general, there's a shortage of people, experts who can actually take off from there, from what is happening. So skill development. So these are the three main areas, in general, applicable for all the TIHs and applicable for IIIT COMET as well, but focused on communication systems. In the technology development area, IIIT COMET choose the problem statements from Department of Telematics, DOT, where we're looking for need for indigenous development in the space of 5G and advanced 6G, as well as reducing import dependency. So two of the areas which we focused on was one of the 5G advanced massive MIMO base station, components of that in the ORAN space, and smart radio environments. This workshop today is focusing on the smart radio environments, which is reconfigurable intelligent surfaces. And we're looking at to see how we can nurture and how we can collaborate across the various different work which is going on in this space, and ensure that we can meaningfully contribute towards the nation mission, meaningfully contribute to the TSDSI mission, as well as ensure that certain products or certain space gets into this area. Uh, some of the things on the background on this, on the ORAN base station, some development has been going on. In the next 8 months or so, you will see some of these models. They are actually on development at this point of time, and we will see uh, ready to launch in some space. It's happening right now. The ODU accelerator card is pretty much there. I mean, some of you post this session, we can actually show you in COMET lab the work which is going on there. This is, I'll quickly skip through this because the entire workshop today is based on reconfigurable intelligent surfaces. But some of the work which has happened and some of the space, and of course, in the demo, Professor Arzad and his team and Professor Prem and his team will be actually showcasing, and across the industry, whatever work has been happening will be showcased today. I just want to briefly tell you about the entrepreneurship development. We have actually supported about 7 to 8 startups in the infrastructure space. It's very difficult to get in startups, but we have actually nurtured, or actually say groomed, a faculty-led startup, which is here led by Professor Prem Singh and Ekant Sharma. We also have supported several startups in this space, and some of them have actually won the accolades, which is listed there. And we have collaborated with IIT Hyderabad in the Future Wireless Communication Program. About 300 plus participants benefited out of this. And we have recently launched in Bangalore the same program, which is kick-started and right now running. There are about 20 students who are actually getting benefit out of this at this point of time. Very soon, we are looking at seeing how it can grow. It's a 3-module course, which runs about eight months, 2 plus 2 plus 4. So we're looking at enhancing and bringing in more people. This is basically hands-on, a mix of classroom, come hands-on project-based development onto embedded communication space. Some other partnerships which COMET has, and we are looking at seeing that as we grow and as part of this current workshop, look at meaningfully collaborate with all of you. Thank you. And I welcome all of you whenever you have time to come to the Comet Lab, which is in second floor here, and we can some of us and we can all tell you what is else been happening here. Thanks a lot, uh, and I welcome again all of you for this workshop. And I invite Professor Das, our director and project director, director of IIIT Bangalore, as well as project director of IIT COMET Foundation, to come and say a few words. Thank you, Professor Das.
Good morning, all, and a warm welcome to RIS workshop in IIIT Bangalore already. And thanks, Mr. Sridhar, for the CEO of IIIT COMET Foundation for anchoring and introducing all of us. So before I go in, I want to have a special thanks to my esteemed guest, Mr. Pathak. As Pathak is here, thank you, and Mr. Shutar. Both of them are excellent supporter of telecom across the country, but also the IIIT Bangalore and to this workshop. Thank you, both of you, for coming and giving a talk. And also Mr. Prakash R from the CDOT, who has been the TSDSI's one of general chairs and also heading it. I want to say that we are all proud of TSDSI because it has become a uh, point of melting from academia, industry, and the government to taking the country's things to the international bodies. 2014 started, 2014-15, I attended the first one, and also till today the member 10 years is gone. The biggest pride is that 5GI later on, this RIS itself, which is now one India is leading, thanks to TSDSI, Dr. Arjad is sitting at here from his team, and IIITB also. The maximum contributions to the standard body in RIS is coming from India. So thank you all for that supports, and also Mr. Vishnu. Thanks from Tejas for Jishnu coming from Tejas and helping, and all Dr. Saptashi I can see from our RIS and other eminent people from the industry and also from government and academia. So I have one two most important thing to say, because I can see some of those young minds are here. They may be wondering. People has been telling that communication has been getting commoditized, and also the what is happening in the world, and all the situations in the dynamics of the market is changing. Of course, everything is changing and happening in a good way. AIML is coming. So I have only 2 points. The first number one point is that communication is one of the most important pillar in this one and zeros. What is this one and zeros? As you know, when we started studying BTech, or before BTech also the plus two science. So at that time we are introduced to this digital world called this one and zeros. So if you look at these one and zeros on this earth, I always say to my students, these one and zeros is only in 3 states. Whole world, if you look at, only 3 states these one and zeros are. We call these are all 3 C's. First C is the conservation of the information, the one and zeros. That means your storage, high speed memories, all cache, these, that, and all primary memory, second. So first is called and memory management, all those things, research, deep research is going on as the data is increasing. So the first is the conservations of the information, the first C. Second C is your the communication. That means if any sensors anywhere the one and zeros are generated, that has been communicated from the sensors or IoTs or anywhere I am talking, or I am also generating any file, or you are generating file, it is being communicated to a data center, or in your computer it is being stored. So that is called communication. That is the second C. And the third C is the computation. After you generated a data and you have been communicated that data to be stored, then after that, when you want to run any algorithm, AI, ML, and all kind of things for networking communications or for your any of the e-governance or governance or running the country, anything you need to compute the data, the CPUs and GPUs are there. So that is called the computation. So data will be inside the CPUs or GPUs. So if you look at your information is only on these three states. So one is conservation of information, communications, and computation. So this communication is one of the most important pillar, and it will be there forever. And only thing is that it will evolve towards the better. So you don't have to worry as the younger generations that you are in a communication areas. That means this area will grow, and always there will be some demands as we grow in respect to the quality and performance is concerned. Now, the second point of me, only 2 points I say. The second point of me is that this TTT COMET Foundation has been supporting RIS. I am not entering into technology part of RIS. There are tons of papers are coming out from different institutions. But my vision and the TTT COMET Foundation vision is that our vision together is that if you look at India, to be honest, very honestly, I'm saying this, is that we are as the largest populated country in the world now. We have crossed China, no doubt. But if you look at the niche manpower in the communication, understanding the fundamentals of the communication, like protocol stacks and the physical layer communications and the signal processing, these three areas, current and ultimately putting into the VLSI circuits, like design VLSIs. So these niche areas, manpower, we are not yet critical. We are very suboptimal. So how to solve the problems of the country and the many parts of the world? We need you more and more manpower in this, and academia should take this responsibility first, because academia is the root of training the manpower to the reach to the certain level, and after that industry takes over. Our government supports to both of us, academia and industry, department of telecom, department of science and technology, MATE, and all help us. But take such a great hands, they're helping hands. So my point is that in RIS, IIIT COMET Foundation, we have 10 institutes working with us closely. IIIT Bangalore is holding it, but IIT Vilai, IIT Delhi, IIT Roorkee, IIT Indore, IIIT Naya Raipur, there are IIIT, you can name it. So, and also the companies like C. Tejas, and many companies are working with us very closely. So what I wanted to say is that why I brought this topic of critical mass of the manpower is that we as a country has such a low suboptimal critical mass in the niche area, understanding the very depth of the things. So we should work together. We should complement each other. Like academia should generate manpower and train them and teach them up to POCs and certain level. Industry should take over, and we should work all the industry together. We should work in India together. Government should support and work us together, which is happening now. Because if we want to do a worldwide impact, we have to work together. If you look at Finland, such a small country, they have a huge critical mass. If you look, I'm not taking our north side neighbor. He's a huge. We can't imagine the amount of manpower working there. So and Korea and Europe and United States, all Western countries. So if we want to make an impact, these platforms, IIIT Comet Foundation or any other platform, we should work together. We should complement each other and see that our research output, our product output should have an impact in the world. And I have no doubt that RIS will have an impact, because as we go to the higher frequencies, which we'll have a lot of talk today, and there are so many great researchers, best brains of the country and the world are here. Some of them are in this room. They will be talking, and some of the papers will be discussed. Demos will be there, and IIIT is setting up a test bed, which just now Mr. Sridhar showed you. Please use it. I am telling you, we should work with together. Any industry, any academia, and government wants to use the test bed for RIS. Please use that infrastructure. Make your results available to yourself or to your counterparts. So all are welcome, and I am ready to host some of the TSDSI's workshops in future. The first technical workshop of the TSDSI was hosted around 9 years back when TSDS started at 10 years back. After around 7-8 months down the line, we start. It was in IIIT Bangalore. So IIIT Bangalore silently contributes, doesn't speaks out so much because we are a silent worker. And thank you very much, all of you, for coming and enjoy. So one last word I will say: let us work as a team, complement each other, make the country go ahead. Thank you.
There's a couple of more things to be done for the inauguration. Would like to light the lamp. So usually we light the lamp before, but we decided to do the other way around this time. So please, all the Patakji, Sutarji, Prakashji, Prasadas, please. Prasadas, if you could give the memento to. This is for Mr. J.K. Sutar. This is for Rajesh Patakji. Thank you, Rajesh Patakji. This is for Mr. Prakash. Thank you, Prakash. So just Prasadas, I want to give to memento to Professor Arjad also. So thank you. I know this session got a little delayed, but it was overall pretty good that all of us were here and nice session. Thanks a lot. There will be a break. We'll cut the break to 10 minutes. But before the break, we can all come back here for the tea. We want to inaugurate the anechoic chamber where the test bed actually for the RIS is being there. So I welcome all the dignitaries to come there. We'll inaugurate and then come back for tea. Okay. Thank you. Thanks.
ठीक है ओके हो रही है भाई नहीं नहीं only for live camera This is the
Sir, give one. One more. I'm not cutting you. Sir, we are not coming. We are not coming. Sir, here. Shall I?
क्या दिख रहा है भाई? अब दिख रहा है? अरे दिख रहा है, नॉमिनेशन हो रहा है, वो दिख रहा है। Next item. Yes, ma'am. Yes, ma'am. Now, अब बता।
Check.
This is Rakesh Patel.
So, ladies and gentlemen, we will now transition to COMET RIS updates, demos, and launching of testbed, which will be shown by the IIITB COMET Foundation team. I would like to welcome Professor Sumava to accommodate this session.
Should we start? So, very good morning to all of you. I am Shomabu Mukherjee, Associate Professor in IIT Jodhpur Electrical Department. And so, this session is basically a brief overview of what the COMET Foundation is doing for the RIS activity. So the session will go like this. First, I will present some of the works which we have done, and then followed by some other team members from Dr. Priyanka from IIIT Bangalore itself, and Dr. Prem also from IIIT Bangalore, who will be presenting their part of the RIS, and we'll show you jointly what we have contributed towards the development of the technology as well as towards the standards. And that will be followed by the demo, which will be shown online. Anyway, after that you can also visit the demo in the downstairs in the anechoic chamber as well after this session. So with that, let me start. So as you all might have heard that in the first session that the project name was Smart Radio Environment Implementation and Development for Targeted Use Case. So basically, before going into the actual topic, let me briefly introduce my institute. So this is a aerial view of IIT Jodhpur. This is the famous administrative building and the clock tower, which is typically visible from IIT Jodhpur. I come from here in Rajasthan, Jodhpur, and Jodhpur is famous for this Mehrangarh Fort and Blue City, and because the view from the fort is this blue, that's why it is called Blue City. And these are some of the glimpses of the institute. So our institute currently has 290 faculties and more than 4,500 students, more than 12 departments and some interdisciplinary research platforms. In our electrical department, we have 4 MTech programs and PhD program in all dedicated areas. These are the some of the glimpses of the campus. Just to introduce that, what is IIT Jodhpur. So let me come to the topic. So why we are talking about this reconfigurable intelligent surface or RIS? People also talk it in terms of IRS, intelligent reflecting surface. Both are to some extent referring to the same topic as well. So essentially what we are targeting is that can we increase the data capacity or throughput of the system. And if you talk about FR1, the lower frequency sub 6 gigahertz, the major problem arises from the blockage, that is the direct line of sight path. So of course we have different algorithms to talk about the non line of sight path, but what if we can improve that? So that was the major motivation for the discussion. Of course we had some of the options. For example, relays are there, or you can increase the number of base stations, obviously densification of the network, but then the cost increases multifold. So people are looking for different options if we can do that. And there this RIS comes into the picture, which can be energy efficient solution as well as can be cost effective solution. And therefore the development of technology, one side can be that what is the exploration of the technology, what is the potential of the technology, but also in the other side can be how commercially viable solutions we can put as a technology, and which can be India's perspective towards 6G as well. So that is the motivation for this current project. I think some of the things are known to many of the you who are already working in RIS, but still let me give a brief overview. So typically, if you think about electromagnetic signal, if you put a perfect electric conductor, you will follow Snell's law, which means that whatever is the incident angle, that will be the reflected angle. So that is well known theory. Now the things got start changing once we go for generalized Snell's law, where there is some additional thing which we are adding into the surface, which is called phase gradient. What it does is that I'll show you the equation in the next slide briefly, only one slide. I don't want to make you bored. So the idea is that if you can introduce intentionally some phase gradient into the surface, what you can do is that your reflected beam reflected angle is not equal to the incident angle. You can change it. What does it mean is that if you can dynamically change the phase gradient, you can steer your beam into different directions, even if your incident angle is not changing, which is a very good perspective or plus point from the communication network point of view, which means that you can send your electromagnetic signal or microwave signal, which is the current mobile technology which is working on. You can send it to the blockage area, and therefore can solve multiple problems. Of course this is very simplified form which I am talking about. There are many different things has to be developed, but this is the basic idea. And this is what you can see in the figure itself, that this is the base station and this is the blockage, and this is where we need to send the signal. And this RIS can work in that places by deflecting the beam. Even if the incident angle is not equal to the reflected angle, we can do that by using this phase gradient. So how this type of surfaces can be implemented? So I am giving you one of the perspective. This is one of the solutions. Definitely there are other solutions available. People are already discussing different technological implementation perspective. This is the most commonly used and most cost effective solutions people have found out. You take a printed circuit board substrate and make some patterns like this. like this. This is a copper based metal patches kind of pattern. Based on how you are designing the pattern, you can create a desired phase gradient and get the desired response. So basically, this is what you can think about the generalized Snell's law based equation, where your theta d, which is the deflected angle, and theta is the incident angle, they are related with the phase gradient d phi dx. So if you change your d phi dx, you can change theta d for a particular fixed theta I. There's some illustration of the same concept into two dimension, where we are also talking about phi I and phi d, and you can get this kind of equation, which will help you to ultimately get the desired phase which is required at a particular mnth unit cell. So by solving this equation, you can find out that what is your phase profile required in the surface. You design it accordingly and then get the response. So I'll not go into the much detail of the design part itself, rather than I'll show you some of the design examples. So how we are going to do it? One of the ways is that if you have decided that where you want to deflect the beam, you have the fixed phase profile. But that is not what is meant right now. Right now, people are talking about reconfigurable intelligent surface, which means that your phase profile is required to be tunable, reconfigurable. So if you want to do it continuous reconfiguration, then the hardware complexity increases. So the most obvious choice is that you quantize it. The number of quantization levels you can choose based on the complexity which you can afford. So the most commonly used quantization method is 1-bit quantization, which will use on and off, 1 or 0. And so the obvious choice will be, this is your unit cell, which is a metal patch kind of structure, which will be connected to surface mount device based SMD component, pin diode switch or vector diode switch, whichever you want to use. And either 1-bit or 2-bit, whichever you want to use less number of bits, less number of control circuit configuration, and achieve the desired response. Of course, it means that the amount of quantization levels you are making, that will depend, means that will decide that how accurately you can deflect the beam. More number of quantizations, you are more close to the continuous beam steering, continuous phase tuning configuration you are achieving. So that is of course a trade-off, and but there are different algorithms which you can apply there and find out a best optimum solution to achieve your desired direction. So I'll just show you one of the design examples which we are working on. So this is a brief structure of the top view and bottom view. So how it works, this is one of the approach, not the only approach. So here we are taking a metal, a copper based metal patch, which is conventional microstrip patch you can think of. Although I should not call it microstrip patch, it is you call it as an antenna, printed antenna, and that is connected through a via to the bottom layer, where there is a piece of transmission line. Now those who are from electromagnetic background will understand that if you have a transmission line and there is a impedance mismatch, there will be reflection. And in this case, the impedance mismatch is explicitly open circuit or short circuit. So what will happen is that you will have full reflection. So what essentially it will do is that it will capture the electromagnetic wave, send it to the transmission line, goes there, full reflection, comes back and re-radiate. Now, in this total process, there will be some phase difference, of course, and you can tune that phase difference to get your desired phase gradient response. And that's how you can achieve a complete surface based on your desired need. So this is just a design example I am showing, and you can see that we have made two cases where there is almost a 180-degree phase difference, and this can be used as a 1-bit configuration or quantization based surface for your desired RIS section. So based on that, you can definitely calculate the equation which I have shown earlier. You can get a desired phase profile. For example, here we are showing two cases. One is for azimuthal direction, one is for elevation direction quantization levels for a particular degree. I think it is for 40 degree, which we are showing right now. And the two colors are representing two different bits or two different quantization levels. One is either 0, one is 180, and accordingly you can create your surface according to that surface level and generate the beam. So these are some of the response which I have only included two responses, one for I think 40°, one for 50°. So both of the cases the incident wave is normal, which means that 0° incidence angle, and I am able to deflect the beam in the 40° and 50° around in that direction, which is the application of the generalized Snell's law. Ideally, if you follow the Snell's law, 0° incidence means 0° reflection. Here we are getting 40° and 50° reflection, and with a sufficient gain, so we can definitely achieve this blind zone coverage kind of scenario. So this is the board. This is of course without using switch. This is just an example surface which we tried, and this is the experimental setup which we tried, and this is the response which we can see. So what you can see is that if you are not using this RIS board, then you are getting reflected beam at 0°. The moment you are using this board, you are getting the reflected beam at 40° response. So which proves that this surface actually been able to implement the generalized Snell's law. Now I'll just add. We have not much time, so I'll add some more one more point only. We tried to make another idea from this particular study, that can we make it a cost effective way of even from this. So what we found is that for many of the cases, this number of combination of bits are very constant throughout the row or constant throughout the column. So what we tried is that, can we only make these two rows and create a system which can mechanically change these two. In that case, I can create a cost effective solution. So this we recently developed and tested. I'll show you the result in the next slide. And it also works very well, pretty well, for the implementation of the surface. Of course, it is not fully electronically tunable, but it can be a cost effective solution for the first version or first generation of the RIS. So we feel that that has a lot of potential for initial stages. This is the response. So these are pieces of each rows arranged in a surface kind of scenario, and this is the response. So earlier graph, there is one addition, that is this pink graph, which is for this piecewise surface, and you can see that they are also matching with the actual surface. So this actually works. You can actually create only one row. This is also maintenance wise is pretty good, because even if your one of the rows are bad, you just replace that, and that works. So that way, very cost effective solution can be a good candidate for the industry perspective. So with that, these are some of the structures which so far we have developed. We are also in the development phase. We are doing lots of new designs, and hopefully we'll come to the some more good designs as well in future. uh, the next few slides, I am just showing what we are doing as a teamwork, and this is I have borrowed from other team members as well. So this is the complete team. Sorry, this is the complete team, which includes all these institutes: IIT Delhi, IIT Indore, Naya Raipur, Dhanbad, BHU, Jodhpur, Bangalore, and IIT Bhilai as well. These are students from IIT Bhilai. There are also students from other faculties as well, which I could not include. Of course, we have good collaboration with Tejas Network, and of course, TSDSI members are also there. So what are we could able to do is that we could able to develop a first version of the standardization activity. So where we started is here, that how these control signals will be transferred between RIS and the network. So what we typically thought of that, there can be multiple RIS. So first you need to identify which RIS you are going to use for control signal. Then you need the capability query, that what are the capability of this particular RIS. There can be different solutions available in the network, and all RIS may not be using the same capability as well. So you have to know at first that what is capable for this RIS, and then accordingly you have to use your algorithm. So that is this capability query, and then you will come the configuration part, that okay, you have this capability, so configure your surface accordingly so that I can deflect my beam towards the desired direction. So with that note, this first version of the TSDSI standards based setup was done. This was done in IIT Bhilai, and there are some pluggable modules. So the idea is that even the today's workshop, the one of the idea is that whatever you all can design, we can plug it here and test, and therefore we can see that whether India's perspective wise all are in sync or not. So yeah, so we invite everyone to test your surface with this TSDSI based system. These are some of the standards which are we are, as a team we are contributing all together in TSDSI, and ultimately we could come up with this TSDSI standard for RIS, and hopefully this is in development stage. Of course there will be multiple versions as well, and we are hoping that we'll be able to make a strong case in future from India's perspective towards RIS activity. Some similar activities are going on globally as well. From Etsy side, and Rista is from China side, there are white papers available. You all can see those kind of activities as well. So we have to also make a strong case here, and I believe that this workshop can be a good platform for this case. So that's all from my side. This is I would like to acknowledge both COMET as well as IIT Jodhpur for this whatever research we could do, and we are continuing that. We hope to contribute more towards these directions, and I thank the funding agency for that. So thank you. So maybe one or two quick questions, or we can also complete all the talks and then we can have joint question and answer session, whichever is fine. Maybe one or two quick questions, maybe, or if there is any, and after that we'll shift to the next speaker. Yeah.
in the, from the board. Like there'll be a reflection,
Yes.
and then, but is there a kind of, there will be a, what do you call
It cannot be
gain?
zero. There will be some loss.
Yeah.
But it's very minimal.
It's
less
very,
than-
yeah, I mean, I heard it's minimal, but if there's a number that's, if you have something, you could share with us.
So essentially, what when we are testing, I have not tested the insertion loss as such. When we have simulated, it is less than 0.4 dB. So 0.4 dB, less than 0.4 dB. So it's very minimum. It can be even improved from that also. But essentially, when you are testing and surface, more than insertion loss, probably is what is more important is that how much additional power you can deflect. So that is what we are trying to measure as for now, rather than going into the detail of the surface. If we can deflect more power, that is even for now it is enough.
Good afternoon, sir. Point 4. Right now it is point 4, which is pretty good. But in some cases, when you work as a cavity, then it can go up to -1 dB also. That
Yes.
will.
Yes. That's true.
Hello?
Maybe we can move to the next.
Yes.
After all the this, talks are, we can have a joint question and answer. So I welcome Professor Priyanka Das to have the next talk. Thank you.
Good afternoon, everyone. I thank the COMET Foundations for organizing. I am assistant professor in IIIT Bangalore, and this work is jointly with uh, Amrita Mukherjee, the research associate here, and also Dr. Smriti Kumar, who is currently pursuing PhD under Professor Arjad in IIT Bhilai. So my area of research, particularly in this COMET RIS project, is basically the channel estimation part. So first, let us understand why channel estimation is important. So as you see that this is the transmitter and this is the receiver. So what we are talking about the RIS. So of course, if you transmit a signal, two replicas will receive at the receiver. One is the direct line of sight path, if at all it exists, and another is the reflected path via the RIS, and they are going to superimpose on each other. Now, depending on whether you want constructive interference or destructive interference, right? Always we want the constructive kind of interference. How it will happen? Obviously, you have to control the phases of the RIS elements properly. So if you can able to control the elements phases in proportional with whatever you see the sorry Yeah. So ultimately, we all know that it is very crucial to have the channel estimates in order to get better at the user end. So there are challenges involving in the how do you typically estimate the channel states. The first important challenge is of course like IRS consists of large number of reflecting elements. So we need to worry about how efficiently with low pilot signal overhead we can estimate the channel uh, at the base station end. So here what will happen is no you can exploit the reciprocity property of it. So for example, if I want to estimate the downlink channel, then if I exploit the channel reciprocity, the receiver can send the pilot, and base stations can estimate the channel out of it. Second is passive nature of the RIS is no, it is not allowing to estimate the channel separately here, and no, you cannot separately estimate this first channel and the second hop channel. So what we are targeting to estimate is the cascaded channel. So this um, and I don't spend much time. Professor Sumava also has explained on this. So typically the channel estimator module is here. I briefly explain the where we are in terms of the working principle of the channel estimation module. So I just want to give you a very overall no broad level of idea. So let's say this is my base stations, this is the user, and this is the CE module. CE module is responsible to estimate the channel and feedback to the user, and then finally the user has to report based on its current status. So if I want to focus the message flow diagram, so let's say you want to communication initiate request and you have given a response from the user end, then basically you have to say whether the time frequency resources for pilot from the base station to the user end, and you get an acknowledgement. Then actually you are starting sending the pilot signals, and then the users receiving the pilot, it is sending to the channel estimation module. Here we can apply our own algorithm, and I will say a very simplistic form of algorithm what we are trying to do right now, and you get the estimate back. Then once your channel estimation is done, you send your data packets. Then based on the sending data packets, you can compute the throughput. And of course, if you have a target set for the throughput, you can compare with the target. Based on that, we can take some decisions, okay, which I'm not going in detail. So this is overall the kind of messages we have to strictly follow, and we have to act accordingly. So basically, if you want to have a better quality of user experience, the importance of channel states is very crucial. So what we started in our team is to find the channels, and we apply the very simplistic form, which is the least square approach. So if we just see what is the least square approach, So you can see that, let's say, no, it's a simple line of sight model. So I have my receive signal, which is Y, and I am receiving the pilots over P such pilot transmissions. So it is, your channel is here and the pilots are here, plus some noise will be there. So what is the model? Finally, the equations I can write: y of p is h x of p plus n, and the simplistic the framework for the least square. We want to minimize the norm of this, the square norm of this, and the answer we are getting is your estimated channel should be function of the pilot, the received vector, the pilots, and this. So this is a very simplistic thing which no we first tested on our setup. And of course, know how do you verify this? You have estimated your channel, so you have to apply your engineering technologies. We have all learned the simplified path loss model, link budget, and all. So this is a like a verification tool. We can see that yes, your estimated channel is indeed no satisfying what is expected, and we had a no positive response up to this extent. Next, what we are intended to do right now is the channel estimates including the RIS into picture. So typically when there is no RIS, you only have the direct path. Now if you want to incorporate the RIS, you have to also focus on this path and this path. And as mentioned, we will be only doing the cascaded. We cannot do G and H separately. We have to do the cascaded channels over here. So typically you can reformulate the same without IRS structure in the presence of IRS, and by doing couple of steps, what you can see is that you can write your signal as some direct path plus the RIS reflected path, and of course your pilots will be there, and also the AWG and noise will be added here. So after doing simple signal processing techniques and writing in our suitable matrix and vector notational format, what we can really exploit is, yes, you can reformulate the same structure by in the framework of the our famous least square approach, and you can estimate the vector in this way. So this was we tried to do the algorithm steps of this, and we are working on it currently with the RIS aided channel estimations, which will be the input to how to control the phase shifts, which will give you the better performance in the exert end. So coming to our experimental part, so my team is working on the 5G setup, and we are started working using the open air interface. So we have established the core network, which no, you can think about this is a transmitter, which is a 5G transmitter base stations, and this is the user end. And what we have established is the OAI connections with streaming of video. We have seen that this is actually no working perfectly. Now we are doing the channel estimation part, and you are welcome to see the demo which we have downstairs. So what is what we are going to no demonstrate here is we can have one thing is static RIS, or we can have the control elements, the phases are changing continuously, or you can have a fixed angle, the maximum benefit, the maximum the beam width is focused to a particular angle. You have a transmitter, you have a receiver, and this is currently we are under process. So I want to also tell what other channel estimation is no the work is under process. This is the collaborator Samrat Mukhopadhyay from IIT Dhanbad. So his team is particularly focusing on the channel estimations, not the OFDM point of view, but in the OTFS point of view, and they also have come up with their own algorithms for the channel estimation part. And this showed so far is this the OTFS signal generations and receive receptions, and USRP based no, they have integrated with USRP, and they are implementing their algorithms. So thank you for no attending this, and any questions I can take. Yes, please. Yes, so order of pilots we need at least. So there are two things. One is if I want to estimate one by one these one, so we have to send the pilots greater than number of RIS elements. So let's say 64, I have to be used more than 64 set of pilots. People are also coming up with the concept of grouping concept. So where you don't have to focus on all the elements separately, but you can group, and the overhead is less. So you can have lesser pilots overhead in that case.
Massive MIMO kind of an array. So then do you think the number of pilots required increases or can it
Yes,
actually be
it will
reduced?
be more in that case if we talk about MIMO antennas in the base station side.
Okay, so the overhead actually increases.
Increases. Thanks. Any other question? Okay, then I invite the next speaker, who is Professor Prem Singh.
Good noon, everyone. I'm assistant professor at IIIT Bangalore. So I'll be presenting activities which we are doing here at in collaboration with some other institute, and these activities are funded by the COMET Foundation. So the aim is to develop a prototype for RIS-headed communication. This is funded by COMET Foundation, and three organizations are involved: IIIT Bangalore, Roorkee, and IIT Patna. This is the list of investigators from these institutes. So involved in this activity, and the aim of this is to develop prototype here, and then as mentioned by Mr. Sridhar, then probably the Comet Foundation will take it to commercialization. So we have designed two RIS. One is 2-bit with the 2-bit controller, and one is with 1-bit controller. We have set up a prototype. I'll show a video of the prototype, which is available as of now at IIT Roorkee and will be coming up here at IIIT Bangalore soon. And then our aim is to integrate in end-to-end 5G network. That is something that activity is going on. That this is one aspect of this project. The other aspect is, of course, RIS is one of the potential 6G technology. So we are also doing a lot of research related to this technology. So when you integrate this RIS with different technologies, then what are the changes you have to do? How do you optimize feeds? How you learn channels? Okay, and what are the kind of energy efficiency it is providing you? All that research is also going in parallel in these three institutes. So coming to the design one. So design one, we have, it's a 8x8 design, which is based on RF CMOS switches. These CMOS switches can be controlled by IO pins with any embedded platform. And it is a design for 3.5 gigahertz frequency, which is, you can say, it's an N78 band for 5G NR. And we have two sets of wires. One feeds the RF signal from patches to the control circuitry, and other is the offer the common ground for both DC and RF layers. Some of the results in the high frequency simulation softwares. You can say when the signal is incidenting on the RIS, it is perpendicular to the RIS, then it is indeed being reflected in certain directions, which you can see in the 3D radiation pattern in the middle, and On the right hand side, it's a 2D radiation pattern, which you can clearly see a peak coming in at that certain position. So this is the front view and back view of this RIS. So after designing this, we found that uh, this is the setup which we use to test this RIS. So the finding after designing this RIS was managing 2-bit. It's first it requires more power. Complexity is more. Complexity is more, and one more thing is 8 cross 8 RIS elements are not giving us enough gain. So then we sort of changed our strategy and went for the second design, which is 1-bit, in order to reduce the complexity, to make it simple. That design I'll explain now. And second thing is we increase the RIS elements from 8 cross 8 to 16 cross 16, and that we have tested. But we, with whatever test we have done, we still feel that 16 cross 16 is not giving us enough grain. So what we are doing is, and there is a constraint, you can't keep increasing these RIS elements, like you can say 16 cross 16, let's go for 64 cross 64, then there may be a lot of challenges in fabrications. So maybe the vendor will say, okay, I will not be able to fabricate such a big RIS, I need at least this should be the size. So to kind of do a balance between these, so we first designed 16 cross 16 1-bit RIS, which now I'm going to show. And then in order to increase the gain, we are now coming up with 9 such RIS plates. You can say each of that is 16 cross 16, so 3 cross 3, and then you control them together. That is the strategy we are now following. So coming to this, it's a pin diode based design, okay, where the reconfiguration can be done by setting pin diode on and off. So there are 2 patches for each RIS elements. They are connected to pin diode, and the position of pin diode when it is on off, it offers a different impedance. That RIS elements offer a different impedance, which changes the phase. So this is the idea. So again, pin diode can be reconfigured using any IO pins, uh, using any embedded system. This design is also 3.5 gigahertz. So our aim was from the beginning that we want to design at 3.5 gigahertz, because our aim is to finally integrate this as end-to-end 5G network. That is our aim. These are the results in the simulation. Now again, the horn antenna is at perpendicular to the RIS. Then you can see it is indeed radiating or reflecting the signal in certain direction, which you can see the 3D pattern and the 2D pattern. These are some of the patterns which we come up with. This is again in the high frequency simulation tools. So you can see when you set the different pattern, so this on off pattern means you have the different combination of on and off of the RIS elements. Then you can see the beam is being you have beam in different directions. So now this is the top layer, this is the bottom layer, 16 cross 16 RIS. This is our second design. One unit element on at this the top side, and on the right hand side that is the bottom side. Now this is a I think around 2 minutes video. If you can play this will show us the how we have been able to dynamically reconfigure the RIS and able to receive the signal. Voice, can it come?
This is our RIS. This is our RIS, fabricated RIS. And this side we have connected transmitted antenna perpendicular to the RIS. Frequency is 3.5 gigahertz. So for that we are using B210, and here it is transmitting setup. Now here we have connected receiver antenna. This is receiver antenna B210 2.3.5 gigahertz. Now we are seeing pattern here. So we are not able to see any pattern with this receiving antenna. It's connected approximately 40 degree. So we'll see here pattern. This is the pattern where we are not receiving any signal. Now we are going to change the pattern. So we connect it here, the MATLAB. So I'm changing pattern here. Now everything is static position. Transmitted antenna, receiver antenna. Now I'm changing here only pattern. Now we able to receive the signal. So everything is fixed here. Now transmitted receiver only we have changed the pattern here. Now we are receiving the signal here. So you can see here it is a different pattern. So in this pattern we are able to receive signal.
Next. Yeah. Okay. Thank you. So, other than that, as I said, this is one part of this project. Other is we are doing a lot of research in this domain. As I said, RIS is one of the, so we are doing a lot of research. So around this, we are exploring how do you integrate this technology with cell-free, NOMA, other waveform like FBMC, OTFS, IoT, and when how does it going to perform? You have physical impairment, you have hardware impairment, and synchronization impairment, and other that massive MIMO. So with that, I'll not take much time. So this is uh, the physical layer security when you have RIS. How do you use physical layer security when you are integrating RIS with other potential waveform like OTFS? Some of the results here. Then we are actively now involving or doing research in these areas. RIS assisted cell free, RIS aided communication with hardware impairment, then with cell free when you include hardware impairment, then RIS and FBMC, and there are so many other areas we have been working as far as RIS is concerned. I think this is the last slide. Thank you.
First of all, thank you. This demo was pretty elegant. My question is that the way the RIS and the antennas were placed, it seemed that the antennas were in the near field of that RIS. So, does it have? Did you see any effect on the beam forming direction, being it is so close?
So as I said, this is a still the prototype is, I would say, it's not very mature. Very still, we have been able to able to reproduce the 4 QAM symbols, and now the effects of near field, far field, and all that. That is something we are still investigating on. And then finally, as I said, the aim is to integrate this is in 5G network. But as of now, the answer is we have not investigated.
Okay, thank you.
Thank you.
Pattern has been changed.
So it's like, so let's say one bit. So when I say pattern means you change the combination of on and off of pin diodes. So as I said, this pin diode, it connects the 2 patches, and when it is on and off, this not radius, sorry, RIS elements offer different impedances, and that then when you come up the combination of this on and off, they offer different phases to the electromagnetic wave incidenting on it. So you have to come up with a phase such that it is changing the incident electromagnetic wave in certain direction. So changing pattern means we are coming with different on and off. So I think I showed one slide in the tool where we have different pattern of on and off of pin diodes.
So last question, please, because we have very less time.
Sir, I have a question. If we deploy the RIS in real time, like near where the signal are not there, so what are the elements are required to what quantity of the elements are required in a single board?
See, deploying and placing RIS is I would say is not a big deal. The main challenge is how you control it from base station.
Yes, sir.
That is the main challenge. And I'm sure while there are so many prototypes coming up in academia, the main challenge is how do you establish or how do you control this from base station. If you want to integrate that in, let's say, cellular network, if you want to integrate it from some other standards like, let's say, Wi-Fi and so on, then of course again the main challenge lies how do you the signal exchange between base station and this controller is happening, and how do you control that, because that phases you set that depends on what kind of channel you have. So that the channel is dynamic, which keeps changing. So that is the main challenge.
Yes, sir. Thank you, sir.
Yeah, just one last question. So the pattern change is shown in the demo. Is it a trial and error, or is the channel estimator at your RIS and plays a role?
No, here it's like in theory, in the simulation tool, we tested some of the angles, and then based on that, we try to reproduce that here. But as of now, you're saying there is no real-time channel estimation and feedback. That is not happening as of now. Yes, trial.
So with that, we thank the speaker now, and we'll quickly move to the online demo session. So I'll invite Smriti to please show us the demo. Yeah. Re- Hello. I request our speakers to please come to the stage so that we can present a memento. So, Dr. Priyanka Das and Dr. Prem. So now we will quickly move to the online demo session. So please.
Good afternoon, everyone. I'm Smriti Kumar. I'm a PhD scholar under Dr. Arzad, and I'm from IIT Bhilai. Today, I'm presenting an end-to-end test bed for RIS system, which has been developed under COMET Foundation. And you can see on the screen the institutes that have collaborated in this development process. So, first of all, uh, actually, for risk-aided communication, what we require is continuous monitoring of the channel for current for appropriateness of current risk configuration. Then a method to continuously modify the risk configuration based on wireless communication channel, among other factors, as well as a method to convey to the risk hardware uh, the RF level requirements like beam forming directions, number of beams, etc. For this purpose, an interface has been standardized as TSDSI STD 5003 interface. Okay, fine. This is the testbed architecture that that is in compliance with TSDSI architecture. You can see here it is a modular testbed. The channel estimation part, it has modules like channel estimation, generic risk controller, risk hardware. Is communicating with generic risk controller through risk specific controller, and risk specific controller and generic risk controller are communicating with each other through standardized interface. Uh, so this is the TSTSI standardized interface. You can see here. So as you can see here, uh, this is RF level channel control algorithm which communicates with dedicated risk controller that communicates with risk hardware. So these are the various phases of the message flow between this control algorithm and dedicated risk controller. As soon as our user is powered up or registered in the network, risk hardware discovery is done, and after the confirmation capability queries are done. This means that the algorithm asks for parameters like risk position, then range of the received angles, and the dedicated risk controller it responds to the queries. and based on the response, the algorithm decides the parameters for best reception, which are then communicated to the dedicated risk controller, and the risk controller then further communicates these to the RIS hardware through appropriate electrical signals. So, this this interface, as you can see here, it is modular, which means that there are specific modules which I have already shown. There are specific modules for channel estimation, specific modules for generic risk controller, and risk specific controller, uh, which can communicate with risk, so which makes it vendor independent and ensures interoperability. Then dynamic configuration process, which means that what happens that upon startup, the RF level channel control registers, the dedicated risk controller queries the capabilities and configures for the optimal beam forming through specific electrical instructions, which I've already explained in the last slide. Uh, then the abstraction of the system parameters, what it does that every interface, it can be vendor specific, and what it means that inter-vendor communication is also there. So what happens that because of this, scalability becomes easier. So this ensures consistent communication between different RIS architectures, which enables various designs to coexist. So this is our experimental setup. You can see there is a transmitter, receiver, and the line of sight communication has been blocked. And there is a RIS which aids this communication environment for better reception. Uh, Here the various modules which I have already discussed, like channel estimation algorithm, and this generic risk controller, they communicate through REST APIs for a modular functionality. So now we'll discuss. So now we'll discuss demo specific. Uh, so this is a high level summary of the setup. Um, we can see here, first of all, a USRP transmitter, it sends a pure tone of complex exponential signals. Then operating frequency is 5.5 gigahertz. Then comes the channel estimation part, which looks for the received signals amplitude. And then comes the control algorithm. We have implemented it in various forms. We have implemented it as exhaustive search, where overall valid patterns are means compared, and best beam forming angle or the optimal beam forming angle is decided based on that. And there is a slight efficient algorithm also, which I'll be showing in this presentation. uh, then there is this RIS hardware, which is open source RIS, and the control we have limited it to some state. To We have limited the control to same state for a column. Uh, this will be clearer when I'll show you the lookup table demo. So the operation sequence is like this. Uh, first comes the factory calibration part, where the vendor populates a lookup table. The vendor will set a given target interface parameter and find the best configuration for the target and populate the lookup table for field deployment, where this risk specific controller will use this lookup table. So in field operation, what will happen? Generic risk controller, it will monitor the ongoing channel and send a desired parameter towards the risk specific controller. This risk specific controller, which will perform a table lookup, this table, and configure the risk hardware accordingly. So now we will come to our algorithms. But first one is channel estimator. So what it does is it estimates the wireless channel from receiver and provides it via an API. What it does is it exposes the magnitude via a Flask API. So it computes the magnitude from the complex data received from the receiver in real time. So this is the channel estimation part of the test bed. Uh, the testbed has a modular approach. Researchers uh, who are developing RIS hardware can change only RIS specific controller and use the testbed. Researchers who are interested in channel estimation part, they can simply modify the channel estimation module and keep the other modules as it is. And those who are working on generic risk control, they can modify the generic risk controller and still the algorithm will work. The test bed will work. You can see the link. This is GitHub link where this detailed design development application development document is available. So that can be used to study this test bed, and researchers can also use this once they study this document. Uh, See, this channel estimation, as I have mentioned earlier, that a person who is interested in research for channel estimation, or a developer who wants to develop channel estimation for various communication in risk environment, they can incorporate measurements parameters suitable for their models. For example, if they want to use it for Wi-Fi system, Wi-Fi communication, they can integrate IEEE 802.11 standards and optimize high frequency multipath effects. Uh, Simply what they will need to do is there is a function get magnitude in the code, which can be which only needs to be modified, and it will start working for Wi-Fi system also. Then you can use my laptop. Okay, fine. Excuse me for the delay. So this is how the channel estimation algorithm works. You can see it continuously monitors the received signal and displays outputs the magnitude of the received signal through get API. um get API magnitude and for demonstration purpose, as I have mentioned earlier, we have only used complex exponential signal. This is solely to illustrate the complex. There are other variations like QPSK and OTFS which have been implemented. QPSK right now, many of you must have visited that anechoic chamber. So the setup was QPSK model there, and we can give live demo of there in the lab also. So this is how using GNU Radio Companion we have generated our uh, transmitted signal, which is a complex exponential signal, as you can see. So next comes lookup table, which I have already mentioned that which can be calibrated at the factory end by the vendor. So what it does, this algorithm populates a lookup table with beam forming angles corresponding the patterns to maximize the signal magnitude. What it does, it iterates through various patterns for beam forming angles for each angle and generates random patterns and evaluates their performance and sends the configuration patterns to RIS via serial communication. This is the setup where we have done the lookup table calibration. So this is the message flow. The lookup table algorithm, it initializes the serial communication to RIS hardware. It gets beam forming angle from the user and sends random patterns to the RIS, gets the magnitude of the received signal, and then based on the current magnitude, the maximum magnitude pattern is populated in the lookup table. So the APIs and interfaces that it uses are, as you can see, get magnitude API, lookup, which uses get method, retrieves the magnitude values from a signal data source. Then lookup table API that posts the magnitude, and the final API, it actually works to populate the lookup table. So here we have used a resolution of 10 degrees, limited the number of configurations by fixing the patterns to one column at a time, although 2 to the power 256 different patterns are possible if each of the elements in the configuration are configured at a time. We are using only beam forming aspects of the interface, but other aspects mentioned in TSDSI interface, that like multiple simultaneous beams and different incidence angles, etc., also can be utilized. So here you can see how lookup table is calibrated. First we call the channel estimation algorithm, then then we call the lookup table algorithm. It asks the user for the target beam forming angle and sends various patterns to RIS board. Here you can see simultaneously we are getting magnitude. The best magnitude is then identified, and that pattern is stored in beam forming in lookup table as the beam forming pattern for that particular angle. So you can see here how means it is changing the beam forming patterns and receiving the magnitude through channel estimation algorithm, and using that for decision making, which is the best beam forming angle for a particular angle. So this is an example of a lookup table. You can, as I have told you, we have used 10-degree resolution, and these are the various patterns of risk configuration uh, for these beamforming angles. Then comes this RIS specific controller. This is also vendor specific, and it depends upon the RIS hardware that we are using. So it queries beamforming angles from the lookup table, and receives once the beamforming angles are received, the corresponding angle is the corresponding configuration is sent to the RIS hardware, and via serial communication, and that way what it does it for what it does is for as per the command from generic risk controller, it decides which beam forming angle is best for a particular position of the receiver. So these are the APIs that it uses. As you can see, there is configuration right API, which is a part of TSDSI standard interface, which we have seen earlier. There is configuration right API. It uses this API to send the beamforming patterns to uh, RIS board, and gets the magnitude from channel estimation algorithm through this API. So here you can see that our interface is in compliant with TSDSI interface. So now comes the generic risk controller, this part. So this is the main algorithm that communicates between channel algorithm and RIS specific controller, and indirectly thus communicates with RIS hardware too. So this is the main control. So here we can see it retrieves valid angles from the RIS specific controller through capability query, sends each angle to the RIS specific controller module for RIS configuration, measures the magnitude using channel estimation algorithm, finds and sends the best angle for RIS configuration via RIS specific controller module using APIs. So these are the APIs consumed and the methods used in generic risk controller. So just for refreshing our memories, this is the TSDSI standard uh, uh, interface. Here you can see capability queries, responses, and configuration right. So all these functions have been incorporated in our test bed. So now you can see the complete function of the test bed. So first, channel estimation, then generic risk controller. You can see it is calculating the optimal angle for a particular location of the receiver based on the channel estimation magnitude and the risk configurations. Change the slide. So here you can see uh, at this position of the receiver, the incidence angle is 70°. Uh, but line of sight communication is obstructed. So you can see the testbed is creating virtual line of sight communication through beam forming angle of 70°. So this is how our testbed works. So as you can as I have already mentioned, so this is our approach is modular. So developers can modify uh, channel estimation and align with communication system they are using. RIS module replaced within one specific replaced with one specific to RIS system being used. The RSC module is designed to work seamlessly with GRC framework, facilitating smooth interaction with any RIS board and its specific control systems. We are using serial communication here, but there is no limitation. You can use any type of communication, even Bluetooth communication is possible. uh, Developers can modify communication protocols endpoints to align the requirements of their specific RIS hardware, and GRC is also flexible, that can also be changed as per the requirement of a particular RIS hardware. So please use this testbed for your RIS research, and detailed design document is available in this GitHub link. For support, you can contact our team. Um, and for any feature addition, Dr. Arzat is also available. These are the references that we have used. Thank you.
So with this, this technical session is now closed, and there is one small. The next session we are pushing after lunch. We'll go for lunch for now, and then after one update is that this particular demo which you are showing, it is also available in downstairs. Anytime you can visit the anechoic chamber and see this demo. On the whole day, it is available, and yeah. So let me present a memento and then close the session.
The lunch has been arranged in the multipurpose hall. We have a very short lunch break, half an hour. In half an hour, we have to come back here. So there are volunteers will coordinate there and then come back quickly. So we quickly go for lunch, have a bio break, and then come back, or bio break, lunch, and then come back. Thank you.
Your phone is here. Oh, then why not going? You're alone? Recently. You are alone here? No, no, मतलब यूपी से हूँ नोएडा के पास से दिल्ली के पास में नोएडा and Delhi is the border. Like you, Noida is the border of UP and Delhi. You can search it. Go. Amity University, Noida.
Thank you.
Next, I would like to invite Mr. Srinivasan from India. He's the expert in cellular biology testing with over 23 years of experience, spanning from 50 to working 60 technologies. He has been actively involved in contributing to cellular standardization for more than 30 years, engaging in research and serving as delegate in various PDPP various approaches. A key contributor to regional standardization effort in India, Srinivasan has been actively involved with the TSDSI inception in 2015. Welcome.
Yeah, good evening all. Yeah, we'll provide some views and some preliminary results or related. Okay, no? Sharing. Yes, sir. Our views and some preliminary results related to the deployment aspects of RIS, and then also current snapshot of what's happening in standards related to RIS and what's the views inside the standards related to RIS. The next slide. Okay, as outlined, I think I'll touch upon these points. So one is the RIS use cases and challenges. That means there are many use cases studied from the academic perspective and research perspective, but we just highlight which would be the top priority or the immediate relevance for deployment and standardization. And the gain as assessment aspect, I think this is touched upon from Tejas also. So the main challenge would be how do we really assess the gain on this RIS and some deployment related considerations. So we have some preliminary results on what is the optimal RIS size or number of RIS elements which would give the network the required throughput performance, and then status in the standardization. The next slide. Yeah. Yeah, next one. Yeah. I think this we touched upon mostly we can categorize an RIS into these three forms. The preliminary form would be there could be a pre-configured. I think yeah, there could be a pre-configured reflection, so it's not dynamically changeable. So this could be used for the coverage solutions where you can go to that specific place and fine tune that and have the required performance kind of thing. Next one is slightly network can kind of select which is the reflection needed. So this would require a thin control signal, and then third one is more dynamic beamforming, which would require some dynamic feedbacks, channel estimation, and related aspects. So I think the first one is like a passive, second one semi-static, and the last one is like a dynamic. I think the work would be around these variants. So that I think these are the list of the use cases or areas which has been investigated from the academia and the research perspective. There are multiple things where RIS could be useful, but I think the primary interest would be of coverage extension from the actual operator's perspective, and then potentially would that be also useful for spectral efficiency improvement? Because I think there it comes the multipath and multiple I think the ranks involved, and if the device is already in a rich scattered environment, so how the RIS would be really beneficial needs to be investigated. But I think these two are really of interest for the cellular system. And I think we list down some overview of the technical challenges, starting from the basically, okay, I think this is not visible, clearly visible. So one is the operator deployment, so which is almost equivalent to when you deploy a repeater or something, cost of the site acquisition and other things, and the panels to be how it is to be deployed. And then the scalability and integration, really, so when you have, instead of few elements in a whole network, if you would like to have a multiple RIS elements, how a network manage them in a centralized fashion. So that is another challenge. So when they start deploying in a large scale, this needs to be addressed. And the hardware aspects, I think that's now under investigation. So what would be the fabrication cost and what kind of control we need? I think one thing I have seen now, I think the activation delay of the pattern, I think that in line with the real beam switching, those would require some more details onto the fabrication aspects. And again, the other part is what is the actual performance gain in a real rich scatter environment, the urban environment where in the street or something where we have already a good multipath kind of thing. So how this would give a benefits needs to be investigated. And then this part is a modeling accuracy, because if you get into standardization, so we need to start with the channel model, clutters, and then how the RIS works in that. In that, you may need to model the RIS size and elements also. So that we have some research saying that accuracy is not perfect. So we need to investigate towards having a better channel model. And then the physical layer design challenges comes later when you have some actual feedback coming into picture, because that feedback needed with RIS is slightly different from feedback without RIS. So those aspects would require some deep review into the current NR or maybe whatever the 6G physical layer design, which is meant for some other purpose. So again, modifying that specific to RIS would require careful analysis. I think this was, I think, sorry, this one. So roughly, I think we need to for channel modeling, we need to do two things. One is the actual channel itself to be modeled. So there we see some challenges on that modeling. I think I couldn't exactly, maybe I'll share that one. This is our preliminary result. Another one is we have difficulty, okay, in modeling the panel itself. So depending on the panel modeling, there could be an inaccuracy that will lead to the gain assessment difference of around 6 dB. It's a preliminary. I think this was also reflected from earlier presentation. So I think we need to have a careful analysis which gives approximately closer results. Then that could form the basis for further investigation in standardization. So these two are the main challenges for standardization to pick up these activities. I think the main scenario, I think it is from some operator, the name is not mentioned here. Okay, the main trialed one was an coverage scenario. That means the UE is under the non-line of sight coverage. So when we have an RIS, that seems to be the improvement into the number of ranks from 1 to 2 to 3 to 4. So there is a quite good improvement on the throughput on this specific scenario. These are all some, again, so number of elements in RIS, how it impacts the overall rate gain, and number of elements, RIS elements in the cell, how it impacts the overall throughput gain of the cell. So we see the number of elements in RIS plays a good role, and number of RIS slightly increases. When you increases the number of RIS, that slightly have some impact onto the throughput. Overall, okay, maybe it's an initial preliminary result one. So fewer and bigger is better. That means fewer RIS elements with slight bigger panels seems to give some optimal performance as per the initial. Finally, it's targeting the overall cell throughput things. Yeah, I think now I'll spend some time on here. Overall, I think that there are three ways of the coverage solutions are important. Like starting from LTE itself, there was some coverage solution was developed, which is a complete relay concept. Actually, the whole the relay component will have the complete UE part, including the core network, and then it replicates towards the UE. But that was completely a big overhead because that architecture also involves many changes. So due to that reason that in 3GPP NR, we have this decode and forward, which is the simplest. The stack part is very simplified compared to the LTE relay. So that's what the IAB. So that seems reasonable, okay, comparatively compared to the LTE relay. that was a reasonable solution which provides some coverage extension into the NR. And then later, I think there are some further simplified version has been introduced in release 17, which is the network controlled repeater. So where only it's an actual repeater, but the repeater's behavior is network controlled via a thin control channel. So that allows network control over that. As of now, maybe many operators deploy the passive repeater. So now this will have a flexibility of network. Because of the beam-based interface, there could be a need to control this closely. So that now RIS comes into the another category called which is reflect and beamforming. So which have some overlap with the NIS, at least that NCR, at least related to the control interface between the central element and the RIS. And again, smart, it requires something more smart radio environment, again, the channel estimation and beam switching related things. The additional challenges are there, but at least for the initial work or something, there is a quite good overlap with the NCR. So what is the latest views inside 3GPP actually? So this was mentioned by many operators. I think it started from release 18 onwards. There are many operators seems this is a nice to have feature for coverage extension compared, like it's, they wanted to try out an alternative to the NCR kind of thing, how this work, because compared to NCR, this power and other things are a little less. So due to that reason, wanted to study, but the general agreement was that it needs to start with the study to understand the proper channel modeling and gain assessment related to that. So mostly if a work starts in 3GPP, in case if a work starts, that would start with the channel modeling, and then usually that's normally any study work starts in 3GPP with the channel model followed by the use case needs to be prioritized and that description should be clarified. So on that, if the gains and results has been evaluated, then the next step could continue. And so what would be the impact at 3GPP in case if it goes to 3GPP, what's the impacts to the specification? So there are multiple things. So I think the study should define the model, channel model and evaluation methodology. That is to move forward the study. But once the study done, so there are different functional aspects into the 3GPP radio interface. So initial access, synchronization, and how to identify SL is RIS. I'm getting the beam via RIS or not. These are all the just camping related things. And then on the MIMO related aspects, there are the codebook related impacts and how the beam switching and beam selection happens with and without RIS. And then the measurements and feedbacks. I have seen this channel estimation model in the morning slides. So how that works and in a transparent way when multiple UE is getting into the system. So all these needs to be answered in a 3GPP study. So I think there is enough work to do to solve these problems to get into a standard. And then there are, I think, as we see, because we need to also see the comparative benefits against the solutions already available, like NCR is a potential available candidate, which is specified already and gives some benefits. So what's the gain versus pain for bringing something new with respect to NCR? Also would be studied as part of the ongoing, okay, this impact should be studied when this study really starts in 3GP. I think I have a last slide. Yeah, again, I think standardization agrees that this is a very hard topic in the research, but from implementation point of view, there are many open questions exist. How do we really realize that? And it has a potential 3GPP impact wise, if you compare, it has an overlap with the NCR study actually. And then we have the summary of preliminary studies. I think this I have just started. It is effective for the coverage performance. And then again, if you want to have a better performance, the surface needs to be large. And then again, I am repeating, the model needs to be studied carefully. And mainly the CSA acquisition waveform related things. So I just kept this chart, the hype chart. So, okay, we know that RIS started innovation trigger, it almost reaches the peak of the innovation, but for standardization should start from here actually. So you have almost many things stabilized. Now standardization will pick up from here via its own steps of study and other things, but parallel deployments in a transparent 3GPP transparent solutions could be investigated parallelly to so via prototyping or something. Yeah, that's all from our view.
The nice presentation. Thank you. Can you go to that slide where you're showing that gain versus?
This one or
Yeah. So what is that x-axis? What is that Voronic cell?
sorry?
Average risk in
Oh,
each.
this is okay. Maybe a cell type. I need to check from this. Just in a general cell. Okay, maybe it's all the coverage overlapped or something. From simulation perspective, they have this term. I need to check. It's
Is it standardized? Is that Voronic
I
or?
think so. I think that was, yeah, it's the term. I think on a maybe a spherical cell kind of thing. But for simulation purpose, they might have used that term actually.
Okay, so this is not some standard
No, no,
terminology.
no.
It is, oh,
Yeah.
okay. Thank you.
Integrating that in cellular network. So with our study, what we have feel that you have to you you have to kind of make a lot of changes in reference signal design when you acquire channel estimation through RIS, and that is a challenging thing. So, what is your both of your take on that? How do you then? What's the plan for integrating that in a cellular network?
See, I think what currently going on in TSDSI is a risk controller to risk interface, which does not. It's almost transparent to the reference signal channel estimation. It just gives the capability queries, get capability, gives some directions for beamforming. This could be a transparent one which would not, okay, which is need not be, the air interface is not impacted. So this could be an application, an operator can make use of this from his application to the vendor panel kind of, which may not even come into the purview of the 3GPP architecture, because it's generally completely and over the outside network elements, it could be standardized. But if for the real performance or optimal performance, if you need the reference signal channel estimation related design, that needs to be integrated into the basic 3GPP standard. That cannot be done. Okay, if that done independently, we have many other issues to handle.
Just to add to what Srinivas is saying. So what TSDSA was done is actually that RIS controller thing. So the channel estimation is not part of that. So for the channel estimation, so what I would suggest is for 5G we can't change the pilot. So you have to leave with whatever is the piloted thing. But if you figure out that there are improvements we need to do for increasing the pilots or something like that, we would have to do that in 6G, like, because that opens up completely. You can decide where to put your pilots and all that. And specifically too, I think if you see the two things which are shown in green, right, in slide 2, so these two lines are there in the 6G. So it's still not clear. This was the last meeting, like RIS can be part of that two lines, which are already incorporated into the 6G study item. So we will see how it evolves. Maybe as we get more results, maybe at some point RIS may get in. But initially, it is captured as part of coverage extension or efficiency improvement. Both these lines are today there in the standard. Last week, whatever was finalized in the study item, it is there. So I think, at least from my side, I think it's not precluding RIS in 6G.
I think that is that's a too early statement. No, I think actually the to answer, 6G study is just now starting. It's a perception inside standard that this is not an immediate priority item, because as I said, because it has to start with channel model and all. So there is some channel model work needed for the basic FR3 and other things. So this can come in.
Yeah, we will discuss offline. Okay, thanks. Everyone, let us thanks the speaker. So next we have Mr. Jinesh from He leads the system engineering team in MediaTek Bangalore, focused on conducting system evaluations and performance analysis go beyond 5G and 6G wireless communication systems. Please come. Thank you.
Yeah, always pleasure to be here. I'm Jinesh, and the topic that we're going to present is on this RIS assistance. So this work we have been doing from here, from MediaTek Bangalore, and I've been working on this with my colleagues Chandra and Rama, who are there with me here, and of course Akshay is always there. So this is more of a kind of a case study kind of a thing, wherein we try to see the problems with fixed wireless access and then see how RIS can help there. So fixed wireless access is kind of like it's one of the most successful 5G use cases, which actually has been somewhat monetized. So within the scope of release 20, it has already been accepted as one of the use cases that will be studied further in the context of 3GPP. And so fixed wireless access, yeah, typically it comprises of a base station unit, and there may or may not be an outdoor unit which connects the signal from the 5G NR signal to the indoor unit, either through a wired connection or this, if, or alternatively these two can be clubbed inside, as shown here. So these are, and the type of deployment, whether it's outdoor or indoor, it depends on the environment and specific requirements. So if there are typically narrow alleys and a lot of losses, outdoor losses like blockage, etc., it's typically indoor. And if it's like a line of sight communication where there is no significant blockage, and like semi-urban or rural kind of connectivity, you can typically an indoor CPE kind of scenario is preferred. But having said that, there are challenges in both scenarios. So in outdoor, typically what happens is that you don't have this penetration losses. So performance is better because there is a better link between the G node B and the CPE unit. But then the cost is typically higher per CPE device. For indoor CPEs, you have this penetration losses, but the cost is lower because you don't need weatherproofing, etc. And so, uh, you know, but then it's at the cost of performance. So there are pros and cons. So the challenge in these kind of scenarios is one of blockage of the G node B to the outdoor CPE link due to buildings and obstacles for the outdoor CPE, and also for uplink coverage enhancement because of power limitations in the uplink. And because uplink power transmission is typically way lesser than the downlink power transmission. And for indoor CPs, it's the over and above these kind of losses, you can have this penetration losses because of the thick walls and the indoor path loss from the kind of outdoor, from the unit to the CP. From the wall to the CP, there would be an additional indoor path losses. So to summarize, there are challenges in fixed wireless deployments, and we need, you know, we need spectral efficiency enhancements and also coverage enhancements, especially in the uplink. And this is needed for indoor deployments of this CPE and also for outdoor deployments. So one of the directions, there are many directions. One of the things that we are looking at is using RIS assistance to indoor CP and outdoor CP for enhancements in spectral efficiency and coverage. So that's what we'll talk about. So we saw kind of experiments already wherein we could see the gains. So we'll talk about how these gains can be realized for RSRP enhancement. uh, for a particular RIS configuration that's available commercially. So we see that this RIS is a feasible option to enhance the communication between the G-Node B and this CP, either outdoor or indoor, and it can be used for RSRP enhancement. So for typical RIS sizes, these are the sizes of the RIS. I think we saw these kind of sizes below in the second floor. Uh, so for a 10 cross 10 RIS at around 4 gigahertz, it will be around 38 centimeter cross 38 centimeter. And what we can get out of this without assuming any path loss, etc. That means because of the device, it is around 40 to 60 dB potential risk advantage on the RSRP, and this can be obtained in outdoor and indoor risk connected CPEs. And so this RSRP benefit is contributed from the risk reflection and refraction. So this is because of the number of elements and the risk gain in a particular direction. And so for outdoor CPE, this risk gains can work over the impairments, which are like blockage and obstacles. And also it can, which can be typically like, we see that in deployments, the blockage losses can be of the order of 10 to 30 dB. And coverage limitations of the order of, coverage limitations is in the uplink. And in indoor CPE with RIS, there is this additional, so this is the outdoor CPE kind of scenario, wherein you have a blockage of the main link, and then you have a stronger link through the RIS, which can give this kind of gains over the blockage. This blockage link can be around 10 to 30 dB. And in this, through this indirect link, we can enhance the throughput and coverage performance. So for indoor CPE, over and above this kind of situations, what happens is that there is this, say this is the wall of the indoor building, and the risk can be placed on the window. So the wall penetration losses can be avoided. And then we have the signal that is intelligently reflected through this wall unit into the CPE, which is placed away from the wall. So the penetration losses due to the wall and also the indoor path loss can be avoided, providing additional around 12.5 dB gain because of this distance to wall attenuation being saved for a typical 25-meter radius assumption with this 4 gigahertz operation. So these are the kind of RIS RSRP advantages that we can get. So now what we do is, this is without any, we don't assume path loss, right? So to assume path loss and a systemic loss in a kind of a system evaluation, a cellular system evaluation, we look at this throughput performance in outdoor CPEs and indoor CPEs. So this is a cellular system evaluation with 7 cell and 3 sectors per cell and ISD of 500 meter. And we assume UE drops, basically CPA drops, typically 6 CPAs per sector, and then randomly dropped, and 50% of them experience this blockage for the outdoor CP scenario. And we also have indoor CP scenario wherein this penetration losses are also there, along with the distance from the wall to the CP unit, there will be losses. And we examine what kind of performances we can get. So I would just like to point out Chandra, who has helped doing this evaluations from here in MediaTek. So what we see is this risk significantly enhances the performance of outdoor CP and indoor CP. And here is a performance in the downlink and the uplink, with and without the risk assistance. And but then there are CPEs which don't have this coverage limitation because of the blockages. We kind of exclude them to see the performance gain, because the deployment would typically assume there is a coverage hole kind of scenario, and the order of gains are of this nature. It's like several orders of magnitude in the user perceived throughput. And similarly in the indoor CPE, wherein the challenge is even more because of penetration losses, the gains are even more, both in the downlink and the uplink. And the reasons, so we see this, the gains of this order in these kind of scenarios, which is like 360% and that. And the reasons for this performance is the risk deployment in the cellular system, the beamforming, and also without significantly enhancing the co-channel interference. And also we have, because of this higher, uh, uh, risk gain in the uplink, we can use the resources more efficiently and flush out data in this bursty traffic. So all this contributes to this kind of gains which are of several orders in magnitude. So similarly, yeah, once you see spectral efficiency enhancement gains, similarly you can see coverage enhancement gains as well in the uplink. So uplink coverage gains in various power classes of the CPE UE. We can see the gains are of the order of 34 to 26. But if the power class is higher, the challenge of coverage extension is lower. So we get more gains when the power class is higher. That means when you have lower transmit power. So, and the gains are of this order by putting this RIS element. So we have early views on the POC as well, but this is a kind of in a lab environment, not in a deployment. But then through a live network, we have an indoor. This is our setup here. Then it's a fixed RIS. It's a dynamic RIS configured in static scenario because it's fixed wireless access, right? And so we have this kind of G0 be placed here, and there are losses. So if this is not there, there's a corridor, and there is a good coverage scenario, and there is a bad coverage scenario. So when it is without this, uh, if you look at the coverage whole kind of scenario, that means location 2, there's significant drop in the throughput. If you look at both the uplink and especially in the uplink. And then with this assistance, you can have this kind of gains of significant order, like 300% in the uplink. So, but when you go from in the downlink, in the lab scenario, we couldn't kind of get a good coverage whole kind of scenario. The transmit power is pretty high, at least 20 dB higher. So we didn't get a good scenario, so we couldn't get that kind of gains in the downlink. But this is an ongoing experiment, and we believe that in a better lab setup, we can have more gains. And these numbers also, like, actually the ZPE also showed this kind of numbers, both in the uplink and downlink in coverage limited scenarios. And we kind of get that in the uplink part because we already could identify a coverage limited scenario and we could get this throughput enhancement. So in summary, based on the performance, we see, and as identified by many, that RIS can provide the significant gains and to address these blockages and penetration losses, especially in fixed wireless access. Because you don't have this kind of, it's a static scenario or a one-time configuration scenario, as long as, or at least you can say that the beams change slowly over time. And so there are throughput gains and coverage gains, uh, which are of several orders in magnitude, both in the uplink and downlink. Yeah, so that's about it. Yeah, if there are questions. Yeah, please.
Yeah, thank you for the presentation. So in that slide, when you did the system level simulation,
Yeah.
the
Yeah.
yeah here, what was the carrier frequency you took?
Yeah,
It
we
was
took around 3.5 gigahertz
3.5.
FR1.
Okay, and you have you was told you are dropping in UEs on an
Yeah,
average.
yeah,
So
like 6 UEs per. Yeah, I think we can show that. Just, there are six CPU UEs
hmm.
per sector.
And it's a fixed CP, right?
Yeah, CP
It's a
locations
fixed.
will be fixed.
And RIS also is randomly dropped.
No, no, is one RIS per CP
Okay.
and placed at the same height of the CP.
Okay. So
It's one RIS per CP kind of thing.
and the distance is always fixed.
Distances, yeah, typically around 20 meters, 10 to 20 meters. If it's indoor, it's within 20 meters. If it is outdoor, it is 10 to 20 meters. So this is the kind of, yeah, we have a, oh, this, yeah, it's like, it's a 21 ring simulator with all the configurations here. And yeah, it's per floor. Like you place, you drop the CPEs and then in a building, and then it's one CPE per building, and then one RIS per CPE, and 6 such drops can be done. And we can run this many times to do an averaging.
Okay, so I didn't quite get. So how do you fix the RIS distance from the CP, ODCP? You fixed it as 2 to 10 meter distance from OD. It's in the same height, like
it's at the same height.
Same.
That's the assumption.
Okay. Okay. Thank you.
Yeah, please.
You have assumed in the practical results and here also that the RIS width is element width is lambda by 2.
Yeah.
And,
Yes,
and you are
lambda by
saying
2.
that you are able to accommodate 16 RIS elements in 60 centimeters.
Yes.
Does it
I think
match
it's,
up?
yeah, it's based on a commercial.
So 8 centimeter, 4.
No, 60 centimeters.
38. You are able to accommodate 38. So if you go to the first slide
First slide.
here.
Yeah, this one.
So here you have 38. So here you do not have lambda by 2 separation.
No, this is not 38 centimeters, 10 cross 10 RIS.
So 38 cross 38 RIS in 60 cross 60 centimeter.
No. 38 cross 38 centimeter is for a 10 cross 10. Just look at the colors.
Acha, okay.
60 by 60 is another configuration for 16 cross 16 RIS.
Okay,
Yeah.
okay.
Yeah.
Yeah, thank you.
Any other questions? So I have one question. Like I have been hearing that FWA is the main use case of FR2 to monetize FR2 deployment of 5G. Is it a valid
Yeah.
for FR1 as well?
It's for
It looks
FR1.
like by seeing your results.
Actually, FR2 is, I think FR2 is also a good candidate.
Okay.
Because there's a lot of spectrum available.
Yes.
But if you look at US, I mean, their 6 gigahertz is wholly unlicensed
Okay.
as of now. So there will be some kind of, there are unlicensed deployments in fixed wireless access.
Okay.
From
In
PMO.
FR1 as well.
Yeah, in FR1. Like there is CBRS and then those other frequencies.
Okay.
Around CBRS, and the other one is 6 gigahertz unlicensed, 5 gigahertz unlicensed. They all have this kind of solutions. Yeah.
Thank you.
Yeah, even the actual measurements which you had shown in that slide, right, with the physical after
configuration.
So this was done in far field, or how did you did the measurement?
See, yeah. No, these are not. This part is a system
No,
evaluation.
not that one. The one
here,
I think.
right?
No, not this here. Just before that, this one. This is
Yeah.
actual measurement, right?
This is actual measurement on an experimental UE. So we can read the measurements on RSRP and throughput. And whether it's far field or near field depends on the 2D square by lambda.
So do you have the distance numbers in this? Where did you keep your
3.5, right? There, like under 10 meters, it will be in the near field.
So these are near
There will
field
be some. If it's under 10 meters, it will be typically in the near field.
Near field, yeah.
3.5 gigahertz and this kind of risk. That's what, if I'm not wrong, right? Under 10 meters, it will be in the near field. But we don't use near field beamforming.
So that distance which you're showing 4 meter, 10 meter and all that, right?
Yes.
So can you just explain that? So you have kept a G node.
Yeah. So there's a lab G node, indoor G node read. And then there is this corridor.
Okay.
And this corridor.
Okay.
And the G node B is placed in the lab, and there's a glass separation.
Okay.
So you forget there is this UV outside, so it's very close. So it is like a very strong RSRP scenario.
Okay.
And then you have this corridor, and then what we do is we kind of really go further away so that you lose the errors component. And then you place it there and see what is the throughput loss.
So then the distance between RIS and that OC2 where you have done the measurement is 10 meter, right? So then these results are far field results, right?
We didn't check for near field conditions.
Oh, okay.
Use of near field beamforming. But because of 2D square by lambda and some fraction of that, if you look at aperture and the wavelength, I think under 10 meters will be typically in the near field.
And these are blind correction, right? It's not like channel estimate and all that. Uh, Okay.
It's not on.
You are not channel estimation and all that.
Yeah, but
Do you have an
existing
additional?
channel estimation will be done. So it's
Whatever
not
the
a live,
existing channel model,
it's a
like,
live network, but there is no RIS processing on the RIS signal. This is on a live network. If you look at it, it's a mobile. This is it's the live network.
okay, okay,
So there is, and it's a static RIS, so there is no need of a
okay,
controller. You kind of, manually kind of place it there, and then whatever is the signal. So this will be typically SSB or SRP. What you see.
okay. And that angle is 45 degree, or you have kept it like this?
It's a 45 degree.
45
So
degree.
that it's this is optimized for 45 incident and 45.
Okay, thank you.
Okay, so let us thank the speaker. Thank you. So our next talk is online by Mr. Vinos. Mr. Vinos joined Qualcomm in 2021 and has served over the years in roles spanning technology and standardization. He has responsibility for Qualcomm standardization engagement in India and Southeast Asia. Uh, Please welcome Mr. Vinos, Dr. Vinos.
Hi, good evening. Just checking if my audio is coming through.
Yeah, you are audible.
Okay, I need a share permission so that.
Can you give him right to share? Do you have his presentation?
No, I don't have his presentation. I'll share.
Yes.
I can share it from my side. I think somebody needs to enable it in the tool.
Yeah, we are looking into it.
Yes,
Okay.
he's
Yeah, please go.
Okay. Thank you for having me. And sorry I couldn't make it to the event. I'm also running a little short of time, so I'll try to actually squeeze it a little faster. So the what I intend to speak today is about RIS as a smart repeater specifically for coverage extension, one of the use cases which being pursued by India in several other platforms. So I believe that this particular slide seen in here has been discussed multiple times. So the whole idea about having RAS is have reflective surfaces. I think the analogy I would like to have is we are having like small mirrors, literally reflecting radio signals in this particular case in a way into directions we really need it for either for amplifying the signal or for killing a particular signal, right? For lack of a word, right? So it has potential to improve spectral efficiency. It can circumvent blockages and alleviate the problem of multipath. And wherever you have MIMO and poor scatter environment, it can actually balance out a few other elements as well. It's been proven to be energy efficient, and the one of the main things I would like to take in this particular talk is explain how this fits into the 3GPP framework and how some of the existing control channel tools available in there can be leveraged for deploying this particular use case, right? So the way at least we see the application of RIS is to control the radio environment so that you get it in a manner you want it, right? So it's basically reflective surfaces enabled through the use of the right or the useful of diodes. So as you can see the uh, um, plot seen on the right hand side, depending on how you actually articulate it, you can actually get close to 20 plus dB gain in certain bands, right? So this particular simulation you're seeing in here, it's not simulation, it's actually real-time deployment. It's on the 2.3 gigahertz channel, which we had been testing on in our headquarters in San Diego. So at least the concept has its point. The catch always was, where do you apply it and how do you actually apply it, and what will be the use case when it comes to the deployment thing. So that's why these four different deployment scenarios were of consideration within the team and also within the industry. The first one on the top left is the vanilla one, where you have the base station transmitting, you have a end user available somewhere, you use the IRS, you get the reflections, you basically get it in the manner you want. That is not right. It has its value, but you have other solutions addressing that particular use case as well. The real field use will come in the remaining three you actually see in here, right? Either you have a multi-user downlink, meaning multiple users will have to be served, but again using a single IRS, or you have multiple IRSs, you should have a single way of controlling them so that multiple users can be scheduled and delivered signals in the downlink. And the use case which I am interested in is the last one, where you have the concept of select users, meaning they are outside of your coverage boundary, outside of the regular coverage itself. And can the RAS be used in a manner in which you can actually extend the signal to the those low SINR users, right? So this is the 3GPP solution which I had been actually mentioned about, and that's about a network control repeater. So in release 18, this was studied where the amplify and forward repeater was actually enhanced in the 5G case, and signaling support was enabled in that particular release so that you will be able to control that repeater to apply your functions. What we were able to show working in our lab is leverage those control channels, substitute the repeater with an RIS, and show that similar performance can be availed in this particular use case, right? So it was basically leveraging the release 18 control interface and then some selective changes which were brought in during the release 19. Uh, Again, I need to admit, I really don't know what happened during release 19 and what is the current status today. But the project when we kickstarted within Qualcomm was about, can we simplify this repeater and then really see, if RAS can serve that purpose. Why did we do that? The reason we did that was, once the technology was available, then a market can basically adopt it, do product innovation around that particular concept, and then develop off 3GPP solutions and plug it into a existing cellular network deployment. Right. So that was the baseline in which we initiated this project, and then we were able to show that yes, in practice that is actually possible. So two more slides I have in here. One is about the general use case in which this coverage and net extension related proposal actually comes in handy. So what you are seeing in here is actually a huge terrain. Let's assume very large cells where there is line of sight blockages. You have to rely on RAS or some other coverage extension means to do it. Of course, there are other solutions like satellites and other things you can bring in. But if you're actually extending a terrestrial network, then this particular RAS model is like one such solution, right? So the only new thing in here is the RAS which you are seeing in the downlink and uplink is basically controlled by the base station, and in a manner, it treats it more like a repeater in itself. And the UE, which is actually outside of the coverage area, is still able to receive performance, right? And how is it actually fitted to the 60 story? So if you look into a potential 60 deployment, which we are considering in our proposals, it's going to be a blend of several solutions, including satellite, millimeter wave, sub 7 gigahertz spectrum and other related things. And we do see a role for RIs to play in here, like cost effective, implementation specific, region specific repeater, which can leverage 3GPP signaling and then actually bring in those values, right? I think that's what I had for the 10 minutes or so I had. If there are like any one or two quick questions, I can take it and then I'll have to leave.
So
Yes, any questions, please? Any questions? Okay. Okay, thank you, Dr. Vinus, for the presentation, for the talk.
Thank
Thank you
you,
very
and sorry
much.
for rushing. My next meeting is actually waiting for me. Thank you.
Yes. Okay, thank you. Okay, so everyone, yeah, this was the last talk for this session. So before ending this, I would like to invite all the speakers and the CEO COMET Foundation on the stage, please, and hand over mementos to the speaker. So first, yeah, first is Mr. Vishnu, please, if you can. Srinivasan. Jinesh. Okay, so no, I'm not a speaker. That's it. So now I would like to hand over the stage to no, no, only three. No? Jinesh and fourth was online. Online. Am I missing? Srinivasan and Jinesh. Just a minute. Let me check. Jishnu, Srinivasan, then Jinesh. Jinesh is the 1%. Okay. Okay, so for the next session, I would like to invite the session chair, Dr. Saptarshi Chaudhary. Dr. Saptarshi is currently head of Radio Access Network System Engineering, RIS. He has 20 years of experience working broadly in wireless communication domain, in particular 6G research, 5G advanced research, and beyond wireless research, 5G system, link level simulation, complex algorithm simulation and design, and radio access design and development, etc.
Okay, good afternoon. I think it's a long day. So what we'll start off with is the research labs that are engaged in doing these RIS activities. It is a complex subject as you might be seeing it actually, and the endeavor is to come up with the efficient lab for this proper evaluation of this technology. Without this, I think the success is very difficult to achieve. You have seen this. The initial the use cases is still the coverage, but we are talk about the more complex beamforming and all this stuff. It takes time. Any technology of this nature to get into a proper deployment case is humongously research oriented and deployment tested items. So what we do here is that we have 5 speakers here actually who are representing their own labs in their institutes and in academia and in the companies over here. So the first speaker, I invite Professor Debrati Das, from IIT KGB actually. So are you there actually? Okay.
Okay. Is that the इसमें नहीं आ रही तो क्या करेंगे proceed or let me do the second part let her stay okay she's still joining Sridhar so let's move okay may I invite Anand from CDOT actually to share his experience in his research lab.
Yeah, good afternoon. Thank you for inviting me for the small talk. Actually, myself and Amit, we have just started off some small 6G study group in CDOT Bangalore office. And as a part of this activity, we have explored the RIS area. So as we come from the government backside, we are looking at enhancing. So let's say we have the coverage till the Gram Panchayat, can we go to the villages? How far, how tough is it for that last mile? Or let's say last but 1 mile connectivity using RF, okay? So signal is available on your phone, but it is not good quality. So that's what just, can we extend it further? Let the slide come in the meantime. So let me speak. Let's not waste time. So the objective is very straightforward. So objective is coverage. Okay, not capacity. Right now, not looking at capacity. I'm looking at coverage. And as the Indian mindset goes, how difficult is it to beat copper sheet? Can somebody tell me? I mean, I really, I'm finding it hard to beat a copper sheet in terms of gain. So in our lab, we try to simulate a real world scenario where you need to bend the RF to a village, a particular area. I'm not talking about beam steering or beam forming of high end stuff. I'm not thinking about any pilot signal design. I'm just asking a very basic question. So how difficult is it that just put a copper sheet at an angle which ensures that the angle of incidence is equal to angle of reflection? Basically, you're trying to beat that. Okay, it's very difficult for us. We tried to do it ourselves in house. The closest we could defeat copper was by 6 dB. That's all margin we could get. So no copper with RIS. So just think about 3 levels. We are missing the central part of it actually. Second part which we faced was the reciprocity of the whole system actually. The system RIS by inherent has a reciprocity problem because the code book is actually proportional to the angle of incidence and the angle of reflection. Now, if you reverse it, that is when the mobile wants to talk to the tower backwards, it doesn't work very well. It doesn't give you equal things. So you're just looking at one dimension, you're seeing simplex only. We have not gone to duplex still. Many research papers I still see have not gone to duplex, they have not gone to broadband, they have not gone to FR1, really speaking, FR1 in the village level, which is band 3. The unit cell size for us is around 8 to 10 centimeters. Okay, one unit cell. So you just give me an estimate of the RIS 64 by 64 what we have. So as we investigate further, what we feel is a thorough investigation on the system level architecture in the coverage domain is what has to be taken by the academia. Maybe somebody can come up with a design and please reach out to me and showcase this is the RIS. Don't care about the angle of incidence and angle of reflection. It works very well. Then the question comes out automatically, is it not the same as copper? Okay, copper sheet and aluminum sheet will do as well unless you really want to steer a beam. And how difficult is it to bend a beam? Actually, this thought process comes from inside. When we see the solar panels could be highly efficient if you have a motor which can track the sun, but hardly 80% in India at least don't. We are like the, what should I say, the bare minima kind of people. So it just works for us. So we are happy with it. So with the correct orientation, I think we don't need, in one sense, the RIS. So if you want to do, if you really want to beat the copper, you have to work really hard. There are two domains which we tried. One of the domain which we tried to do was to see, okay, can we break a hill? Can we come across the hill? Because when we saw the DOT reports regarding coverage, we saw the Western Ghats and the Northern Himalayan belts are the one which is not covered. Coverage. I'm not talking about throughput here. I'm just talking about coverage. Okay, just give a coverage. So just get a couple of extra dots on your symbol. That's what I'm looking at. So we try to do with this project, Drishti, we just try to do it, but where's the point? Point, it's not on. Yeah, it's on. I don't know. Okay. So we are trying to jump over a hill. Can we jump over a hill? Is it difficult? We tried to do Nandi Hills. We did the simulation of Nandi Hills. Can we jump over a Nandi Hill? It's not easy. It's not as easy as you think. So we developed a couple of PCBs. We tried to make a panel out of it. We tried to jump. No, not, we could not get proper results still. So we are still away from the whole thing. We know it can be done easily. So our objective financially is the repeater. So financial competitor for us, RIS is the repeater. Just put a repeater and all you can, problem is solved actually. So the cost is not a base station, but the cost of is a repeater cost around 1 lakh to 5 lakh range. Can you come up with the entire structure of an RIS with all the things in place on top of hill? And we met one BSNL person, and the one simple question she asked was really bonkered my head was, what if a tree grows in front of an RIS structure? That's whole thing goes for a toss. So there are a lot of simple solution questions which academia has to focus on. So I understand it is fun to play with OTFS and RIS and heterogeneous stuff, but just simple questions. If you can, somebody can help me out. It really helps me to cover the last mile of a already deployed 4G station to just reach out to the next village. Oh, that comes to the second question. Okay, we did a large scale analysis of this, and we found that it's not just the tower. The tower has to, base station tower should have a dedicated antenna port which should beam towards the hill. Now, which operator in their right mind will want to share, take a base station just pointing downwards, make it look upwards, hit a hill, and then put RIS down the hill. So the PTGTGR into GRIS, that comes in the equation now, GRIS, the gain of the RIS. So you need a very big structure on top of a hill which does not, which withstands all the rain, all the fall, all the foliage, all the bad things nature can push, including monkeys and elephants. And then on the other side of the hill, you must get a good coverage. Okay, so please, somebody show me a big good scenario. We have done the simulations, not simulations in, of course, and some things, but it's tough. It's tough for us to do so. we could just with a copper sheet, we could do it actually. Just copper sheet. Is working very well. Come to our lab one time. I will show you what magic a copper sheet can do, which many of the RIS can't. We do have a reflector array structure. We do have a near field structure, a simple copper structure. That was a eureka moment in our lab actually. One of our engineers were trying to do, and we could get around 10 dB gain just like that. Okay. And what we had to do was to develop small scale antennas of this nature of ourselves. We were not using that stick antenna because it's not directional. See, we don't want to eliminate the whole structure. We want to eliminate a subsection of the structure. So we had to come up with our own designs. So once the design was the antenna itself, we had done for a Wi-Fi, a 4G, and a Wi-Fi and 5G antenna. And then all the antennas we developed our own. We are ready to share to any research academia. One of the RIS boards which we developed, which demonstrated some of the use cases with just a copper sheet. Okay, so it's doable with a copper sheet. So unless you have a really fancy things, you can tell me, Anand, for a coverage, I need to have a show me the results. Just to do so, one more thing which we felt was whenever we design RS structure, again and again, I need to change the control panel. The control panel was always a problematic. We were using an Arduino Omega and we were not sufficient pins were not there, ADC was not there. So we came up with our own RS controller, two controllers, one bit on universal. We can have a lot of whatever voltages you want. So we have two antennas which we are right now able to sell it out if you want to academia or industry, and a couple of RS controllers so that you design your RS structure, the front end. And one more problem was when you do yourself integrated, you go to 4 layers, the PCB manufacturing becomes complicated and things like that. In this case, you make the 2-layer RF board of yourself and then come and connect it to our RIS controller, which is a separate PCB altogether, which will take care of your own thing. So works. And we took the code, the code which you have for the TSDSI standard. It's hardly small code, piece of code, which you could put into a Arduino based microcontroller inside the board. It's available and we can share those also. So the problem is, again, I'm telling you, the research should focus on, I understand 6G, we want to play something new toy, but existing toy we can't disrupt. So we need to see how to enhance coverage with the existing 2G, 3G, 4G bands. That is the band 30, band 3, band 40 systems, sub 3 gigahertz, okay, sub 3, not 3.3, sub 3 with the big structures, how to do. So please help me out. If anybody is interested to talk to me about this or as system as a whole in general, please reach out to me. And if somebody has defeated copper by making the angle of incidence, angle of reflection, please reach out to me. I want to see how you're able to defeat copper in RIS. Any lab, I don't mind. You show to me that, okay, with this much structure, I could defeat copper, plain copper or aluminum for that cut. So please reach out, okay? So there are enough opportunities. I know there's enough opportunities, but we are still scratching the surface. So I feel we have to be a little bit optimistic and pessimistic at the same time, to play the devil's advocate ourselves, because when we get overexcited about near field issues, which we also faced, how test everything works very magically near field. So this much everything works. But when you put across the building, it doesn't work for us. It does not work because again, the signal receiving the RIS itself is in the almost dead, minus 80 dBm. And when you reflect that, even if it's 2 dB, 3 dB, 5 dB gain, doesn't help. It goes further. It dies out very fast. So please, somebody does a good lab, outdoor, FR1, and defeats copper, please invite me. I'd like to see the lab setup. Thank you. Thank you. Any questions?
Any questions?
Okay. Thank you.
Okay, thanks, Anand. Okay, so we'll move to the second speaker from Debarati in IIT Kharagpur. She's online? Okay.
Hello, am I audible?
Yeah, you are audible actually.
Can you see my screen?
Yeah, you can start, Debarati.
Okay. Today I will be talking about some spectral efficiency optimization that we have done using the EIMM based techniques with the IIS assisted next generation communication systems. Myself with my team. So basically, we targeted
One
what?
second, Devrati, just a sec to pause you. Professor Uday, after Devrati, you can speak actually, okay? Okay, yeah, continue. Sorry, Devrati, you can start, continue.
Okay. Okay. So what we targeted is to go ahead with enhancing the spectral efficiency, because we understood actually the standard optimization algorithms, whatever we tried for this IRS assisted millimeter wave communication system designs, they were actually becoming heavy complexity wise, heavily very heavy with the complexity wise, and these optimization algorithms, once somebody will try to run on the practical systems, it will not be actually practical in sense to go ahead with. So we looked into actually the what will be the channel estimation complexity, and once we integrate the channel state information, once we are doing the beamforming web vector estimations and the gain vector estimations for IRS. So how this complete work, including the channel availing channel state estimation and providing the beamforming gain vectors, will be jointly addressed for enhancing the spectral efficiency for this case. What we understood then actually that we can decouple the channel state estimation part by using some kind of the sparse Bayesian learning based algorithms or any other the sparse learning based algorithms, so that actually the initial values of the state channel state estimations can be get, and then go ahead with the application of AIML for the estimation of your gain vectors for the IRS, so that you can get the beamforming vectors very easily. And definitely, actually, if there is a movement or there is a mobility incorporated in the whole system model, then your channel state information update will be also an additional task coming into the picture, so that you can keep on updating also your beamforming vector based on the instantaneous location of the object or the user, mobile user. So joint optimization of this IRS phase shift vectors and doing the beamforming that we found, it is a non-convex and computationally very intensive. So we have applied here the AIML based approach. To give you a brief about the system model, so we understand that there are the very big IRS structure for helping us to direct our beams to our UV, and UV is reachable within the range of this IRS is a basic assumption of ours. Though we have shown here that there is a BS to UV channel, but practically even if it is getting blocked, whether we can establish the communication link was also a question in our head. We consider that there is a MIMO system comprising NTA base station antennas as well as NR antenna systems using your inside your EV. The IRS, which is actually was there in our hand, we wanted to utilize it, the elements in a very crucial fashion. For example, is there any, we ask ourselves, is there any need to turn on all the elements of this reflecting elements of this structure of IRS at a time, full time, will all of them will be on? Can we do something by grouping themselves depending upon the location of the user ends? Can we group them out in such a fashion that partially we will be turning them on based on the requirement, and we can still get the sufficient amount of the dB values in terms of SINR, so that my spectral efficiency is enhanced and it is sufficient to meet up my data rate requirement of the user end? So apart from this controller feedback link, whatever was traditionally there, we mainly tried to find out what are the number of the elements optimally should be turned on when the UV is moving away from the base station or away from the IRS or towards the base station and towards the IRS in a dynamic environment. How will you choose the number of the elements out of the whole structure and still you can maintain the quality of service? In order to do this whole part, this whole problem statement, we have introduced this AIML for doing so. So we can think that it is a hybrid approach where we have utilized the sparse channel estimation along with the deep neural network. And for the sparse nature of the millimeter wave channel, as we targeted beyond sub 6 gigahertz, So for this 7 to 14 millimeter wave channel, will be having the sparse channel estimation techniques, and through our different algorithm proposals, we found that sparse Bayesian learning can be actually be used efficiently for getting the channel state information. That information will be fed back to the DNN structure for predicting the IRS phase. And once actually this continuous channel state information will be getting updated by the estimators. So definitely the DNN structure should be giving the and predict the newer IRS phases depending upon the location of the current location of the UV. So this graphs we found actually when we were trying to compare the different sparse estimation techniques when the movement was going on, the UV was moving, and we found actually we were targeting to find out the very complexity efficient algorithms for the estimation, because we understood that it will be as a whole joint estimation plus the phase estimation techniques will be jointly maybe very huge, complexity wise very huge. We try to keep the channel estimation as simple as possible, but also efficient to enhance our spectral efficiency. After comparing the different algorithms available in the literature and also our own proposed algorithms, we understood that the SBLs, the sparse Bayesian learning algorithms, were giving the least NMSE and also complexity was not so high that you will be getting jumbled up while you will integrate it with the DNN based phase estimation algorithms. So what we did actually is that to maximize this spectral efficiency problem with the estimated CSI, we frame our own optimization problem to maximize the capacity. To maximize the spectral efficiency means you are definitely going to enhance the capacity, and such that we understood that one particular user should be connected with at least one group of the elements. So it will not be simultaneously connected with two group of the elements. What I mean by the group of elements is, suppose you have a 128 cross 128 structure. If I frame a group of 4 cross 4, so multiple such groups will be there within this 128 cross 128 structure. So at a time as a user, depending upon your location, you will be connected with any one of these groups of the structure. I will connect you with a particular group of this within this bigger architecture. You will be connected to a particular group in such a way that your individual capacity or spectral efficiency is maximized. So that was the target, and it was actually also the WebDM in the picture. So we tried to calculate the gain, channel gain for a subcarrier based, and this whole problem actually was a non-convex one and could not be solved directly. We tried to utilize our SDR techniques, the semi-definite relaxation technique also to relax this problem into a convex problem, because as it was a non-convex one. And then we have tried to solve it through a solver and then integrated it with a deep neural network. To give you the brief over the block diagrams, so you are getting the received signal, you are doing the CSI estimate by the SBL, and then the feedback is coming directly disconnected to the deep neural network. We structured it with the input layer of the 16 neurons with the 3 hidden layers, and there was another output layer of the 8 neurons. So that whole part actually gave us a whole optimum IRS phase matrix that actually we have checked with respect to the spectral efficiency maximization. I'm not going into the detail of the algorithm that we have designed here, and also we have some publications if anybody is interested, they may go into the details of it, how actually we have relaxed the non-convex to the convex problem and how we have integrated, how we have trained the neural network that I will be briefing up with more. The adjustment of the hyperparameters, for example, the number of the neurons as well as the layers, the learning rates, all are actually very well defined in the publications. And optimization of the whole structure, the deep neural network structure is also in detail explained there. This is and basic complexity analysis. Here also we will be able to show you that though the DNN alone is a very complex one, but because of the optimization that is plugged into it, we have actually successfully could be minimize the complexity of the whole algorithm, including the joint estimation as well as a phase estimation, channel estimation as well as a phase estimation within the fourth order polynomial. These are the sum of the simulation parameters. So as I said, initially we tried with the 7 gigahertz to 14 gigahertz, and also actually we have put it up to the 30 gigahertz structure. So 24 to 30 gigahertz frequency range also the proposal was tested. Here particularly I am going to show you the all the detailed simulation results related to the 30 gigahertz. We considered the 64 process 64 cells, and there were the transmit as well as the receive antennas, which are the MIMO structure is a 4 cross 4. We have the groups of if you make it actually the 8 cross 8, so it will be having 8 number of the groups as a whole, and we have the 8 number of the subcarriers and 8 pilot tones, and the distance that we varied between the base station and the IRS, we kept it within the 50 meter. We varied it also up to 150 meters, 100 and 150 meters. And there are actually the non-ideality factors, where actually we are considering that there are a lot of the non-linearity related issues will be coming into picture because of the very high frequency that we are using, and the nonlinearities will be coming from the mainly RF sections. So that factor also we have introduced and considered in the whole simulation. This is the interesting part to show that the y-axis, if it is a spectral efficiency in bits per second per hours, we are plotting. And suppose the user is moving uh, away from the base station. So when I'm telling it is 0, so user is very close to the base station and it is moving away from the base station. It is in terms of the meter, it is increasing. Your IRS is standing away at 50 meter away from the base station. So if there is no IRS in the whole system, so spectral efficiency is expected to fall following this blue line as you are going away from the base station. Because of your frequency is 30 gigahertz, this graph will be also shown if you are in a 7 to 14 gigahertz. If you are away from the base station, expected that your spectral efficiency is going to be low because of the huge loss, that path loss, absorption loss that is happening in the channel. But once you are having actually the IRS and you have a least square based channel estimation, and there is a traditional, semi-definite relaxation based programming you are doing, following the standard optimization techniques. So this is the spectral efficiency, the green curve will be showing you. You cannot go beyond actually 1.2 bits per second per hours. But once you are having actually the sparse Bayesian learning estimation and DNN best expectation, phase estimation techniques in your hand. So the spectral efficiency can go beyond 2 bits per second per hertz. So it's a huge actually, and if you are having a wider bandwidth, so now you can multiply with the bandwidth and you can see actually the huge spectral efficiency enhancement that is possible because of this algos. If there is a grouping ratio also, we varied actually the grouping ratio. The terms grouping ratio is saying that how will you choose the group of the antenna elements. So if actually there are 8 number of the antenna elements out of the 64, so it is 1 by 8 is your grouping ratio. If it is you are choosing all the antenna elements at a time for your transmission, then your grouping ratio is going to be 1. And so you can vary actually the number of elements dynamically depending upon the user locations. So spectral efficiency is expected to vary and reach to a maximum depending upon the grouping ratio that you are having. If you are varying also the distance. So the lower graph is you are away from the base, suppose 90 meter, followed by the different ones are like 30 meters, 60 meters, 70 meters, like that you are varying. And once you are actually just exactly 50 meters, these are very close to the IRS. So definitely actually your spectral efficiency with respect to the grouping ratio also is expected to vary not much as compared to the others that are varying. So as a summary, definitely actually all the elements actually not required to be turned on at a time. They can be dynamically selected Depending upon your location and depending upon your requirement of the spectral efficiency, I can keep on choosing and dynamically varying the groups of the, create the groups of the elements for your application. And this is actually the deep neural networks efficiency we have shown here. So whatever was actual data rate and what is actually your predicted rate by the DNN, that we have tried to show here when the testing was going on. And this is the convergence plot with respect to the epoch when the deep neural network was getting trained with respect to the validation loss and the validation data. We see that the MSE plots are coming very close within 30 to beyond 30. Actually, they are almost converging. So within 30 epochs, very fast you can converge. The architecture what we have optimized, that is actually very easily practically implementable. So that's all the conclusion, that the use of the ML models can help you to reduce the computational complexity hugely. Whenever in a dynamic environment, you wish to choose dynamically the number of the elements. When your user is mobile and your channel state information is continuously varying, the IRS can play actually very important role for the range extension as well as actually increase spectral efficiency compared to the traditional today's communication systems outside. But its efficient use and dynamic use is required to be done. That is the message from our end. And IRS actually is a very promising one for the next generation communication system when it is clubbed with the AI models going to be. These are some of the publications and the patents that we are having. Few are actually already under the review stage. That's why we have not shown. Thank you. Any question?
Yeah, I think Professor Devarati will take the questions after end of this session, actually. Okay.
Okay,
Okay.
fine.
Thank you,
So,
Professor Devarati.
any query is there? Please request them to send me through my email.
Yeah, 1 second, Professor Uday. Just we'll just call you on things. Just give me 2 minutes. Okay. So.
So I have stopped my screen sharing. Is it fine?
Yeah, that is fine.
Thank you.
Okay. Okay, Professor Uday, over to you actually. You're audible?
Am I
Can you just
audible?
speak? Yeah, now you're audible. Yeah, thanks.
Okay, let me just let me know if it is visible in full screen mode now. Are my slides visible in full screen? Yeah, okay. All right,
Yeah, we are
good
putting it
afternoon
up.
and
Just a second.
say again. Should I go ahead?
Yeah, you can start off, Professor Uday.
Okay. Well, thanks for the invitation, and I'm sorry I couldn't attend in person. Seems like a very, very interesting and relevant session right now. So I'll talk about the work that we have done at IIT Madras and also in collaboration with our partners in Samir, Kolkata. So I'm partly also presenting on behalf of Dr. P.H. Rao. So I want to start by acknowledging our funders. So we have IRS funded research from METI for the collaboration, and I have funding from Qualcomm as well for this work. So the scope of the work, that there are two scopes of work that I want to talk about, which I hope will be interesting to everyone in the audience. One is something which I think everyone who builds an IRS needs, which is beamforming algorithm. As we saw in the previous talk, they approached it from an information capacity point of view. We approach it from a more physics-based approach of beamforming. So in a recent paper, we showed that you could do beam forming in an optimal way in an extremely fast linear complexity algorithm. So you don't need semi-definite relaxation, genetic algorithms, etc. And this was an open problem until we solved it last year using a surprisingly simple algorithm. It's very general purpose. It works for multiple states. So your IRS could be 1 bit, 2 bit, anything. It also supports non-ideal weights. So let's say that you fabricated your structure and it's not amplitude is not 1, it's 0.8, and the phase difference is not 180, it's 160. What do you do? Well, the algorithm still works. We also show how you can incorporate what is called pre-phasing, and I will talk about this a little bit later, and how you can do multiple beams with a single code book. So this is not TDD. This is at a given time, the surface will produce multiple beams. So this is one of the solutions by which multiple UVs can be serviced. So I will talk about these in a little bit more detail. So the key idea behind beamforming is that we see in the literature is that you take the continuous variable solution and then you threshold it. So here is a simple 3 by 3 IRS. You give it some sample incident angle and an output angle, and then you look at the continuous variable solution, and then you just threshold it. If it has a positive phase, you say, okay, weight should be 1. If it has a negative phase, you say that the weight should be -1. Most algorithms work like this, but turns out that this is not the best way of doing it, and that's what we show in our work. If you notice, what has happened over here is that we have partitioned the weights into the left and right, but there are more than one partitions. And so it turns out that if you find the right partition, you can increase the gain by even a dB or more. And so finding the right partition gives the optimal solution, and this is the idea which allows us to even work with non-ideal weights, multiple bit solutions, and so on. So the next problem that we can easily solve with our algorithm is that of grating lobes, and I think this is familiar to everyone. That if you take a 1-bit IRS, it could be with pin diodes, varactor diodes, whatever, RF switches. If you illuminate the IRS with normal incidence, you can see you have these two symmetric lobes that come. So if you wanted to send it to 45 degrees, you're sending half the power to -45 degrees as well. So this is actually happening mathematically due to a symmetry in the gain function. The expressions for gain are identical at theta and minus theta with normal incidence. So the idea then is to break this symmetry, and you pre-phase the cells. So you could say that some of the cells are going to be phased ±1, whereas some others are going to be phased ±j. So they're 90 degrees apart. So that breaks the symmetry. It's still a 1-bit control, so it's not you have not gone to 2-bit, except it's just that there is a pre-phasing of some of the cells, and you can see that the grating lobe that was appearing at 45 degrees is completely gone, and you're back to a single beam. So this is one of the advantages of using the partitioning algorithm that we have proposed. What else could you do with it? You could once you have a single beam that is propagating, you could scan it across space. So these are the simulation results, which shows you you fix your incidence angle, and then by changing the code book, you could sweep across the IRS. Across the reflected angle. As I mentioned, the complexity of this algorithms is order n. So in theory, you could even implement it in real time on hardware. You don't need to do any complicated convex relaxation or genetic algorithms. And the code is available. If you look at our paper, it's half an hour for a student to just convert it to MATLAB, or we could also provide it to you. We could also do multiple beams using a single bit IRS. So this is interesting. It shows you 3 beams that we wanted to synthesize. You can synthesize multiple beams in a nice way only if you have a large IRS. So only at, let's say, 30 by 30 does it make sense to try to do multiple beams. So it is possible with the algorithm, but you need to give it a big enough IRS for it to make sense, which brings me to the next topic, which is how else could you use this algorithm? And a common item of discussion in all of these forums is what is the optimal size of the IRS, right? So this work helps us to answer that question. So one is, for example, what is the beam forming error as I increase the number of bits of the IRS, or as I increase the size of the IRS? So it turns out, as you can see from here, as you can invest by going into multiple bits, which is increasing your hardware complexity significantly. Or if you want to stick with a 1-bit, what you need to do is go to a larger IRS. So no surprises here. We intuitively expected that, except that this work helps you to get specific numbers out of it. And what I mean by beam forming error is that, let's say I wanted to beam form to a certain angle. What is when I implement the weights, how far away is the actual beam? So that is the beam forming error. This is about size. The next thing is how about the beam width? How thick or thin is the beam? And what is the kind of gain that I get? So gain over here, I mean, is simply the array factor expression. So you can see that as I make my IRS bigger and bigger, my beam width becomes narrower. So all the way from 16 degrees, I can get it down to 3 degrees by increasing the size of the IRS. And obviously that means that I'm making the aperture size bigger. So therefore, I'm going to get more gain. So no surprises here as well. So this, I'll move on to the work that we have done with Samir Kolkata. So this is Amitesh, Dhruva, Satyajit, and Dr. P.H. Rao with myself. We've built a 7 gigahertz IRS very recently. It's Varactor based, so although it's expensive, the power consumption is extremely low, and it has a very unique unit cell design where, as I'll show on the next slide, it has an air gap, and by varying that air gap, you can change the bandwidth from 1 to 4 gigahertz. They incorporated our idea of pre-phasing to eliminate the grating lobes, and beam steering has been shown very nicely from minus 50 to 50 in an anechoic chamber. So what the cell design looks like is, this is kind of the pattern that you have, 4 leaves with a central area. And it's a very clever engineering solution to have this air gap maintained reliably. I think the size is 20 by 12 is what has been built. And so this is an example, this is to show you how the pre-phasing has been done. So we all know in a varactor that you could get a very large number of states, but I want to use only a 1-bit controller. So what is happening over here is that you give a slightly different voltage to the pre-phased guys as compared to the regular guys. So you could get this, some of the cells will have 0 180 and some of the cells will have 90 to 70. And so throughout the beam forming algorithm, each cell has only 2 values to choose from, either 0 180 or 90 to 70. So that's why I can get by using just a 1-bit controller, because if you just saw this table, you would think I'm doing 2 bits, but it's actually just a 1-bit. So that means significant simplification in the control circuitry. Okay, so just a snapshot of the hardware. This is the IRS being tested in the anechoic chamber at Samir Kolkata, and we were able to show beam steering. Incidence angle was minus 50, and at 7.3 gigahertz, you can sweep from minus 40 to 50 degrees. Fairly good coverage, and the side lobe levels are not killing you. And I think that should, this is the last slide that I have to talk about what is the ongoing work. I also have a collaboration currently with Professor Devidas, who will talk later in the afternoon. We're trying to build in more advanced functionality over here. We want to make sure that it works just as well at multiple incidence angles, multiple polarizations, so that it becomes more realistic towards wireless solutions. Some of the important things that I spent some time thinking about, and I think is relevant to this forum, is a lot of the designs that we see are based on simply the unit cell performance. But if you look at a finite IRS, its performance is actually different from a unit cell based one. And quantifying this is important, and getting an algorithm that designs directly the finite size is also a very important problem. It's a very difficult problem because the compute times really become very large. So that's why it's an important research problem. Sensing is another issue, right? We've seen some of the earlier talks talk about different versions of or types of IRS. So should you co-locate a DOA on the IRS and make it more autonomous or less autonomous? It's a controversial issue. And of course, operator consensus. If my IRS is adversely affecting another carrier, then how does that inform the design of my IRS, right? So these are, I think, 3 very important questions that we need to answer, discuss in the coming year or so. So with that, I thank you for your attention. My email address is here in case you want to reach out to me. The PDFs of the papers that I've spoken about are also on the website, on my website, so you can download and read them. So I'll end here. If there are any questions, I'm happy to take them.
Any quick questions or? Okay, so we'll move to Mr. Vinod actually from RNS.
So, very good evening from my side. Uh, Myself, Vinod, I take care of applications in Rodin Schwartz. I've been 12 years working in the company as an senior lead engineer, especially for signal generators, spectrum analyzers. So today we'll also see about in the T&M perspective, what will be the RIS, what are the solutions we have for this ecosystem. So all these things I will like to present. Before that, I would also like to introduce who we are. And I would like to show a small video for this. Maybe quite a few people aware of Rodin Schwartz, but for quite some people who are new. So the Rodin Schwartz was invented in 1933 by two professors, Dr. Lothar Rode and Hermann Schwartz in Germany, Munich. And from then now it's almost we have like 14,000 employees working around the worldwide in 60 countries as a subsidiary, and we have a presence in almost 70 countries worldwide. So we have a moreover 3 billion of turnover last year we have made. So this is some of the quick timeline about what we are having as in product solutions. So where like I'm from the test and measurement division, and we also have a technology division where we support mostly for the defense segment for the military and the aerospace, all these applications. And we also have one more vertical of business where the land comes switches. So this is also we will support for cyber security solutions as well. Then we have our major products starting from the VNE. This was our first solution. From then we now move to signal and spectrum analyzer, and the latest we have a product, we call it as an QPS walk, which will be like already installed in Delhi airport. So there's a security scanner for millimeter wave applications. So that sooner we will also see that in the Bangalore as well, airport as well. Yeah. Just move to the next slide. Coming to the academy and the research areas. So we seen some of the quite a topics where we see these are the interest wherein the 6G will come into existence. So one is that FR3, the terahertz communication, the millimeter wave, and then we also have this RIS, the reconfiguration intelligent surfaces, and photonics as well. So some of we have also seen this augmented reality with the metaverse. We already collaborated on these topics as well. So moving to RIS. So basically this is we have already had a lot of sessions from the peer team here. So the RIS is nothing but a reconfigurable material where we want to have the phase attenuation, even the amplitude parameters has to be varied. Even I want to change my polarizations, all these things to be varied. So why we have to do this? We want to achieve a solution where I want to reach out to an even to a dead region of the UE, where I want to be able to reach it. So that's where my refraction and all the parameters has to be reconfigured. So coming to the one new solution where R&S is partnered, this is 6G LIC RIS. So this is a project where Rodin Schwartz and some of the education institution we are partnering with this for developing a new surface material which can be used used for your RIS purposes. So where this will be especially like I can talk about, for example, in future we can also have a billboard which will be acting as your reconfigurable antenna surfaces also. That's a kind of an application where we can use it. So why this RISS is required? This is very much required to increase the coverage and as well as the efficient like power spectral efficiency and as well as the battery efficiencies, all these things to be increased. So what are the test requirements in the RIS basically? So basically I want to measure, okay, what is my 3D reflection pattern. So as earlier some of the industrial colleagues who has discussed, so they have done their own setup to measure the 3D pattern of the solutions. But now what we have is, like, for example, if you want to change the impinge angle of this um, or a surface, so then we do have a turntable where I can able to efficiently define, okay, what will be the turning angle I would like to position my RIS system, and I want to measure this. So for those kind of things we can also do it as an like 3D pattern diagram, as an 3D hologram also we can able to get it. Then we have a like the speed of reconfiguration. So this is especially when it is comes to, okay, how fast I can able to reconfigure my antenna so that I could able to do a better spectral efficiencies. So all these measurements also we can able to perform with our solutions. Then coming to the quality of your transmission, the EVM measurements and all these things, where the signal generator and spectrum analyzers, so those things also will play a major role. Not but not least the channel sounding. So basically I want to also understand, okay, how good the spectral efficiency in the over the air. So I want to also measure the channel sounding measurements over here. So this is prototype RIS where Rohde & Schwarz partnered with Greenwave, so Greener Wave. So with that, we had an 29 gigahertz RIS plate surface. This was the first surface where we have tested for these applications. So where we have this feed antenna, which is also transmitting an FR2 5G, and with that we will be able to measure what is the impinge angle. So you can see now there is an angle of impinge rotation is also happening here. So we not only this, we also have partnered with multiple other industries, and we also collaborated with German education institutions. So this is the press release which I have discussed about the greener wave and Rohde & Schwarz, where the same solution whatever I have shown as a video that is being released from Rohde & Schwarz as well. So what do our portfolio consist of? So this is basically the signal generators, and we also have a compact a vertical chamber to do like you can have an efficiently reproduce the exact what we have shown in the demo. The same way you can also have an a millimeter wave chamber which is portable, and the idea of this chamber, we also have an 1800 m which is an slightly an expandable chamber, so as and when required you can also increase the requirement of this. And we also have a WPTC, so this is an one more over the air chamber where we can able to perform for an wider, like for example if I want to have an in this room itself I want to have my chamber fixed, so we can also have those chamber installed here based on your frequency range requirements and everything. So then we have this CMX 500, the call box tester. Most of you will be known this. This is now also we are enhancing the feature for FR2 and as well as for the 6G in future. And we have this signal generator and spectrum analyzers and network analyzers. As definitely I want to measure the 3D pattern measurement, then I need a network analyzer to measure my reflections and antenna radiation pattern, all those things. So coming to this, we already, as I mentioned, we have engaged a lot of research papers on the 6G LICRS, and as well as we are now a partner or a body with ETSI ISG group of RIS and as well as 3GPP to framing the specifications and all these things. And this is our complete solution what I have explained earlier. So we have this signal generator and then the turntable with an antenna chamber and the measurement solution with an FSW spectrum analyzer. So where I have used an software AMS32 to configure the elevation angle and the required impinging angle. So all these things I can able to directly able to configure here. So this is just only one probe antenna I have positioned. Suppose if I want to have a multiple angle. So for example, if I want to do a 3D assessment, then I have an four feeder feed through antennas can be positioned over here. Then I can also perform an full 360-degree measurement. So this is also possible from Rodain's website. So apart from this, we also have a certain webinars, and also there are a lot of videos which we are surfaced in our web page. If you're really interested to go through, please contact us. So myself and my colleague Mahesh Kajavi, we are always around, and you can also take our contacts and we can able to help you out. With this, I would like to thank IIT B Bangalore for this opportunity, and thanks for everyone. Any questions?
Thanks, Vinod, actually, for your presentation. Any quick questions? Okay, thank you. We'll call up on stage Dr. Ramia, actually, from CEVIT.
So good afternoon, everybody. Thanks for the opportunity, and it's a pleasure to be talking among the allied group here. So this is a consolidation of certain work done at CIVIT, and also some thought process which we collected from literature, and also during our discussions during the 3GPP meeting with fellow 3GPP folks. So the focus of my presentation would be, of course, all of you have talked a lot about risks, the advantages, and the deployment issues, concerns, etc. So this main focus would be talking briefly about the NCR, which is also like a repeater, and how is NCR different from RIS, and what are the challenges that are forthcoming in RIS that we anticipate, and what the challenges that have to be addressed so that RIS becomes part of the future standardization process. So these are some basic slides, and all of us are aware of, so I'll just skip them. So the main advantage of RIS comes from its ability to provide ubiquitous connectivity and to handle coverage holes in a very energy efficient manner, and also it's simple and cost effective. That's been talked about very widely from the morning. So of course now currently it is started with passive risk. Going ahead, we can look at amplification issues, how to perform efficient channel estimation, and to bring in AI module. So these things can be advancements to improve the performance. Even those were dealt in today's discussions. Yeah, coming to NCR, NCR is a network control repeater which was dealt in release 17 of 3GPP. So basically, we know traditional repeaters which does amplify and forward, and but then they didn't have any beam information. They just amplified the signal and just transmitted them back, which didn't go through very well in LTE times. Then during NRS 5G times, people brought in something called IAB, Integrated Access and Backhaul, which had a UE part which will connect to the main base station, and a DU part. DU part is like a miniature base station connecting to access nodes. IAB, the advantage was it was doing decode and forward, and since the DU unit is something like a base station itself, it can do good beamforming. But the architecture was quite very complicated, so they wanted something in between. A repeater which does amplify and forward, but which actually can do beamforming in the intended direction. So this can actually avoid unnecessary energy wastage, and it can, since you point to the required UE and you deal with the required beam, the throughput, the spectral efficiency improves further. So thereby they brought a network controlled repeater. So you have a repeater controlled by the base station. So it has two units, the empty unit and the forward unit. The empty unit is like a UE, which gets some control information from the base station, and the forward unit just amplifies the data and sends it to the UEs. required access UEs. So the basic information that MT gets from the base station are beam information and the time resources and on-off indication. So if you have to service a particular UE, what should be the beam that has to be used, and what are the time frequency resources in which the beam has to be used, and if required, switch off the NCR. So all these together helped in improving the spectral efficiency at the intended UE and also power consumption at the NCR node. So going further, RIS was looked like a miniature version of NCR. So RIS, so the control unit was very much simplified. I mean, the MT was much more simplified, and of course there was no considering and passive RIS. There was no amplification factor as such, but the beamforming was handled by the use of meta elements. So that's why RIS was considered as a popular alternative. So these were the advantages which were seen of RIS compared to NCR. So it can be more simple and cost effective. Like MCR is again, you need as much real estate as the required for a base station, and there's a lot of power requirements involved that is not involved in RIS, and it can be mounted in any place. Like we can go for wall mounted configurations, and it has higher configurability, and it was seen as a particular interest, especially in indoor and control scenarios, to enhance positioning accuracy, and for especially for factory scenarios where there could be lot of IoT devices involved. So these were the prime advantages of RIS compared with NCR. uh, okay, but then there are also other challenges as well. Though we say it's a very simple and cost effective implementation, how really cost effective it is, it's a real question. Like a simple 8 cross 8 RIS may not be really sufficient. For example, if we require good gain as compared to NCR, we may really need a very large surface, in which case the complexity again may improve. And since we have lot of large RIS surface, the control need to be transferred was enormous. But then I see today morning there were a lot of solutions. People were talking about lookup table based or having a quantized control, which could be potential solutions to this concern. But of course, this is a concern. When we have a large RIS, control becomes much more elaborate, and it adds to signaling complexity. And of course, since dimensions increase, how well will be the deployment and cost of deployment as such. Then translucent RIS, something which is similar to even a glass surface was talked about. But then there are some very practical limitations attached to it. For example, I mean, technology will keep evolving. After some 5 years or 10 years, we may need to change RIS, but then during that time, we may not be able to really change the glass involved with it. I mean, we can't do infrastructure modifications for RIS, so there are practical feasibility involved in it. So these are the challenges when we concerning the deployment aspects. And of course, so far RIS was seen as a viable candidate concerning FR2, but FR2 is not coming into practice. So since people are quite happy with FR1, how really required this will be is a question. But then going further in 6G, FR3 is very widely talked about, so probably there RIS may find its way. But then that requires still a lot of study. Yeah, other thing is multi-operator scenario that again people talked about quite well. Suppose an operator A installs an RIS, and if it creates an unintentional reflection or unintentional hole for an operator B, that's again a point of concern that has to be dealt with. And of course we are looking RIS from a more static or semi-static point of view. But if we have to tune the beamforming vectors to actually cater to multiple UEs, that can create frequent changes in RIS communication channel. So that can also cause an hindrance to other operators or other UEs in the scenario. So these are some other concerns. And of course, the design unit, we have to see that design of the control unit and how elaborate it is. Those things have to be currently dealt in detail. So this slide gives some of the numbers actually. So compared to NCR, we see if with an ideal RIS, NCR provides 33% rate improvement. But of course, the NCR the cost involved is sufficiently high. And another thing that was found is to really achieve as much gain as that is achieved during with NCR, RIS requires much more elements than what has been dealt with in current situations. So again, as I said, when we have more elements, issues in deployment and issues with signaling, issues with reference signal transmissions, all these come into picture. So with all this, we are yet to see. I mean, these are not like blocking factors. These are like concerns which we have to be addressed with academic area and research bodies need to address these things. And of course, the standardization impact. So when we bring in a new network entity like an RAS, what are the effective changes that need to be brought in specifications to meet out the requirements? Those things have to be effectively studied. So these are some of the challenges which we have to be answered to push in 3GPP into some standard body in an effective manner. Yeah, so finally comparing NCR and RIS. Uh, in RIS, spatial selectivity is lagging. That is what is there in NCR. And there is no spectral selectivity because RIS can actually reflect signals of all frequencies. That can become that is the thing which is creating an interoperator interferences thing, interoperator problems. Uh, yeah, of course, the large size that is required to achieve the same gain as an NCR. And in RIS, another thing is we have double path effect because we have a channel between the base station to RIS to UE. So this double path effect have to be carefully studied. And so far, many studies have considered ideal RIS and ideal channel conditions. So what happens in case of imperfections? So these are some of the concerns to be addressed to bring in RIS performance as close as to NCR and push it to some standardization bodies. Yeah, thank you.
Thank you, Dr. Ramya. Any quick questions? Okay. Thanks, Dr. Ramya. Okay, now invite Dr. Tapas from TCS to talk about his lab.
Okay, good afternoon, everybody. I am Tapas Chakravarti from TCS Research. Now, before I begin, for many of you who are not aware of TCS Research, it is an entity in itself. One can say it's pretty large, spread over multiple cities, have hundreds of scientists working on multiple different areas. We work on different aspects of life science, physical science, biological science, but at the intersection of computing. So one of the area, large area, one of the biggest group in TCS research is called Embedded Devices and Intelligent Systems, headed by Dr. Arpan Pal. And I am principal scientist and I lead the sensing and communication. Our lab is twofold. One is in Kolkata and another part is in Bangalore. My colleagues are sitting here who are part of this today's presentation. Now, since time was 10 minutes, so I will try to make it possible so that you can get a glimpse of what we are doing rather than trying to go into detailed results of it individual. Now, before I begin, just give you background. We began work on metamaterials way back, 4 years back. Our initial idea was to work on novel sensors with high sensitivity, but we quickly pivoted on to antennas because some of our groups were interested in 5G advanced and 6G, where metasurface antennas were considered to be one of the very emerging areas to look into. So we looked into lenses, we looked into transmit arrays, reflect arrays, and finally 2 years back, we said that we are formally going ahead with RIS design. So what I am going to present today is from the microwave perspective, what we have done. But apart from that, we have done also channel modeling, which was headed by Dr. Anil Kumar, who is sitting over here, but recently has moved on, but some excellent work has been done. So his team continues to do that. So how do we position from TCS research? How do we position RIS? Now, initially when I started, I positioned it as a technology for 6G also, not from the communication perspective, but it is good for me to get an approval because RIS is one of the very important technology that fulfills the SDG goals which are laid down for 6G. And it is very, very interesting. Instead of considering that RF channel to be an impaired channel, we are using that impaired channel to design a technology which will be very futuristic. But over a period of time, now we consider that RIS can be positioned in such a way that it will be positioned as to future-proof the industrial automation networks. Because whatever the benefits that RIS has, which has been discussed from the morning, is equally applicable in indoor warehouses, large factory spaces, which is this industrial environment anyway is known to degrade signal quality. There are a lot of places where the signal doesn't reach, and TCS continues to get many such requirements. Why can't we have a proprietary RIS design with RF planning as well as our own control, which connects back to a private 5G to connect the future wireless devices in a factory space? So when we started, we mapped out the patent space. We saw that there was significant white space. China was leading in the patent. So we started designing new unit cells, variants of these unit cells, and we started mapping its parameter versus performance. Means each metasurface unit cell will have its own electromagnetic performance ability, whether it is transmitting, reflecting, or polarization conversion. So there is a snapshot of multiple unit cells. There are many more. But for example, you can see on the left-hand side, there is a variant of Alford loop with a ring outside. Because many a times when you work on this transmitter array, for example, you need, for phase gradient metasurface, you need 2 pi phase variance. And you will not get it. So once is that you have to go up to 4 layers. Another one to increase the intrinsic inductance of the unit cell. And all these unit cells are sub-wavelength, around the order of 0.3 to zero point 0.4. And for example, Minkowski, different variants of Minkowski has been worked on. Now, some representative designs I am showing. I'm not going into any results. For results, you can always reach out to me and my colleague Amarta. On the left-hand side, this one, as mentioned, it is our first. See, we started with IFR2 because that is what was mentioned in Samsung's vision paper, that in the FR2 band, RIS lensing will be truly required. Because one of the issues that because interesting to say that I started Samir Kolkata Center in 1993, and it was launched as a millimeter wave technology center. So we started working beyond 24 gigahertz from the very first day. So we know that the diversity of path is much less in millimeter waves. So we started working there. So what you see is a typical partially reflecting surface placed at lambda by 2 on 4-layer patch and with its own radome designs, and it has been built in Hyderabad, and we tested it. It works beautifully. On the second one is very interesting. I don't think you have seen anything like this. This is again a standard square patch. This is IISc make. TCS gave a project to IISc Chemical Engineering Department, and this is printed on a paper, ordinary paper, inkjet printed. So, and the idea is that there is a small patch. Can we retrofit a 2-layer of papers with a gap of 3 millimeters on it to enhance the directivity, which is standard in PCB making. But the idea is that if when you inject print nanoparticles on this, it doesn't come easy. So step by step, we progressed over a year and to reach the exact simulated, when the simulated and the perform gain we matched. The right hand side is our in-house mail controller. I must say that what you see on the right this side is a 10 cross 10 RIS, Minkowski. So now we didn't start with PIN diode or switch or anything, which are easier options. But it is not that we deselected the easier options. We never knew that easier options are there. For us, phase gradient metasurface means phases has to be changed unit cell to unit cell, and that is why we chose directed diode. So this 10 cross 10 Minkowski FR1, and we started with FR2 first. We built one, didn't test it, but we actually tested this. And for this is 100 channels. So we built this in-house control, 0 to 20 volts control. One of the issues that I think you pointed out, that why it is so difficult to control, because even 0.01 puff change, the voltage change plus minus 10 millivolt can change the capacitance by 0.01 puff, which takes the beam to a completely different directions. So that kind of control is required. And this is just a addition to that, a 4-port antenna array built in Hyderabad. And this is the 4 tiles of RIS and 28 gigahertz. This is 6 by 4. We built in tiles because we were looking at multi-beam operations. Now we realized that a single tile cannot give it. So we thought that we will, anyway, that RIS has to be large in shape for it to work properly. So we thought that we will make one and we cascade it. Each tile will have a separate control. But eventually, these four element became so small, this small, that it's very difficult to test it unless you bring the transmitting antenna very close. So we are still working on this, and the diodes over here is very, very costly. This is millimeter. Now coming back to the RIS setup, this is our Kolkata lab. We have moved into IIT Kharagpur Research Park, and we have got a very large space for our sensing. So what you see, there's 2 Minkowski control RIS tiles. There are 4 of them. We used to, and backed by what many of the people are doing over here, backed by pyramidal forms to obstruct the reflections from the walls. And instead of using a horn, we used our own Vivaldi. Because if we put a large C-band horn, there is no space to keep it in far field. So we thought that we will keep a transmitting Vivaldi over here at a slight angle to this, all of this content. And the receiving antenna, which is held by hand, is behind this wall. And we ensured that with the initial testing, there is a foam in between, and tested by VNA that there is no mutual coupling between. Antenna is going through this. There are control panels. How does the control voltages are taken? There is a software we have built in which all these 100 voltages are given. So there is a MATLAB program which converts that this capacitance to voltage, and from there it is a lookup table. There is no automated control so far. Now this is done very recently. This schematic was originally designed by Dr. Anil. His team from Bangalore came, and his OFDM QPSK using this USRP, I think many of you are using. So 3 megahertz bandwidth was our first attempt. This is our first attempt, original image. And initially we gave 2 antennas straight, so line of sight, though this distance is not same as the reflecting path. We tried to adjust the transmit and receive sensitivity powers to get the initial filling. Then what we did, we kept the RIS on. When we say RIS off, basically with the varactor diode, it means that it is sending the reflection to some angle, not the same angle. So to stop that, we blocked it and then switched on the RIS. So here you have the original image. Here is the direct receive. There is an error. This is the decoder errors. We are still working on it. And when this RIS is off, means what is RIS off? RIS has been kept all 0. That means it is at the highest capacitance voltage. So it is reflecting at certain angle, but there is a foam, pyramidal foam covering the RIS. So this is what is, and when the RIS is switched on, you get. This is noisy primarily because one reason could be the signal to noise ratio has not been properly mapped. The second reason is that in the constellation there is a phase instability still. So we have not fully worked on that thing, because we worked primarily on this from the microwave point of view to see whether an image can be transmitted or not. Through VNA we can see that there is a gain, but does it convert into image? Now we are moving from 3 megahertz to 10 megahertz to see what better performance we can get. So I think with this, this some of our patent list and publications mostly in MapCon. So, but after these measurements and other things, we hope to come out with some of good publications. So far we have not. And thank you for to this workshop. This is the first time we are coming out with our detailed work, though it is not means there are a lot of results that are yet to be given. You can always come back, but I don't think we have ever presented these 4 years of work in so far to any forum. Thank you again.
Yeah, thank you, Dr. Tapas. Any quick questions? Okay, thank you, Doctor. Okay, let me invite Adesh actually.
Okay, thank you. Last presentation. Good evening, everyone. No energy. Good evening. Sorry. Last presentation. Okay. Good evening. My name is Adesh Kumar Jain. I work as an industry solutions expert from KeySight Technologies. First of all, thank you IIITB and TSDSI for giving this opportunity. So we got lot of information today, the whole day, with different kind of experiments. What is RIS? What are the different measurements, different numbers? So I hope most of you know what is KeySight Technologies. If not KeySight Technologies, we are a test and measurement company. We have solutions starting from design software to R&D test setup, manufacturing test setup, or deployment test setups. We have test and measurement setups starting from design to manufacturing and deployment. I'll not go into the depth of all the instruments. I would like to concentrate more on the topic today, and I'll keep it short and sweet. We can discuss further offline if any particular questions. I'm not going into these details about what is RIS, what are the different types of RIS, what are the different applications. I'm not going into the details of that. What we are doing as an industry, you have seen this particular ETSI publication number. So we are part of this. Basically, we are driving this. KeySight is a reporter for this particular work group. So we are working with different players in the industry to define what is the standard required, how the data sheet should be defined, what are the parameters. Some of the parameters that is work in progress is what you can see here. So what is the frequency range, bandwidth, many of the numbers I saw in the lab also today. So similar numbers are being worked on. What is important so that it is standardized and everyone can start using the same set of parameters. So frequency range, radar cross section, total reflected power, what is the power consumption for seeing the energy saving, what is the time required for reconfiguration. These are different types of parameters that are being standardized for finally standardizing the design and test of for RIS. Uh, so if I come to test and measurement setup, okay, so if I talk about any of these parameters, what is the basic instrument that is required? We all know the first thing that comes into mind is a vector network analyzer, right? A vector network analyzer is used where a CW signal is impinged, and at different angles we measure what is the power that is reflected, to understand what is the behavior of what is the RIS at different whatever the configurations you do. So that is the basic first step what we expect as test setup for testing RIS. But today in multiple scenarios, what I observed is we were talking mostly about testing in near field, because far field comes with challenges. Now, so as a part of the ETSI standard, so what we are trying to discuss and finalize on is what are the different types of measurement setup that would be possible, and what each of them has their own pros and cons, and what should be finally used. Steps that are shown here to show the to use the RIS measurement. Again, I'm not talking about anything fancy here. We all know antenna measurements. We know how do we do the radar cross section measurements. It is something very simple, very similar, sorry. So what do I mean by that? The first diagram what you are seeing is what we all have been doing, which is kind of direct far field or a near field kind of a setup, where two antenna is used to with a vector network analyzer to do the measurement. But we also recommend to use multi-port setup. Why? Because you want to see multiple polarizations also on multiple angles, so that you can reduce the measurement time, correct? So what is the next two setups? Next two setups are a a step further from this. One is called as 2D scan. What is 2D scan? We are not only doing the direct far field, but we are trying to use a KTAR kind of a setup, okay, for doing a far field measurement also. What you see here is there is uh, basically you can see the reflector here, okay, the feed is here, the RIS material would be, or the basically the DOT whatever we want to mount, it will be mounted here. These are the two angles there, where there are the feed antenna, and this is the reflector. So basically this will convert your signal impinged or whatever you are measuring into a planar wave, so that you will be able to do the measurement at a 2D angle. Basically we are doing only in one angle, we are not using the azimuth, or we are not changing the distance. So a compromise between what we are talking in the first setup and the last setup. When we talk about the last setup, it is the full-fledged where I can do both near field and far field with KTAR, with all the movements, with both azimuth and elevation angle movements of the RIS, to capture the complete behavior of the RIS material. Okay, so these are different types of setups that are possible. So this is one of the measurement example what you can see here. This we did with if I'm right, it is not shown here. This is done with one of the universities. You can see how the measurement was done. This was at sub 6 gigahertz. So similar measurement results you have seen at different configurations. We achieved different angles that was very much in match with whatever is the simulation. Okay, this is something that is done this is a kind of DFF measurement, what basically the first kind of setup where we have done this measurement. Okay, going ahead, this is one of the experiment what we showed in previous MWC. So one measurement what we are talking is, okay, at what angle we are getting the maximum reflection, or where we are getting the transmission. But since this has to be finally deployed, it does not end there. You have to see what is the how the quality of the quality of the signal is getting affected by your RIS material itself. What is the basic parameters what we want to measure here? We want to measure EVM, and the other thing is ACPR, how EVM and ACPR is affected by the RIS material. Okay, now what is the basic setup that is again required here? It would be a spectrum analyzer and a signal generator, which is capable of generating the 5G signals, whatever you want to capture and do the measurement with such wide bandwidths. But additionally, what I want to also bring your all your notice into is, we have a setup where a vector network analyzer in the combination is with a vector signal generator can do EVM and ACPR. Why this is important? This is important because you have to do calibrated measurements. Okay, it is not just connecting a spectrum analyzer, signal analyzer to do the spectrum analyzer and signal generator to do these measurements, but you should be able to do your the RCS measurements, whatever we have been discussing about. Apart from that, you should be able to do the measurement of the quality of the signal also, including EVM and ACPR. So a single setup, a single connection can do both your RCS measurement and EVM and ACPR measurements with calibration till the end of the antenna ports, or basically covering the complete till the DOT port. So calibrated measurement setup can be achieved for your complete characterization, including your RIS functionality and the EVM and ACPR, analyzing the modulation quality of the RIS itself. it does not end here. Okay, so we are talking about understanding the risk behavior, then seeing what is the EVM ACPR, how does it affect. So when it goes to actual deployment, okay, you should be able to see at in the real world how does this behave. Okay, this is one of the campaign what we are doing in Malaga, Spain. Okay, what we are trying to show here is uh, uh, this is basically you can see a live G node B, FR2 G node B setup here. This is the RIS material, and this is the pathway where there is actually no coverage, no direct coverage from this G node B. So because this is facing in this direction, this RIS material is reflecting the signal into here, and we have a kind of a real UV, basically a drive test tool kind of a setup where we have a real UV along with our software to capture the KPIs like RSRP, SINR, throughput, everything can be captured. So in this campaign, we can understand, okay, at what position the RIS has to be, okay, and with what angle, with what kind of configuration, what is the kind of KPIs I can achieve in such a real world location. So we are able to understand the behavior of RIS as per different configuration, then measure EVM ACPR, and in real world we should be able to measure the actual KPIs how a UV actually sees. Okay, so how many campaigns can I do in with such a setup? Okay, for every city, for everything, I cannot keep doing this. So what is the next solution to do that? So we need to have a digital twin, correct? A digital twin which can emulate a RIS also as an additional node apart from a G node B and UV can enable you to do such analysis. A combination of a real world measurement and a measurement in a digital twin can give you a lot of idea of how the actual behavior would be of the risk you are trying to develop or you are experimenting on, how the use case would be. So I have a very interesting video which we showed in our last in this MWC. This is a digital twin. We are using a ray tracing algorithm here. Okay, you can see there is a RIS. There is a RIS. Okay, there is. Okay, the RIS is here. The UV is moving. The G node B is here. So till here you can see the G node B is directly connecting to the UV. When it goes behind the building, there is no direct connection of the G node B with the UV, and it is communicating with the RIS now. So it is using the RIS here to get the signal. So this is a digital twin. This is actually again our office in Malaga that is being we have gotten into the digital world. Basically a digital twin is created. A G node B is here, a UV is moving, and we are able to see how the RIS is helping to increase the coverage in such a location. Okay, so as a test and measurement vendor, we are trying to help you in developing or achieving a final target of having a commercialized RIS with all the experiments you are doing. So it starts with a basic measurement of a vector network analyzer, understanding how the risk configuration is as per your as per your interest, and then measure EVM ACPR, then go into the real world, then get that real world condition into digital twin, so that you can do more campaigns than what you can do in real world. So with this, I want to end my presentation. So we have a lot of offering. We have signal generators, analyzers with 5G generation analysis capability. We have vector network analyzer. The combination of a vector network analyzer plus a signal generator, which can do EVM and ACPR, we call it as vector component analyzer, which is helping you to analyze how the behavior of or how the EVM and ACPR gets affected by whatever devices you have in between. We have the drive test tool, we have different measurement softwares, we have our OTA chambers. A very short introduction in the limited time I have. So please do let me know if you have any further questions. You have my email ID here. I'm around here for some more time. I have my colleague Mr. Rituraj also here. You can get in touch with us if you have any further questions. Thank you. Yes, sir, I have a question.
Thank you.
12th slide, I don't remember the. Okay, this one. Yes, this is a real RIS, and we have a G node B here, FR2 G node B, and we call this as a Nemo drive test tool. That is what we are using here. This is inside a passage where this direct signal, there is no direct line of sight path is not there between the G node B and the UV here. So we are using RIS. We have done one campaign and we are trying with another RIS in some time. Yeah. Yes. Yes. We have tried two of them. We have got very good results from one of them. We are not getting the result from the other. We are trying to understand what is happening there. Yes, we have got good results from one of the RIS. Any other questions? Okay, then I'm around here. Thank you.
Thank you. So we'll call up on stage Dr. Ramya. Adish is here. Tapas, Dr. Tapas. A small memento from IIIT COMET Foundation.
Professor Devdik Sarkar. The tea is on. Anybody wants to take tea can take the tea and come back in.
So you can start. Okay, so very good evening to all of you. I am Devdeep Sarkar from Indian Institute of Science ECE department. So I think we have had a very engaging day of talks on this interesting technology of RIS, that is Reconfigurable Intelligent Surface. So we heard the industry perspective and operator perspective and the different activities that has gone on into various research labs, as well as I think we saw a very nice demo on the RIS done by IIIT COMET team, which is spanned over different institutes. Now, in this final session, I think we will have different speakers, mostly from the academia, who will discuss about their perspective on RIS. So the first speaker in this session is Professor Sandeep Chepuri from Department of PCE IISc. Abhishek Gupta. Okay. So Sandeep, I mean, all the speakers are online. Okay. So we can go with Professor Abhishek Gupta from IIT Kanpur. Over to you, Abhishek. Abhishek, can you hear us?
Hey, hi. Yeah, I can hear you. Can you hear me?
Okay, yeah. Yes, Abhishek, you are audible. So I guess you can share your screen.
Okay, one second. Can you see my screen?
Yes, your slides are visible. Yeah.
Okay, sorry, I'm not able to zoom somehow.
You can share it in full screen, I guess.
Yeah, I'm not able to do full screen somehow because it's. Just give me a second.
You can press play from start.
Right. So can you see? Is it now zoomed in? Can
Yeah,
you see
we
this?
can see. Yeah. It's visible. Yes.
Okay. So one second. It's actually not letting me see the screen, and the other thing is just zoomed into everything. Sorry. So I am not comfortable with this portal, so I'll just go this way because when I zoomed, this just doesn't show me anything. Uh, so hi everyone, my name is Abhishek, and I'm from IIT Kanpur, and I'm going to talk about our recent work where we were discussing how we can deploy RIS. Uh, so we know that the blockages are a issue at modern networks. Basically, when we talk about networks with very high blockages. So in that case, we require approaches which can mitigate the blockages, or we need to find methods which can quickly do handovers and different, right? So that comes with another approach that can we actually do something more, right? Rather than just like trying to mitigate these blockages or do handovers. And that's where the RISs will also becoming important, that you can actually modify channels. So if there is something blocked, you can still find some reflecting path, right? And the ability comes from it's able to reconfigure its reflections so you can reflect in any directions, right? So, but the main problem comes that because the RSS link is made from two links, one from UE to RIS and one is from RIS to base station, it suffers from double path loss. So the question would be, where should I put this RIS, right? If I have a user, if I have a base station, where should I put this? So, for example, if I take a very simple problem, if I fix the location between RIS and the user, and I ask if I move this RIS, the total power will be basically a function of the distance square and 1 upon that. So if I just plot this, you can see that it maximizes when the RIS is at the base station or RIS is at the user. So this kind of gives a very simple answer that you should deploy the RIS at base station or at the user, and because there are many users, you cannot put one user at one RIS at every user. This comes that you should put at the base station, right? So although this is okay with terms of path loss, and then even if you include height, you will kind of get the similar answer. But the problem is the main purpose of RIS is to avoid blockages, and if you put RIS exactly at the base station, then if suppose the RIS is at the base station, if something blocks the base station, then it will also block the RIS. Right? So there is literally no point of putting the RIS exactly at the base station because then both will be blocked. So the purpose you wanted that you can avoid blockages or you can mitigate blockages of the base station, that is not served. So from that perspective, you should actually put the RISs at a location which can provide you an independent channel from the large scale fading perspective. For example, here you can see if you can put RIS here, then when the direct link is blocked, you can get an alternate path. Right. So this is saying something different that you should put where there is a alternate new alternative path. Right. So we should put near the base station, but we should put not exactly at the base station at some location. And what is that location? That is what we are concerned in. So our goal was to find out the optimal location of RAS, which can minimize the joint blockage probability and maybe like maximize SNR, SNR coverage, right? And for that, we actually took a very large scale system because this problem you cannot solve by just thinking about one link. You have to include the effect of interference. You have to include the effect of blockages, right? So we wanted to discuss about a complete large scale network where there are many base stations on a single road. There are many vehicles, right? And we wanted a model where RIS is at some distance from the base station, so it's still near the base station, but at some distance, and we want to optimize that distance that so that you can still get an alternative path. And users are everywhere, and there may be multiple roads also. So when you think about this type of system, which is very large scale, and you require some system level perspective on that, right? To model such kind of geometry, we use a tool called stochastic geometry, which is a mathematical tool to study and model randomness, and you can actually compute the performance when these things are random, right? And here, what are the random things? The base station deployment, the wave blockages, the users. These are the random factors which you want to include, right? So using stochastic geometry, I model base station as a Poisson fund process, and also I took vehicles, which I model using Boolean models. These are standard models in stochastic geometry, and using that, we can actually compute the joint blockage probability, the block probability that the RAS and the base station are both blocked. And now if I plot this, the joint blockage probability, with changing the RAS, this actually tells you a different story. It says that when the RAS is at the user, it gives you the best minimum blockage probability, and when it is at some other location, it gives you more. So this basically says that you should put the RAs at the user, not at the base station, right? So the two things which were important is that one thing is that yes, RA should be placed. If there is only one user, you should place it at the user. Then you get the lowest blockage probability. But then there are many users, so we should select the location for the average user. And what does average user means, right? It is from the perspective of blockages. What are the users which are more likely to be blocked? You should put according to that, right? So we actually averaged it over the whole user distribution, and we then optimized it, and we found that there is a optimal value of location which you can compute, right? And that depends on the blockage severity. So here I'm changing the blockage severity, which means how severe the blockages are with respect to the base station deployment. For example, how severe is the density or the height, right? And we found that it's basically the optimal location of RIS decreases with the blockage severity, which means that if and then we also plotted using numerical simulation, and we found the same thing, that usually the optimum location is of the outer of cell radius, but when the blockages are less sparse, then mainly the cell edge users are going to be blocked, the nearby users are generally fine. So you should deploy according to cell edge user, which means you should put the RS at the edge. But if there is severe blockages, then you should put according to the then all the users can be blocked. So you have to talk about the average sense and the optimal location shift to the origin. Right. Similar thing we also happened when we included the effect of signal to noise ratio, and we plotted the SNI coverage, which also gives you your optimal location of RA, which is close to the previous one, but because of this path loss, it actually shifts the optimal location a little bit to the center more. Right. And we also plotted with respect to interference, and we also included the effect of RAS interferences, and we got similar result, right? So this is like a paper corresponding to that. Uh, so that was the one of the work we have been working on. And that's all from me.
Yeah, okay. So in the online, if there are any questions. Not for this session. Okay, then thank you, Abhishek. Thanks
Thank you.
for the talk. So Sandeep. Okay, so we'll move to the next speaker, Professor Sandeep Chepuri from Department of ECE IISc. Sandeep, can you hear us? Sandeep, are we audible? Okay, it dropped out. So then we can move to the next speaker, Dr. Devidash Kundu from IIIT Delhi. Devidash, are we audible?
Yes. Am I audible to you?
Yes, yes, yes. Hi. Yes. So please share your screen.
So
Yeah.
Devdeep, I'm ready now. So maybe I'll go on whenever you say. I can hear you now.
Okay. So should we have, I think Sandeep has joined back. So let us, okay, Devidash, can you please wait for some time? Then we can have
Sure,
Sandeep.
sure.
Yeah. Okay.
Yeah.
Sandeep, please go ahead. Yes, your
So let
screen
me,
is visible. Yeah.
and you can also hear me all right, right?
Yes, yes, yes. Yeah, you are audible.
Yeah. I guess you all had a very long day, and I could not be there in person because not doing very well. I hope you can still hear me with this voice, but I'll try to uh, cover what we are doing basically with RIS. What I try to focus in today's talk is uh, about integrated sensing and communications, ISAC, which is one of the emerging topics that is receiving interest release 19 onwards, and even in release 20. where there are a few study items related to integrated sensing and communications. So what we'll do is not focus on using RIS for communications alone, but see how we can use that for sensing as well. So integrated sensing and communication in particular, what I'll do is I'll try to showcase how we can use a common base station to serve both users, which will be a communication alone service, but also to provide radar-like service, which is sensing of targets, doing localization of targets, and using a same spectral resource and hardware resource. How do we do this? So that is what I'll try to focus on. That has many applications, basically using the cellular infrastructure. It could be even Wi-Fi infrastructure, but use that as a sensing device. So what I'll focus is on mostly the transmit beamforming, where we'd like to form beams towards users of interest and also sensing a particular object or a target, where sensing basically means like a radar-like setting. And what we will be focusing is on higher frequency bands, where the some of the targets or users or both might not have a direct line of sight because of the frequency of operation or any other blockages. And we'll see how to use RIS in that case to enable such sensing and communication. So we recently had a tutorial style white paper in Signal Processing magazine. The content that I'll be covering is mostly from that, and a few additional works on sensing alone. So I'll go very quick over this. RIS basically is a passive device which can introduce virtual line of sight paths whenever there's no direct line sight path, and these are useful for higher frequency bands where path loss is significant compared to sub 6 gigahertz frequency bands. So again, I guess you've been hearing about RIS since morning. This does not need any introduction. What we'll be using is a fact that I have a passive device which can be controlled, basically setting up the parameters of the RIS phase shifts, maybe a certain amplification factors that can be programmed using this RIS controller, and that is basically controlled by the base station, and that can be used to form beams towards any angle of interest. So that's the setting. And the input output modulus, whenever a signal is impinging on a certain element of the RIS itself has n elements. What it does is it imparts a phase shift and sends back. So basically, if you get a signal from an antenna having n elements, you have RIS which is having m elements. So what comes out is m elements of the signal is what you get, but with a certain phase shift. And what we can control is basically the phase shift of the RIS elements. So whenever you would like to see this as a cascaded channel, what we basically have is I can view now RIS as a part of the channel that allows us to control how the channel looks, and we can write the input output relationships between how the channel looks. And for a simple setup where you can assume a linear model, you have a signal that is at the input of the transmitter that goes through the transmit channel and then phase shifted and is received via the received channel, right? So that's basically the setup. And what now we can do is, if you want to do beamforming, if you have the entire knowledge of the channel information, then you can use that to basically do beamforming or pre-coding of your transmit signals. And if you are interested only in communication only setting, then with a single user, what you could do is you can set up an optimization problem where you optimize signal to noise ratio, and signal to noise ratio is now a function of these phase shifts. Now depending on what the channel is, you can basically pick what the phase shifts are to maximize the signal to noise ratio. And as such, when you know the channel information, uh, the optimum phase shifts are so-called conjugate beamformers. So you basically take the opposite of the channel to mitigate the effect of the channel. So this is fine when you have a communication only setting, but now when we have sensing, then what we will try to do is we'll try to replace the communication performance measure with a sensing performance measure to again compute the phase shifts. And one could think of doing sensing in any typical radar setup like a monostatic or a bistatic radar setup where you can have a transmitter and a receiver which is co-located, and that there is no direct path between the transmitter and the receiver. So then you can use RIS to basically receive back the signals. Although because of the quadratic path loss, the signals might be very weak, but that is still better than not having a line of sight path where you don't see the targets itself. So one advantage of RIS in this particular case is to use RIS for non-line of sight imaging, radar imaging. So think of your favorite setting, monostatic or bistatic, then you can use RIS. So this is some experiments about transmit beamforming when we are doing sensing alone. So here is a cartoon illustration where there is a target that is moving in a certain trajectory covering points from A to J, and you would see the transmit beams that are formed. Uh, when you want to do sensing, you would like to basically form beams towards the directions of interest. So whenever there is point A, you directly form the beam towards the target, and you don't basically use RIS. But when we look about points in this regime, say F or J, then you see that F, it doesn't matter because the RIS and the target more or less are in the same direction. So you basically form a beam which is similar. Then but if you look at point J here where the target is not directly visible, you can do non-lines of imaging by forming a beam towards the RIS, and then RIS is going to further transmit the beam from the transmit beam towards the target. So that is what you see here. You form a beam towards RIS, and then RIS is basically pointing, forming a beam and sending signals to J, to the location J. So uh, what one you can what so the point is, if you are using RIS, you can also do radar imaging beyond communications, which is basically one of the common use cases of RIS. So what I'm trying to show here is you can also use it for sensing, target positioning and localization. The other application that we have been looking at is integrated sensing and communication, where you have a dual function base station which serves both communication users and targets. And now, in case you have scenarios where the users are not directly visible to the base station, but you can access the users via the RIS, or it could be that the targets are not directly visible, like in the previous setting. Then you can form beams to RIS and then further forward that signal to the targets. So this is typical in ISAC, where you would send a transmit signal that contains both communication waveforms and sensing radar waveforms. You would send a common waveform to the through the DFBS, and then the goal is to basically design beams, the precoding matrix or the beamforming matrix that is good for both these sensing and communication tasks. So in that particular case, the communication performance measure could be measured using, for example, the SINR, where now because you are also using radar waveforms, the SINR is not just the interference that a particular symbol to a user uh, causes interference to the other user, but the radar waveforms also act as now interference. So now we can basically formulate this as an optimization problem where you try to form beams that are good for both sensing, which is the communication constraint, SINR constraint, and to have a certain beam pattern which is good for sensing, for example, beam patterns that have good autocorrelation properties. So now when you also have these RIS, there is other parameter that you have to design is basically the RIS phase shifts. So this is a optimization problem that can be solved using usual convex optimization techniques, or you can use a neural network to solve this optimization problem. But the point is, now you have more flexibility to design the beams because you can now do non-line of sight imaging. So here is some illustration where you see that the beams are formed towards the targets and RIS, and this is a case where communication users are not line of sight. So you use RIS to form beams, and that is sending signals intended for that particular user via the RIS. So you can use RIS also for ISAC. That is the point of this slide. In addition to this, what we have also been doing is uh, uh, radar imaging using a single antenna, but using RIS as coded phase shifts, coded aperture imaging, where typically whenever you want to do 2D imaging, you require a MIMO or a phased array radar. But now, since you have a single antenna, there's no way that you can resolve both targets and range and azimuth or range and cross range using a single antenna receiver. So, but instead, what you can do is you can use RIS to form multiple coded beams to form images. And this is one such setting where you can use RIS basically to use RIS as a synthetic aperture radar or a coded aperture radar. So this is also something that we have been looking at. The other thing that we can also do again in the ISAC setting is a codebook based design where you can use RIS, a part of RIS screen, you can allocate to do sensing of targets. And the remaining part you can use, for instance, in this case, to make have a rank 2 channel. So these are some of the things that we have been looking at. I can, of course, go into the details if it is of interest to any of you. But the point is, RIS is useful beyond communications, particularly for sensing and this new technology that is integrated sensing and communication. So that's basically what I had to say about what we have been doing. If you're interested in these areas, I invite you to look into this tutorial style article that appeared in Signal Processing magazines. It's titled "Integrated Sensing and Communications with RIS," and that's all what I had to present, Devdeep. I'll be happy to take any questions if any of you have.
Thank you, Sandeep, for the nice talk. Any question from the online as well as offline audience? Do you have anything in the chat box? Okay. So maybe I just have one small question, like regarding that application of RIS for ISAC. I think so. Are you using the full RIS surface for generation of like these different beams, or like only partially, like some portion of the RIS you're activating for, let us say, sensing, and some portion for the communication?
Yeah, so we have like a couple of different configurations where we could do kind of a space division where you allocate a few elements for sensing and few for communications. In particular, since we are doing passive beam forming, it will be difficult to form pencil beams with RIS. So the beams are usually very wide, and as a consequence, what we can do is we can do kind of a surveillance mode with fewer sensors, and then use a lot of these RIS units to then do a finer scan. So when you're doing in that surveillance mode and till you figure out the exact location, you can use the remaining elements of the RIS for communication. So that's how we do that. But otherwise, we can. So one of the disadvantages with RIS is that it is limited to a single user communication. It is not like a MIMO antenna where I can do pre-coding at the RIS. So basically, whatever we transmit to the RIS is reflected back. So now I cannot send more streams because I have more units in RIS. So whatever I can do with the actual antennas in the base station, that is all I can do. But So in that sense, we can use RIS either to do non-line of sight imaging or to basically enable a better channel.
Okay, yeah. Thanks, Sandeep, for the illuminating answer. So we'll move over to our next speaker, Professor Devidas Kundu from IIIT Delhi. Devidas, yes, it's all right. Stage is yours.
Am I audible, Devdip?
Yes, you are audible, and your screen is also visible. Yeah.
Yeah. Is my full screen visible also?
Yes, it's visible. Yeah.
Thank you. So good evening to everyone. I am Devidas Kundu from IIIT Delhi. So I will be presenting on behalf of IIIT Delhi, but I have my colleagues also who are working in the allied fields. So Samik is there who is working on AI-based channel modeling and sensing, and we are jointly working on actually semi-autonomous RIS. Dr. Vivek is there who works in the area of Li-Fi and Wi-Fi for indoor communication. Shobha is there who is working for radar sensing, and these are my actually anytime go-to person whenever I actually fall into trouble. And I work in the surface electromagnetics and reconfigurable intelligent surfaces. So uh, today from morning we have actually have a lot of useful discussions. So I will not bore you with the details of what we are doing. I will just give some bullet points that have been done in our lab. So I will present only two problems in this talk today, and I will try to confine myself within 10 minutes. So problem one is design of 1-bit coding metasurface based RIS and its microcontroller based control circuit. I have seen that many of you have already working on this or have already done a good work on this. So we actually tried to do miniaturization of the unit cell of a 1-bit coding metasurface. Then we got a good phase difference of 180 degree for a good bandwidth. And our solution approach is actually physics based theoretical calculation first, then simulation using full wave solver. Then we also have developed our hardware for of the RIS, and we have done the RF as well as communication testing. So test bed that we have developed in IIIT Delhi. One is anechoic chamber. I will showcase the measurement result in our anechoic chamber, and we have also developed one test bed for sensing and communication with moving targets. A previous speaker has elaborately discussed about the sensing and communication using the RIS. So that testing also we have done, but it is in the experimental stage. So basically, we have used two main simulators. One is MATLAB, another is CST Studio Suite, and we have also submitted two NIPs, which are approved also. One as work item, another as study item, and you can find the details of our works in our recent publications as well as patents. So, solution approach, many of you have talked that we have to calculate the phase matrix first, then we have to digitalize or quantize the phase for different beam angle, and then we can theoretically calculate the radiation pattern. And with simulation, we can verify also the theoretical result before going to fabrication. So we have actually our own RIS. You can see in figure 2B, which we have developed at 5.5 gigahertz. It has 16 cross 10 elements. It works well for 5 to 6 gigahertz bandwidth. We have developed also a plug and play control circuit board, which is one for just pin diode switching, another for both pin diode forward bias or varactor diode reverse bias control. So these we have already a couple of control circuit board which we can actually add at the backside of the RIS if our RIS becomes larger. So you can see we have tested the RIS in our anechoic chamber, which is recently developed, and we got very satisfactory result for a far field incident wave of 1-bit coding metasurface. And you have already seen that the problem of the grating beam that will be obvious for 1-bit coding metasurface. After that, we have also done testing for the communication. We have done communication for a very near field incident or transmitter, and the receiver is in the far field, and we generated single beam, and we can achieve a non-line of sight communication between the transmitter and the user. So I will not showcase the video for the communication implementation. We are using the LabVIEW communication LTE application framework to actually do the bringing the video and uh, uh, demodulating it for different channel characteristics. So what I want to show here is that we are also doing a sensing first and then communication with the target. So we are initially sending some signals or the beams from the RIS, and the phase configurations are changing from plus theta to minus theta. And if there is a UE, then we are receiving the maximum power from that location. After identifying that direction of arrival, we can actually configure the actual beam to send the communicating signal with the RIS, sorry, with the UE. So this hardware demonstration I want to hope you can see it. We have a moving target user, which is a horn antenna, and the RIS is initially scanning the space, and whenever the maximum power received, that is my direction of arrival, and we can see that the communication is also simultaneously happening. And another use case that we are also testing is that localization of the non-line of sight human being, or the motion detection of the non-line of sight targets using the RIS. So we are doing the around the corner radar sensing, where we can see that in non-line of sight radar does not work, but with the help of RIS, we can still detect the human being in the in the non-line of sight area. So, and second problem that we are working now is that I have seen that many of you have also done that most of the channel modeling have been done using ideal single link or two links. Two links means the direct path, which must sometimes obstructed by obstacle. So, as a researcher, do not consider that, and the reflect path from the TX to RX to TX to RIS to RX, that generally people consider. But that is very simplistic channel modeling. We have seen from electromagnetic point of view, when there is dense urban areas or indoor environments, then there is rich scattering due to the edge effects, multipath propagation, and even from the mutual coupling of the RIS elements. So we are actually trying to take into account those effects and trying to mitigate the effect of those, especially the multipath effect due to the high side lobe levels. So here I have shown that the direct path is the straight line, solid straight line, but the multipath are dotted lines, and edge diffraction is also a dotted line. So receiver will get all of those signals, and if the side lobe levels are very high, then there is a problem. So how to mitigate the side lobe levels? We actually need to play with the magnitude also. We cannot just play with the phase, because if we use non-uniform magnitude, then we can actually taper the amplitude level of the reflected beam at the side lobe level. And this is very actually well-known phenomena in the RF domain. We can actually use Chebyshev polynomial or binomial polynomial, and we can get a non-uniform amplitude distribution on the surface, where we actually now having both magnitude and the phase distribution on the surface. But good thing with the magnitude distribution is that we once we actually reduce the side lobe level, let's say in this case, you have seen for the 1 meter coding surface, side lobe levels maybe will be 10 dB below the main lobe level, and in experiment it will go up to 7 dB. So that is not good, though that will contribute to the multipath. So one good thing with the amplitude tapering is that we can define a single level of the side lobe level, let's say 20 dB, and for that there is a certain non-uniform magnitude distribution. So you do not need magnitude control for every different phase pattern. Magnitude can be fixed, and which can be realized by using a passive resistance also, SMD resistance for 20 dB or 30 dB that you want, and then you can play with the phase distribution. But in this work, we have done both magnitude and control, and we got full control over the reflection coefficient to achieve not only the single beam steering with side lobe level control, but multiple beam steering with side lobe level control also. Professor Khankoje have discussed about the multi-beam generation only phase variation. We can also do a very less amount of using very less amount of unit cells. In our experiment, we have done 15 cross 10 elements, but with the help of amplitude tapering, we can actually reduce the side lobe level both from theory and full wave simulation less than 20 dB. So the amplitude tapering will certainly help, and that's why we are actually now proposing this amplitude tapered meta surface, which can be used for actually reducing the interference effect for our RIS aided communication, and we are doing the channel characterization by taking into account of the edge effect, multipath propagation, and even mutual coupling. So we will publish our result very soon, and we are comparing it with the traditional RIS, and you will see the improvement of the result. So I got one actually slide template, and there is one point that view of different institute regarding the RIS classification. So yeah, I would suggest all of us to actually go through this paper, because this paper has been written by 3, 4 IEEE fellows, and most of are actually very big shot in this area. So they have classified the RIS into mainly three types. One is passive static reflector, where there is no pin diode or vector diode or magnitude or phase changing property. Only they can send a fixed beam that generally is a conventional reflector. What we are all working on currently is the passive dynamic arrays, where the arrays are loaded with pin diode or varactor diode to achieve the dynamic phase and or magnitude changing property, thereby capable of dynamic beam forming. But we cannot call this as active arrays because it is not using any active element. But recently we also have seen that active arrays can also be realized using the low cost CMOS or BJT amplifiers, which can enhance the gain. So that can be also another category. And many of you have shown that relay versus RIS. RIS really helps to achieve the spectrum efficiency. It consumes low power level because RIS does not require front-end circuitry for all the elements. Only the transmitter side requires a front-end circuitry. And relay, but by the way, require front-end circuitry, processing, reception, retransmission, etc. So with this, I want to conclude. Another interesting point was their challenges. So I feel from the academic side, we do not, whatever technical challenges we face, we are ready to take on. But there is another challenge that many people so I will not utter that. I would like to acknowledge our team members at Metasurface Research Lab, IIIT Delhi, Deepak, Khagendra, Pragati, Ankit, Tushar, Kainath, and my academic collaborators also Professor Uday Khankoji from IIT Madras and Professor Sulabh Gupta from Carleton University, working with whom I have gained a lot of knowledge. I want to also thank my industry collaborator TCS, who has given me platform to showcase our works in IMC and TSDSI 1M, 2M. So if you have any queries, you can please feel free to contact me through this email, and I am now ready to take questions.
Thank you, Devidash, for the nice presentation. Any questions from the offline attendees or the online attendees? Uh, I have one quick question, Devidash, like regarding one of the experiments, there were many interesting things that you showed. You showed one with that radar non-line of
Yeah.
sight, percent detection, right? So which frequency is this
Okay.
radar
Yeah.
operating?
5.5 gigahertz.
Okay, okay. So you have some commercial radar board there, or you have,
No,
set up?
we are using two horn antennas
Okay.
as one as transmitter and another as receiver, and we are doing a monostatic sensing, and we are using a spectrum analyzer to
Okay.
collect the both phase and magnitude of the reflect beam.
Right, right, right. Okay, understood. Yeah, thanks. So maybe we can discuss offline more. Yeah. Okay, thanks.
Yeah, sure.
Yeah,
So
thank you.
let us move to our next speaker. I hope we have Professor Brijesh Kumbhani online. So over to you, Professor Brijesh from IIT Ropar. Brijesh, can you hear us? Brijesh, are we audible? Um, Professor Salil Kashyap, are you audible? Are we audible? Can you hear us?
Yes, I can hear you. Yeah, yeah.
Yeah,
Sure.
okay. Then I think before Brijesh, we can have your talk. So over to you, Professor Salil from IIT Guwahati.
Okay, sure. Yeah, just 2 minutes. I'm just sharing my screen. Yeah, 1 second.
Yeah, sure.
Okay, all right. Is my screen visible uh, at that end?
No, no, not yet.
Okay. I've shared it. Just 1 minute.
You can share your screen, maybe.
Now is that visible?
Yes, yes, yes. Yeah.
Okay. So I'll go full screen then. So full screen now.
No, I mean just before your screen was visible. Now nothing is visible.
Acha, maybe should. Okay. Hope it is visible now.
Yeah, yeah, it's visible.
Shall I go full screen? Because every time I'm going full screen, it goes off. So sorry for the,
Okay.
yeah, it's okay. I'll continue this way. Yeah. So
Yeah. Okay.
yeah. So what I'll do is I'll speak about RIS aided wireless energy and information transfer. Yeah, there's a problem that we have been working on for a while now. Yeah. So what I'll be presenting today, these are mainly due to the efforts of my PhD student Chandan Kumar and Faisal Jishan, and a collaborator, Dr. Sarvendranath Trimalapudi, IIT Tirupati. Uh, so just to give you a quick motivation behind wireless energy information transfer. So we all understand massive number of IoT devices are going to form a core component of next generation wireless systems. And most of these devices will be deployed either for sensing, computation, or communication. Yeah, with applications ranging from consumer electronics, intelligent transportation, home automation, healthcare, and so on. Yeah, now the thing with these IoT devices are that these are usually energy constrained, and they depend on batteries with limited capacity. Now, many a times these devices are located at hazardous or inaccessible locations, and therefore replacing battery becomes a hassle. So one of the solution to provide uh, uh, connectivity, meaning energy to these devices, is use of energy transfer, wireless energy transfer, where these sensor nodes they essentially harvest energy from electromagnetic signals. It's a practically appealing technology because you get rid of the hassle of battery replacement, and at the same time you can go wireless. However, one must understand that there are several challenges that need to be tackled to make wireless energy transfer a reality. Uh, the first challenge is that only a small fraction of the power which is radiated by the source can actually be harvested at the user or the sensor node. And that essentially restricts the range of energy transfer wirelessly. Moreover, wireless energy transfer is a fundamentally different problem than wireless information transfer because it is the absolute receive power which is of interest when we talk about energy transfer, unlike information transfer where the received signal to noise ratio is of interest. Yeah. So while your signal may be strong, while your received signal power may be much higher than the noise power that can essentially help you decode data, but the receive power may not be appropriate for turning on the harvester at the sensor node. Yeah. So the design must ensure that sensors harvest more than what they consume. Yeah, and most likely this energy transfer is going to happen in conjunction with information transfer in beyond 5G, uh, because that would be a more cost effective alternative. Yeah. There have been several attempts in the past where people have looked at using multi antenna energy beamforming to these IoT nodes. Yeah, but then uh, uh, using these multiple antennas at the source, yeah, makes the source bulky, costly, and power hungry, because while these antenna elements themselves are cheap, but then every antenna requires a radio to run it. I mean, so, and these radio frequency chains, they essentially consist of power amplifiers, up converters, and filters, yeah, which consume power, make the hardware complicated. Yeah, so an alternate solution could be use of these intelligent reflecting surfaces. Now, there's an RIS forum, so we all understand it consists of a low cost, I mean, it's a meta surface consisting of several low cost passive reflecting elements. And these are capable of inducing amplitude and phase changes in real time. Uh, if we can somehow appropriately program these elements shown in green here, yeah, one can ensure that the multiple copies of the signal received at the user, they sort of add up constructively and boost the receive power. Yeah, now that is a good thing because that can lead to higher data rates, improved coverage, and as well as efficient charging of IoT devices. The other advantage with these surfaces is that these are RF chain free, so they will most likely consume orders of magnitude lower than a solution where the source has multiple RF chains, active RF chains. Yeah, these surfaces are easy to deploy, and therefore it makes it a very promising solution towards energy transfer. Yeah. Now, the first problem that we looked at, yeah, it has to do with joint antenna selection and RIS assisted energy transfer. Now, this is the model that we look at. We consider a source with multiple antennas, but let us say just a single radio frequency chain. Now, the motivation behind having a single radio frequency chain is to essentially make the source simpler and something that consumes much lower power. Now, since the source has just a single RF chain, we need to, the source needs to perform antenna selection. Yeah, at every time instant, it needs to decide which of the antennas should the RF chain be connected to for transmission. All right, so source performs antenna selection. Yeah, the channels are considered Rician via the IRS. Direct path is relay because it is more likely to have only non-line of sight components. Yeah, TDD mode of communication is assumed. Now, for this model, what we do is we propose an antenna selection rule that requires fewer pilots for channel estimation. Yeah, detailed outage analysis is performed both with perfect and estimated CSI. Now, given this setup, we prove that the diversity order is M plus N, where M denotes the number of antennas at the source, N denotes the number of IRS elements. We do extend this model to a scenario where the source will have not necessarily one RF chain, but multiple RF chains lower than the number of antennas M at the source. Now, given that when we have multiple RF chains, we need to essentially select a subset of antennas. Yeah, so given M antennas and let us say Q RF chains, we will have M choose Q possible subsets. So we need to figure out which subset to select. And with subset AS, we also need to design the transmit beamformer at the source and passive beamforming at IRS. We do so using alternating optimization. We do understand that practical IRS cannot induce continuous phase shifts. Yeah, it can only induce certain discrete phases. So we understand we try understanding the impact of discrete phases. The model is extended to multi-user scenario, and the impact of limited scattering on performance is also studied. Yeah, limited scattering meaning it is likely that we will not have, I mean, the number of reflectors around the transmitter and the user will be much lower than the number of IRS elements, which would essentially induce spatial correlation among channels via the IRS. So that impact is studied. Yeah, just two interesting results based on what we observe. So here what we have done is we have plotted probability of outage in energy transfer as a function of the source transmit power. Yeah, and an outage is declared when the sensor node harvests less than what it consumes in sensing, computation, and communication. Now, yeah, we see several curves here. So we do so for different source configurations. So 1,4 denotes a source with single RF chain, 4 antennas. 2,4 is 2 RF chain, 4 antennas, and 4,4 denotes the full complexity source. Yeah, these four curves are for 50 IRS elements and another four curves for 150. Now, yeah, one thing that we note is as the number of RF chains increase, outage improves. That's due to the active beamforming gains that you get. At the same time, with 150 IRS elements, you get increased passive beamforming gains. Again, the outage improves. But what is interesting to note is that C equals 1,4, yeah, source with single RF chain, 4 antennas, but 150 IRS elements does better than a full complexity source with 50 IRS elements. Yeah, which essentially indicates that one can trade active RF chains at the source with passive elements at the IRS to obtain improved outage performance. Yeah, another thing that we observe, I mean, we essentially plot power transfer efficiency as a function of number of radio frequency chains. Now for this uh, result, we had kept the number of antennas fixed at 32, and we vary the number of RF chains from 2 to 4 to 6 and so on until 32. What we observe is that as the number of RF chains increase, the power transfer efficiency increases. Yeah. What is power transfer efficiency? This is the ratio of the power harvested by the sensor to the power consumed at the source, yeah, or in the network. Yeah. So, so initially, as the number of RF chains increases, the power harvested by the sensor exceeds the power consumed in the source. But then beyond a certain number of RF chains, power consumed in the network sort of dominates over the power harvested by the sensor, and therefore we do see a drop in power transfer efficiency. We see these curves going up as we increase the number of IRS elements, indicating power transfer efficiency improves as number of IRS elements increases. Yeah, we also extend our work. Yeah, why just a single IRS? Why not two IRS? And we tried understanding what are the gains that are possible. So given so right now we consider just a simple source with single antenna, user again with a single antenna, but then there are two IRSs positioned this way. IRS1 with N1 elements, IRS2 with N2 elements. And what we do is we perform an outage probability analysis again, yeah, considering nonlinear energy harvesting at the user. Now, for this setup, we obtain the optimal number of IRS elements that minimize power consumption. We benchmark our results against single IRS and massive MIMO. Yeah. Some asymptotic analysis is performed to identify regimes where double IRS is a better solution. We also extend our study to 4 communication links and present how these phases at the 2 IRSs must be configured. Yeah. So just a quick result to essentially highlight what happens to 1 minus the outage probability when it is plotted as a function of lambda naught. What is lambda naught? So yeah, so n1 number of elements here, n2 number of elements here. Lambda naught is n1 by n1 plus n2. Yeah, the fraction of elements out of total n deployed at IRS1. And what we observe is that when you sort of do a, so when n1 equals n2 equals n by 2, sorry about the typo here. So this should be n by 2. Yeah, outage is essentially minimized. Yeah, with equal number of IRS elements at both the IRSs, outage is minimized. Yeah, that's why you see a 1 minus P out maximized here. Yeah, we do this for different scenarios. Scenario one is one with pure line of sight components. Yeah, pure line of sight components, and this is with more of non-line of sight. What we plot here is receive power as a function of the number of IRS elements in a double IRS setup, number of IRS elements in single IRS, and number of antennas in a massive MIMO setup. This plot indicates that double IRS is not always a better solution. Yeah, I mean, there are fewer elements. I mean, you need to have certain number of elements in a double IRS for it to beat single IRS in massive MIMO. Yeah, because you essentially need to overcome the effective path loss of the two hop network here. Yeah, so the effective path loss from the source to user is much higher, and therefore you need a certain minimum number of elements at a double IRS for it to beat single IRS and massive MIMO both. We do extend our study to, so this is all for
Yeah, Salil, actually you are not audible. I think the connection is lost or something. No, I think he's moving. Mm-hmm.
yeah. Am I audible now?
Yes, you are audible. Yes.
Sorry, I don't know at what point I was disconnected.
Yeah, you
Uh,
are at slide 8, I think. Yeah.
Slide 8. Okay, sure. Yeah, yeah. Is that fine now? Yeah. You can see my screen, no?
Yes, yes.
Yes, yeah, yeah. So this is so we extended our study to consider all four communication links between the source and the user. Yeah, this being the direct link, the other link via IRS1, the third link via IRS2, and then the fourth link that sort of signal travels via both IRSs. As expected, communication with by considering all four links does better than communication by just considering two links. Yeah. Uh, and the lower complexity AO based phase shift design does as well as the higher complexity manifold optimization based design. Yeah, we then extended our study to also uh, so source talking to multiple users, but then the channels via the IRSs, they are spatially correlated. Uh, for this setup, considering nonlinear EH and power splitting architecture at the user. What do I mean by power splitting? Only a fraction of the received power is used to harvest energy, and the remaining fraction is used to decode data. What we do is we derive upper bound on outage probability and spectral efficiency. The model includes spatial correlation for cascaded channels via the IRS, And then one thing that we observe is the source to IRS link is common for multiple users. Yeah, so that is also taken care of in the analysis. Uh, one interesting thing, I mean, what we try out is what if the users are served based on round robin scheduling strategy? We go one by one, serve every user. Now, given this model, we develop a gamma distribution based approximation for the cascaded channels via the IRS. We do perform diversity analysis and sort of obtain diversity order in terms of the shape parameter of this gamma distributed random variable. Extend this to multiple antennas at the source, use alternating optimization to design beamformer at the transmitter and at the RIS. Yeah, we benchmark our results against random and equal phase shifts, which are channel unaware phase configuration strategies. So these are strategies that do not require channel estimation. And yeah, so here what we do is we plot outage as a function of number of elements on either side of a planar IRS. Yeah, so we consider an S cross S IRS, and what we observe is that given that a power splitting architecture is used at the user end, as we vary the fraction of the power, while spectral efficiency improves, outage drops down. But then by increasing the number of elements at the IRS, one can essentially obtain a higher data rate for a given target outage probability. We compare our outage probability. I mean, here outage probability is plotted as a function of the source transmit power for two different scenarios. One in which every user is served one by one for tau by u fraction of the time, and another where all users are served simultaneously. Now, what we observe is that the outage probability decays at a much slower rate for the simultaneous service scenario because in that scenario, the design of beamformers at the source is such that it ends up allocating more power to the users with stronger channel. And because of which the likelihood that a weaker user suffers from outage increases. Yeah, so that is why we do see a slower rate of decay in outage probability when all users are served simultaneously. Uh, some of the ongoing works. There's another work where we are looking at again source with multiple antennas but fewer RF chains. So NRF being less than equal to the number of antennas. Yeah, we have one set of users that have energy harvesting capability, another set of users which have data decoding capability. Now, given this setup, we are interested in understanding which subset of antennas to select, how to design active beamformers using the selected antennas, and at the same time configure phases at this IRS to achieve passive beamforming gains. Uh, some of the issues that, of course, need to be handled are how to estimate channels to so many users. Optimal deployment is something that needs to be looked at. At the same time, discrete phase shift is an important practical aspect that should be essentially emphasized while designing such systems. Yeah. Uh, one can so far I've not looked at developing prototypes for these, but then that could be one possibility of future work. Yeah. So with that, I'll stop. I'll be happy to take up any questions. Yeah. Yeah.
Thanks
These
a
are
lot.
some of the indicators. These
Yeah.
are details. Yeah. Thank you.
So, do you have any questions from the online audience? No, I guess. Okay, I think we have one question. What might be the exact reason for power transfer efficiency getting reduced as the number of elements increases in PT versus RF chain plot?
Okay, so here what we do is, so I think this is the figure that is being talked about. So what we do is we plot power transfer efficiency as a function of number of RF chains at the source, keeping number of antennas fixed at 32. Yeah, the number of RF
Okay.
chains is varied from 2 to 4. Now what happens is, what is power transfer efficiency? This is the ratio of power harvested by the sensor node divided by the power consumed in the network in beam forming, channel estimation, and so on. So what we notice is as the number of RF chains is increased initially from 2 to 4 to maybe 6, the power harvested by the sensor node is larger than the power consumed in the network. But then beyond 6 or so, the power consumed in the network exceeds the power, which brings this power transfer efficiency down. But then we do see these curves going up as we increase the number of IRS elements from 50 to 75 to 100.
Okay.
Yeah.
Okay.
Yeah. So
Yeah. Thanks.
yeah.
Yes.
Yeah.
Yeah.
Fine. Yeah. Any more questions if we have?
Yeah. I guess they can. Yeah. Contact you. Yes.
Yeah.
Thanks.
Yeah.
Thanks
Sure.
very much for the talk. Yeah.
Yeah.
Mr.
Yeah. Thank you. Thank you.
So we'll move over to our next speaker, Professor Brijesh Kumbhani from IIT Ropar. Brijesh, are we audible?
Uh, Hello, am I audible?
Yes. Hi, Brijesh. Yes, you are audible.
Yeah. So, okay. So, in the interest of time, I will keep this quick. As introduced, I am Brijesh Kumbhani from IIT Ropar, and some of my colleagues who are also working in this area or the similar aspects of this. They are Samdarshi, Satyam, and Ashwani, and I'm going to talk about performance analysis of RIS assisted NOMA communications. The first problem that we considered was to design a phase shift matrix for NOMA user pair, where we have the system model, which is like the source who wants to communicate to user 1 and user 2, where the direct link is blocked, right? So in this, what we considered was to maximize the SNR at user 1 as well as user 2. So we want to optimize service to both the users, right? So normally what people do is they divide the elements of the IRS, half for user 1 and half for user 2, which in turn doesn't get the full benefit from the overall elements of the IRS, right? So what we did was we proposed a new fetch shift matrix that utilizes all the IRS elements for both the users, and what we got as the benefit, right? So that is an increased throughput, which is the black curve as the results have shown, right? So red and blue, they are the other methodologies which were existing, and the similar trend in the result can be observed when we go for outage probability analysis, right? So we have done both the analysis as well as simulations, and we have got better results by having all the elements, right? So it is obvious that when we utilize all the elements for both the users, we will get the benefit, right? So but how to optimize the phase shift matrix, right? So for that uh, uh, we have the solution approach as we framed the optimization problem in terms of maximization of some SINR. Right? So because this is the users are NOMA users, there may be some interference also, and in terms of that we have the some SINR. Then we optimized the phase shift matrix using the concepts like triangle inequality and the Cauchy-Schwarz inequality, and solved the problem to obtain a suboptimal solution. So this is still a suboptimal solution because the phase shift because the triangle inequality and Cauchy-Schwarz inequality, right? So these both are the inequalities, right? So and mainly the suboptimality is coming because of the triangle inequality. So these results, right? So because it is giving the phase shift matrix, this may be involved in generic RIS controller, and the standardization aspects may be maybe in terms of the regulations for the RIS controllers. And this work we have published in the IEEE transactions on vehicular technology. The another aspect that we considered, that is the RIS assisted underlay cognitive radio for finite block length analysis, right? So normally when we consider the inclusiveness of wireless sensor networks or the IoT networks, or let us say some safety messages being communicated in the vehicular communications, right? So in all these type of communications, very small amount of data is to be shared, right? So when the small data is to be shared, right, so then the block length of the data plays an important role, and that is what is seen in the average block error rate curves which are being shown over here, right? So with the increasing block length, block error rate is decreasing, right? So it is like when our packets are shorter, actually for shorter packets, the probability of receiving erroneous packet, that is larger than that when we have longer packets, right? So for this problem, what we considered is a cognitive radio type of approach, where the cognitive secondary users, they are assuming they are taking harvesting energy from the primary network and using that energy, in addition to that, some of its own energy for communicating with the other users, right? So where we have to do some constraints, like because they are operating in an underlay mode, they should not interfere the primary users, and that is how we have to put some constraint on the transmit power of the secondary node, right? So in this case also we have used NOMA transmission, but the IRS, right? So it is assisting only the farther user, right? So here the source is directly communicating with U1 without the help of without the assistance of IRS, while U2, right? So U2 is being conveyed information via the IRS, right? So again, in this case, we have done the analysis as well as simulation, and we established that the what we established that the fundamental limits for the capacity, which is the Shannon capacity, right? So that is not applicable to the uh, short packet transmissions. So over here, the target technology can be 6G and 3GPP for URLLC, where particularly we can focus on low latency aspect of URLLC, because some of the aspects in maybe vehicular communication, for example, the safety messages, in those type of communications, lower latency is of primary importance, right? And when it comes to short packet, right, so the shorter packets, we already established that the probability of receiving erroneous packet is more as the packet becomes shorter, right? So what approach we did is the mathematical modeling in terms of the in terms of the finding the distribution of cascaded channels and the interference to the primary user, as well as the interference due to ambient transmission to the secondary users, and finding the finding the probability of packet errors, average packet error rate, as well as the we also analyze the latency, but because of the limitation, uh, I have not shown those over here, but those results are available in our paper recently, as expected at IEEE Internet of Things journal. And mainly the relevance to the RIS based scenario, the practical aspect would be in IoT networks, wireless sensor networks, and vehicular networks. Right, so these are the key areas where shorter packets are practically utilized, and we have use the integrate we have integrated the channel model, and system level simulation is done, and the results we have shown, right? So over here, the block length versus achievable rate can be the specification that may be pushed towards the standardization aspects of this. And then what are the views of the IIT Ropert? So mainly the RIS classifications are like, these are well-known types of RIS: passive star, active, and active star RIS. However, one aspect that probably is not looked upon is the relay versus RIS, right? So what thought is, when we have large number of RIS elements, right? So the RIS controller, in fact, there are so many biasing conditions for right now. We have pin diode based RIS controllers, right? So when we have pin diodes, these diodes are to be turned on and off. For that, the uh, biasing conditions are to be met, and yeah, particularly I'm not sure whether the when the number of elements will be very large, will it still be efficient than a relay in terms of energy, right? So this is the question. I don't know whether this has been answered or not, right? And then the simulation assumptions, mainly the idealistic simulation assumptions are considered, while the practical aspect of the RIS, right? So they are 1-bit RIS or 2-bit RIS, while in the simulations or the theoretical development, continuous phase shift is considered, uniform reflection coefficient is considered. Uniform in the sense that theoretically people consider that the magnitude of the reflection coefficient is always 1. The losses in the reflection are not taken into account. The RIS elements, they are considered to be uncorrelated reflections, and the cascaded channels of independent and non-identically distributed nature, these are considered, right? So maybe in the simulations or for the theoretical development, if this type of idealistic assumptions are overcome, that may bring towards the practical more realistic system models, right? So that is all from my side. If any questions, I would like to answer.
Thanks a lot, Brijesh, for the nice presentation. Do you have any questions in the online? Okay, so I guess then thanks once again, Brijesh.
All right, sure. Thank you.
Thank you. Over to you. Yeah.
Yeah. Thank you. Thank you, everyone. Thank you all who have been there online. And it has been a long day. Overall, quite an interesting session. I mean, we had speakers come from academic, we had speakers from the industry, we had speakers from the equipment vendors. Overall, while there's an optimism with respect to what is feasible through the RIS, and that's what has been presented from the various academic sessions, there is also a mechanism what the industry has presented to us stating that be cautious, they need more data, they wanted to see the results. But interesting use case which has come up is that within the industry applications inside, the coverage is not that great, and there could be a very practical application. That's what one of the person in the industry has stated. I'm really not going to take much time. I know it has been a long day to all of you, so really I'm very grateful for all of you to have spent so much time, and thanks for sharing your views, and thanks for participating. From COMET, IIIT COMET, and from IIIT Bangalore, from the director, Professor Das, I only say that we are looking forward to collaborating. We are looking forward to seeing how we can all come together to see what can be made meaningful out of this session, as well as what we can do in the RIS and what are the areas we can really work on. So would be glad to interact and collaborate. So with this, again, thank you all, and have a great day and great future ahead. Thank you.
Tushar, should we close the link?
Hello? Hello? Yes, sir. Please
Yeah,
close
should
the
we
session.
close the link? Yeah, thank you.
Yes, sir.